new materials through induced defects in nanomaterials and apply in different applications. So I will brief you about the physically induced defects in nanomaterials and which information we can extract and which properties we can change of nanomaterials. So first, I will give you some glimpse about Xi'an, Northwestern Polytechnical University, Xi'an. This is the campus of NPU University, and in 2019, we organized event conference there. And this is our university where my institute is located. Qaid Azam University, where NCP, National Center for Physics, is located. This is the building, small complex, National Center for Physics. So the contents of my presentation is objective of my talk, type of defects in crystals, then intentionally created defects and disorder in nanomaterials. Then I will brief you about the ion irradiation induced defects and disorder in nanostructure materials. And after induced defects, which kind of properties we can tune and control, I will discuss, and finally conclusion. So purpose of this center, Nano Center and Defects Engineering, and also purpose of my presentation is to different method to explore, to fabricate or synthesis of defective nanomaterials. Purpose is to explore the different type of methods to create defects in nanostructure materials and use advanced techniques or explore the techniques which are suitable to analyze these defects, quantify these defects in nanostructure materials. And finally, the purpose is to explore the applications of defective nanomaterials. This is our objective. So first I will brief you about the crystal defects. Then which methods are suitable to induce defects? You know, imperfection in the regular geometrical arrangement of the atoms in a crystalline solid. So imperfection exists without defects. Highly crystalline structure material is not easy to synthesize or develop. So defects exist in nanostructure, in crystalline materials. So defects are basically irregularity in the arrangement of constituent particles. All defects and imperfection can be conveniently considered under four main divisions. Point defects, there are the classes of the defects in the crystalline structure. Line defects, dislocations, planar defects, and finally volume defects. So one by one I will explain you. Here you can see point zero dimensions, point defects, vacancies, interstitials, Frankel defects, and Schottky defects. In one dimension line defects, we have edge dislocations, screw dislocations, and 2D, two-dimension defects are grain boundaries, twin boundaries, and stacking faults. And 3D volume defects, mainly voids, cracks, precipitates. These are the defects induced in crystalline structure. So you can see here point defects. One by one, I want to brief you these defects to revise your knowledge. So zero dimension point defects are in non-ionic crystals. We have vacancies, interstitials. In ionic crystals, the defects are related to Frankel defects and Schottky defects. You can see here, we can see missing of atom from atomic side is called vacancy defects in non-ionic crystals. Occur due to imperfection packing, or physically we can remove these atoms from the crystal. We can create vacancy defects. The impact of this defects is in the crystalline density of the substance decrease. If we have number of these non-ionic defects in the crystalline structure, the density decreases. Number of vacancy defects depend upon temperature. Another interstitial defects in non-ionic crystals. Addition of extra atom within a crystalline structure, crystal structure. You can see here, this is interstitial defects through chemical process are physically induced into the crystal structure, and this defects increase the density of substance, cause atomic distortion. Here in this plane, atomic distortion, if the size is slightly greater than, then distortion will be occur in the crystalline structure. So second defects is zero dimension defects. Point defects are Frankel defects, ionic defects. You can see here, sodium atom move from this plane and placed here, displaced this sodium ions from their crystalline position and displaced here, create, we can see here, and interstitial defects are created here. These are the combination of vacancy and interstitial defects. So these are called Frankel defects. And density no change. You can see here, no extra add atom from outer side is not placed here, just interchange, just displace their crystalline position. These are called the Frankel defects. Similarly, in ionic crystal, we have Schottky defects. Pair of anions and cations we can see created. We can see created. So here chlorine atom displaced, and here sodium atom. Pair of anion and cation we can see are called Schottky defects. In order to maintain electrical neutrality, the number of missing atom cations and anions are equal. In this defects, cations and anions are equal. It also decreases the density of crystal because atoms are removed from the crystalline plane. No, this is the vacancies, no atoms are placed here. So which of course decrease the density of crystal. These are the examples. Sodium chloride, these defects are established or exist in Schottky defects. So these are the line defects, missing of the lines in crystalline plane. Here line is missing. Lines are the irregularities in the, due to this line defects, the planes are irregular here. Deviation from the ideal arrangement in entire row of lattice points. So these are the line defects exist in crystalline structure. One dimension defects, we can say them. Surface defects, you can see on the surface grain boundaries defects and plane defects are exist. stacking faults. You can see these are the stacking faults here. These defects are created. These are the 3D defects. Volume defects exist in the materials. So the role of defects. If we treat the sample under temperature, these defects sometimes rearranged, sometimes saturated, and sometimes we can rearrange these defects. During rearrangement, we can, in nanostructure materials, we can weld nanowires, nanotubes. After creation defects and after rearrangement, it is possible to weld nanowires, nanotubes. Change in mechanical properties. These mechanical properties change if we play with the defects. Chemical reactivity increase. We can induce, suppose example, in carbon nanotubes, we can create surface defects. So these layers will be active, chemically reactive, will be chemically active to make bonds with other materials. So chemically reactivity increase. Crystal defects recombine to join nanowires, nanotubes. These are the role of defects in nanostructure material. Modification of physical properties like electrical conductivity we can change. Optical magnetic properties should be changed after create defects into the nanostructure materials. I will brief you all these tuning the properties after ion beam irradiation effects. So come to this slide. You can see here intentionally created defects and disorder in nanomaterials. So our purpose is to induce defects in nanostructure material. There are many methods. So one method is during synthesis route. During synthesis of nanostructure materials, we can induce defects in nanostructure materials. You can see here through chemical process. These are the high quality multi-wall carbon nanotubes. After treatment with H2O2, you can see amorphous carbon zones are created here. Disorder structure is created in multi-wall carbon nanotubes. You can see here disorder structure due to treatment with H2SO4, H2SO4 sulfuric acid treatment of synthesized multi-wall carbon nanotubes. If treated with sulfuric acid, you can see here defects are created. This is the chemical route. We can create defects in nanostructure materials. And nitric acid, we also observe same results. Disorder structure are created during nitric acid treatment. Sidewall defects are highlighted by circles, you can see here. These are the chemical routes. So other methods to create defects and disorder in nanostructure materials due to irradiations. This is the controlled and easy way to induce defects by electron irradiation, neutrons, laser, gamma rays, and ions. These are the different irradiation methods to induce defects in nanostructure materials and control the physical properties. So introduction of defects in nanostructure materials are thus an interesting way to tailor its intrinsic properties to create new potential applications. Irradiation process can lead to interesting, highly defective nanostructure material we can fabricate through these irradiations. So I give you some examples. Electron irradiation induced defects in zinc oxide nanowires. We focus these samples placed nanowires placed in TEM, transmission electron microscopy, and focus the electron beam here. And you can see plane defects here. Highly crystalline zinc oxide nanowires. Planar defects are created here. Merge plane here, and after bending, you can see plane defects were observed by focusing electron beam on zinc oxide nanowires using focus electron beam in HR, high resolution transmission electron microscopy. Just we create defects and get images, we publish paper in macro and nanoliter. So this is new research is started to create new type of materials. In gamma irradiation, I did this experiment in Ithimba lab, South Africa. We put nanostructure materials under gamma irradiations. And you can see here, hexagonal boron nitride nanotubes, nanoparticles transform into orthorhombic and boron oxide. New phases observed after gamma irradiations create defects and disorder created and rearrangement of atoms again. And we observe defects created, and after rearrangement of atoms, you can observe new phases, bond breaks and make under gamma irradiations. And new phase transformation was observed in boron nitride nanoparticles. So, and band gap was tuned, changed after. So another example, again in tin oxide, we irradiated gamma irradiation in Ithimba lab. So we tune the optical properties under gamma irradiation of tin oxide nanostructure materials. Nanoparticles, you can see here, high quality nanoparticle we irradiated under gamma irradiations and change the band gap. So we can tune band gap, and also we can transform from one phase to another phase during gamma irradiations. So what about the effect of ion irradiation on these nanostructure materials? So I will brief you. High energy particle accelerators are mostly used to create defects in the nanostructure materials. The irradiation process can lead to interesting, highly defective nanostructure materials. So this is the accelerator where we can generate ions into the ion sources, then apply high potential. We have this accelerator. You can use this facility. You can send sample or you can visit our accelerator lab, which is functional. You can use free of cost this accelerator facility, and you can do any experiment, material analysis, or induce defects or modification of the nanostructure materials or thin films. You can use this accelerator facility. So here we have two ion sources, apply high potential here to accelerate, generate and accelerate high energy particles, and finally we have work chamber here to put samples, and what you want you can get. These are the chambers where we can place sample in front of ion beam. So basic principle is this: generate, apply high potential and focus beam. In here we have different focusing magnets. Here also we have focusing magnet to focus the beam of ions, like this pointer, beam of photons, beam of laser, and we can get beams of different type of ions, carbon ions, elements like gold ions, silver ions, tungsten ions we can get through this accelerator with in mega electron volt energy range. When these ions interact with sample, what you want if you want to change the properties, you can irradiate here. If you want to extract elemental concentration, the ion beam techniques for material analysis. Also here we have different type of detectors. We can calculate, we can identify the elements in the target samples. So here our purpose is to create defects by these ions. You can see it has many applications. Time is short. So just when ions interact like this cue ball, interact with these red balls, it transfers its kinetic energy to red balls. Red balls displace from their original position to move some gain kinetic energy from this white ball and move somewhere in the Sloker table. So similarly, energetic ions when interact with thin films or nanostructured materials, of course, composed of these nanostructured materials composed of atoms. This ion displays their position of the target atoms, and these target atoms require to somewhere to destroy the crystal structure. Or if in energy if not enough, these ions could be implanted. If energy is enough, these ions pass through the thin films or nanostructured materials left behind disordered structure. And light ions break the bonding and rearrange again after stable state. When material under irradiation is stable, then after cool down, because when ions pass through the materials, the heat also generated along the path of ion track. So after in microsecond, it again cool down, the rearrangement of structure, observe phase segregation. So this is we install a unique technique to estimate the defects created by ion beam in situ structure. We have like PL, photoluminescence is used for defects analysis in the material. And ions also induce in the nanostructural materials or thin films, the light also emit. We collect this light information, give the information about the defects created by in situ, created by ions. So here we irradiate protons, hydrogen ions on lithium fluoride crystal. And you can see here, create defects. These are the defect centers observed using ion beam induced luminescence technique, IBIL technique. Light emit, we collect this light. This light is the information of the defects created by or exist in the nanostructure. So continuously irradiated with protons, you can see here defects are reducing. It means light ions sometimes improve the crystal quality. It means defects are reduced in lithium fluoride crystal. Different materials have different behavior under protons or under ions. So these defects are created. These defects were observed and reduced after continuous irradiation with protons with different doses. While in calcium fluoride crystal, the defects increases with increase the proton dose, with increase the proton fluence. So different crystals, different materials have different observations, different effects. So in calcium fluoride, defects created, you can see this technique, ion beam induced luminescence is very good technique with depth profiling. We can observe the defects through this technique. So another example, we create defects using argon ions in multi-wall carbon and at room temperature. We have high quality crystals here. And few at low dose, low fluence of argon ions, few defects, point defects are created, interstitial defects are created, and further increase the dose, disorder is dominated here. And you can see here in whole multi-wall carbon nanotubes, we observe totally disorder structure. And these multi-wall carbon nanotubes at high dose, at this dose, convert into the amorphous structure. So this unique amorphous nanowires, after ion beam irradiation, is the new class of material may be useful in nano devices. So this is the beauty of ion beam, to control the defects and disorder, and we tune the properties. So these are TM images. You can see here point defects, interstitial defects, dislocations, cross links are created by energetic ion beam. In carbon nanotubes, you can see loops are created, interstitial loops are created here, and observe dislocations, cross links. You can see the interstitial defects are created. So in silicon carbide, same behavior we have observed at different ions. Light ions have different effects, heavy ions have different effects. So we also use copper ions to irradiate on titanium dioxide. You can see here phase transformation observed. From anatase to rutile phase we have observed here. And surface morphology, you can see here change. From smooth, wavy type shape, we have observed the surface morphology after copper ion beam irradiations. You can see here surface morphology also changes. And similarly, we increase the energy of 8 mega electron carbon ions, and we observe different behaviors. You can see here defects are increased using PL, and phase was not changed with 8 mega electron volt. With 5 mega electron volt carbon ions, the phase anatase to rutile phase we have observed. But when we increase the energy of the carbon ions, it has different behavior. Different ions have a different behavior, different energies of ions have a different behavior. So there are a lot of data discrepancies. So we need to use different ions, different energies in nanostructure materials to create different class of defective nanostructure material. So it is broad range of research area. We can use this accelerator to study our nanostructure materials. So example, the physical properties you can change after irradiations. We observe the welding. So conductivity increase after welding, then decrease after with respect to the dose increase of the ions, energetic ions. It means initially welding we have observed, then at high dose, the multi-wall carbon nanotube, the structure are convert into the disorder structure. So that is why disorder structure have less conductivity as compared to crystalline structure. And we have observed transparency increase, you can see here. Conductivity decrease. These are the carbon after at high dose. We observe this multi-wall carbon nanotubes, and transparency you can see increase from 1.2 to 2.4. You can see the unit absorptions increase. Here transmission increase, sorry. Similarly, we irradiate silver nanowires, the conductivity increase with increase of the dose. So we can tune the conductivity of silver nanowires transparency of the carbon nanotubes. And band gap, you can see here, titanium dioxide band gap tune. We have 3.3. After at this dose, we observe the band gap is 2.9. So we can tune by induce the defects levels in Fermi level. So we can tune the optical properties, electrical properties. So recently we induced defects with my student and also colleague, Dr. Obodo. Recently he got the PhD from UNN. He used ion beam to induce defects and observe the enhance the electrochemical properties of these compounds, nanocomposites, and similarly when published in good journals. So after induced defects, new class of materials we can observe. So in also antifungal activity, antibacterial activity, if we induce defects in nanostructural materials, and antibacterial and antifungal activities also affect by these defective ion beam nanostructural materials. So finally, conclusion, the introduction of defects in nanostructural materials are an interesting way to tailor its intrinsic properties to create new potential applications. This is the purpose of our center and also of this presentation. Irradiation processes can lead to interesting, highly defective nanostructures. Finally, promote collaboration between research institutes. Networking, closeness, and personal relations are crucial to promote research activities. Thank you very much. Any question, please?
Hi, Dr. Ahmed. This is Jose
Hello.
Rajan from Malaysia. It's good to see you after a long time. I think we saw it during the last African Nano conference.
Yes, yes.
Okay.
Because due to
it's quite interesting work, and we really like it. But I have a quick question. What do you think? What would have been caused for this band gap to lower when it is irradiated with some energy radiation? Because
in the Fermi level, different defective Fermi level we created after ion beam irradiation defects levels in same material. Suppose we have titanium dioxide have band gap 3.3 between valence band and conduction band, different defects levels created. Due to these defects levels, reduce the band gap of semiconductor materials, not doped. During doping, we can also observe to lower the band gap. And similarly, we have also observed, recently we also observed in zinc oxide nanostructure materials. Due to these defects level created between the band gap.
Okay, thank you.
Okay, thank you very much. Any other question from the audience? Any question for Professor Ishak? Okay, thank you very much, Professor Ishak, for being here with us and for presenting the elaborate work that is going on in your laboratory. And thank you also for your collaboration with the Nano Research Group of the University of Nigeria. Thank you very much.
Thank you.
Yeah. So at this point, we want to invite a professor from the South Africa, Professor Omotayo Arotiba, who in 2009 received his PhD at the Sensor Lab of the University of Western Cape in South Africa, and who leads the electrochemistry research group at the University of Johannesburg, where his interest is mainly on application of electrochemistry to solving challenging environmental problems. Professor Arotiba, who has also published not less than 120 papers of journal publications with an H-index of 31 and over 3,880 citations, has graduated 12 PhD students and 19 MSc students, 15 of whom graduated with distinction. He has been guest editor for electrocatalysis and electroanalysis, and currently for catalysis, a member of Royal Society of Chemistry and International Society of Chemistry. May we welcome Professor Omotayo Arotiba to make a presentation. ICT. While he's getting connected, may I also inform you that Professor Arotiba carried out some postdoctoral research with 3 institutions from 2009 to 2010, the Sensor Lab in the University of Western Cape, Department of Chemical Engineering, the University of Cape Town, and the University of Johannesburg. He joined the Department of Applied Chemistry, now Department of Chemical Sciences, at the University of Johannesburg, South Africa in 2011, where he is currently a full professor and director of the Center for Nanomaterials Science Research. Currently, he is the chairman of the Electrochemistry Division, Electrochem SA of the South African Chemical Institute, and he is a SACI, South African Chemical Institute board member. He's a C1 rated researcher at the National Research Foundation of South Africa. While his main research leads the electrochemical, while he leads the electrochemical research group at UJ, his research interest is on the application of electrochemistry to solving challenges in environmental, water, materials, and biomedical fields. His focus includes, but not limited to, the development of photoelectrochemical water treatment technologies, electrochemical sensors and biosensors, materials electrochemistry, and nano electrochemistry. So we welcome him to make his presentation.
All right. Okay, I'm trying to set my timer so that I'm sure I'm not going to exceed my time, the time given to me. Okay, good morning from Nigeria, and I guess for other people around the world listening to this talk, it may be good afternoon, it may be good evening, maybe good middle of the night, depending on where you are. So, but I say good day to everyone, and it's a pleasure to be here to present what we do in our research group, and I'm grateful to the organizers for inviting me. Today, I'll be talking about nanomaterials in electrochemical, water treatment, and sensor technologies. Most of the things I'll be talking about will be the work that we do in our research group, the Electrochemistry Research Group, Department of Chemical Sciences. I come from the University of Johannesburg. It's a very research intensive university, and we are glad that we are making progress in many areas, including the world ranking, where we recently moved up to the 4th in Africa, as you can see on my screen. And also our department is very research intensive. For about 2 times now in the past 4 years, we have been ranked as the best chemistry department in Africa. And we are glad about that. And it's a sign that we are making impact in the area of research. I am the director of the Center for Nanomaterial Science Research. That center focuses on application of nanomaterials in many areas of research, as listed here: natural product, water, membrane science, materials and polymer research, electrochemistry, nanomaterial for biomedical applications, and so on and so forth. This slide summarizes what we do in our research group. I work with this amazing set of people, with our postdocs and our PhD students. So in our group, we work on analytical biosensors, photoelectrochemistry for water treatment, nanomaterials also for energy application, and we also work on ionic diode and rectification for electrochemical membrane science for desalination. Of course, I know that this group my listeners are from different background. I'm an electrochemist by training, so I'll just highlight some few things, some few importance of electrochemistry when it comes to sustainable and green technologies. Electrochemistry is the basic science behind electroanalysis. Electrochemistry, the science behind electrocatalysis that we use in fuel cell, photoelectrocatalysis that is used in energy storage, solar cell, water splitting, electrochemistry behind energy devices, batteries, supercapacitors, water treatment technologies, so that capacitive deionization, electrocoagulation, advanced oxidation processes. Electrochemistry is used in a lot of electrosynthesis and a lot of industrial application, which I believe many of us are familiar with. And in our research group, we use various types of materials, and some of them are displayed on the screen. We do a lot of work on carbon, different forms of carbon, carbon nanoparticle, carbon nanodot, diamond, carbon exfoliated graphite, expanded graphite, as some people call it. We work on different types of nanomaterials, nanoparticles. Recently, we've been doing a lot of work on semiconductors, and of course, we do work on dendrimers. And my talk is just to highlight the role of nanomaterials in our research. Okay, and generally, this slide summarizes what nanomaterials do in the area of electrochemical application. Number one, we use nanomaterials for molecular entrapment, the so-called host get chemistry. We use nanomaterials as molecular wires. We use nanomaterials for electrochemical signal amplification. We use nanomaterial to enhance the surface area of our electrodes. We use nanomaterials as platform for immobilization and also immobilization chemistry. We use nanomaterials as platform for electrocatalysis. We use nanomaterials as photoelectrochemical probes. We use nanomaterials as semiconductors in the area of photoelectrocatalysis. And also we use nanomaterials in the area of band gap tuning and so on and so forth. I will start by, my talk will go in three ways. I will talk about biosensors, I will talk about sensors, and I'll talk about water treatment. Electrochemical biosensors is defined as a device that incorporates a bioreceptor onto a transducer surface, and in the presence of analyte, it produces measurable signals that are proportional to the concentration of the analyte. So I will explain that by just doing this illustration. So what is a biosensor? Number one, a biosensor is a device that incorporates a bioreceptor. Now, this bioreceptor can be an enzyme, it can be DNA, it can be an antibody or an aptamer. So the biosensor incorporates this bioreceptor onto a transducer surface, and the transducer surface can be made of the electrode and an immobilization layer. The immobilization layer can be a dendrimer, can be a polymer, and the transducer is usually an electrode of this kind. And in the presence of an analyte can be cocaine, it can be DNA, it can be glucose, there will be a biorecognition event between the bioreceptor and the analyte. This event will give signals that we can measure in form of current, light, impedance, and mass. So if you look at this scheme, you will see that at this point of immobilization layer, that is where a lot of material science come to play, because we are trying to put the bioreceptor onto the transducer. So there must be a kind of a platform, a layer, a connector that allows us to do that. And that is where a lot of material chemistry comes into biosensor development. Biosensors have been used in many areas, medically, environmentally, and in the food industry. And there are many examples of biosensors that have made their way to the market. But of course, the most successful biosensor to date is the glucose biosensor. That is the one being used by diabetic, or you can use it in the hospital to know the level of glucose in your blood. Biosensors are generally based on two philosophies. The first one is biomimicry, and the second one is simplicity. In biomimicry, what we are doing is that we are trying to copy nature, because we know that this DNA, this enzyme, they do an excellent job in the body. So we are trying to copy what they do so well in the body outside the body. So the idea, the philosophy behind biosensor is biomimicry. And this guides us in the choice of material that we use. Another philosophy is simplicity. We want something that anybody can use. For example, the pregnancy test can be used by anyone. The glucometer can be used by anyone. You don't need to go to school to get it done. But there are challenges in biosensor development, challenges in the area of sensitivity, reproducibility, biocompatibility. And to solve these problems, we have to optimize some essential steps, which include immobilization chemistry, immobilization layer, biorecognition, and so on and so forth. If you look at what I have in this rectangle, you will agree with me that for you to begin to look at immobilization layer, then you must be thinking a lot about material chemistry. So materials come into place. And if we're talking about immobilization chemistry, it means the type of bonding that goes on our biosensor surface is also important. And we have to make sure that the chemical interaction is close to the one that happens in nature. And of course, the chemistry of nature is usually supramolecular. Okay, one example of a substance that is used, that we use in biosensor is dendrimer. When you look at the structure on the screen, you will see that this looks like nature because this is how the alveoli in our lungs are arranged. And even if you look at the tree, you will see this dendritic structure. So this is also biomimicry. We are trying to look at how nature is arranged. And dendrimer has this natural architecture, and it gives us an idea that the bioreceptor may be able to identify with it. We've done a lot of comparison between our dendrimer and DNA, and we found that they have a lot in common. They are 3D structured, nanostructures, respond to pH, and so on and so forth. So we can see that looking at the two properties, we can come to a conclusion that dendrimer can be DNA friendly. Okay, and when it comes to supramolecular chemistry, this is the chemistry of nature. For example, the chemistry between single-strand DNA combining with another single-strand DNA to form double-strand DNA is supramolecular. The tobacco mosaic virus, in terms of its arrangement, the self-assembly arrangement is supramolecular. So we are trying to copy the chemistry of nature and apply it in our design for biosensors. And dendrimers have been shown to be very good for host guest chemistry, for self-assembly, and for self-organization. And in our lab, we use dendrimer for the following, we use dendrimer in the following areas. Number one, we use dendrimer as a molecular house for our bioreceptors. So you could see that in the structure of the dendrimer, there are many nanovoids where we can entrap our biomolecule or our bioreceptor. So this is called molecular entrapment. So we use dendrimer, which is a nanomaterial, as a molecular house. Another thing we use dendrimer for, in case maybe we have a redox active dendrimer, we can use dendrimer as a redox mediator. What does that mean? Here I have the structure of an enzyme. Here is my carbon electrode. So I need a material that can shuttle electron from the enzyme onto the electrode and take electron back to the enzyme. So we use dendrimers and some nanomaterials as a redox mediator in biosensor development. Another thing we use this for is molecular wiring. For most enzymes, their active redox center is buried in the middle of the enzyme. So we need a material that is small enough to penetrate like a needle into the enzyme so that it can be able to collect electron from the center and drive it to the electrode surface. And of course, for number 4, we use nanomaterial to amplify our signal. Okay, so those are the 4 things we use dendrimer and dendritic nanocomposite for in our research. So let me just give you an example of how we build a simple biosensors. So what you have on your screen is a screen printed electrode. Okay, and in this screen printed electrode, the first thing we did was we electrode deposited the dendrimer onto the carbon. So we have what we call the carbon-nitrogen linkage. So after electrode depositing, we call it a dendrimer modified electrode. Then we now immobilize what we call streptavidin. Now, the relationship between streptavidin and dendrimer is supramolecular because at a neutral pH, the dendrimer, which is polypropylene imine dendrimer, is positively charged, it's cationic. And based on our understanding of the isoelectric point of ceftazidime, we know that it is negative at pH of 7.5. So now we have a negatively charged ceftazidime, a positively charged dendrimer. Then we now have what we call electrostatic supramolecular interaction. So the chemistry is not strong, the chemistry is not harsh, so the molecule can still behave the way it behaves in nature. Why are we using streptavidin? We are trying to look for a way to anchor our antibody or our DNA onto the surface of the electrode. And we know that in nature, there is a very strong bond between streptavidin and biotin. So what we did was that we took our aptamer, we biotinylate our aptamer, that is, we added biotin to one end of the DNA, then we now drop it on the electrode. So what happens here, again, we are copying nature. So the biotin binds strongly to the streptavidin, and in such way is anchoring the DNA onto the surface of the electrode. Now, this setup is now our biosensor. So when we have this setup, we can now introduce our analyte in solution. A drop is enough for that. Then what we did in this work, we were trying to study how to detect HIV virus using the envelope protein called GP120. So this aptamer is able to bind to the GP120 to give us some signal that we can use to do the analysis of this protein in sample. So this is a simple design of a biosensor. And we have used biosensor also, we have designed biosensor based on nanomaterial for detection of many biomedical substances. One of them is cholesterol, as you see in this work. How did we do it? Again, we immobilized our dendrimer by electrodeposition. Now, we deposited a nanomaterial. This is a quantum dot, okay? So we now put quantum dot on the dendrimer. Then we now immobilize our enzyme. In this case, we use cholesterol oxidase. We know that in nature, cholesterol oxidase will always react with cholesterol. Just like glucose oxidase, we always react, the natural substrate is glucose. So you can see we are just copying what goes on in nature. So we have our cholesterol oxidase enzyme on the electrode. Then we can now introduce a solution containing cholesterol, and we can now measure the amount of cholesterol in the sample. Just a little bit of electrochemistry to show you how we use nanomaterial in this biosensor development. If you look at what I have on the screen, it's just a typical cyclic voltammetry. Now, you will see here that this blue, which is labeled D, has the highest current. I just amplified here. Why does it have the highest current? You will see it is because we have glassy carbon electrode, we have the PPI, is a dendrimer, QD is our quantum dot. So by immobilizing these two nanomaterials, we're able to amplify the signal coming in from our electrode. Without this biomaterial, without this nanoparticle, our current signal was low. Then we also did impedance measurement, which tells us the resistance to the flow of charge. So that means the more the resistance to the flow of charge, the less the current. So it's opposite in a way. And you will see that the electrode that has the highest current has the least impedance in this case. And we also saw that when we have this nanomaterial, it helps in the electrocatalytic reaction. For example, you see here that, look at the red line, see how big and enhanced it is in comparison to others. It is because of the presence of a nanomaterial that acted as a suitable layer upon which we can put our cholesterol oxidase so that it can now undergo electrocatalysis with cholesterol in the sample. So we did some measurement. Of course, we did interference studies, uric acid, ascorbic acid, glucose, and we tried to do the stability of the biosensor. Another area of interest is biosensor in cancer, cancer detection. And you heard a little bit about cancer yesterday. And this is one paper. I hope I put it intentionally so that in case we can copy it and read it. It's a recent paper on 2020 analysis of cancer globally. And you will see here, worldwide, 19.3 million new cases of cancer in 2020 alone. And out of this 19.3, 10 million died. And breast cancer has now overtaken lung cancer globally. So breast cancer is the highest, breast cancer is the most prevalent cancer globally, and followed by lung cancer. However, lung cancer remains the leading cause of death globally. And I believe those of us who smoke should have a second thought in this, based on those statistics. And one of the things we see is that the early diagnosis of cancer remains the key issue in cancer therapy. So can biosensor contribute to cancer research? Yes. One of the ways in which we can contribute to cancer research is by looking at biomarkers. Okay, so we look at biomarkers because biomarkers give us an estimation of what is going on in the body, because your body begins to produce some chemicals as a result of some strangers in the body. So we can use it to monitor the progress of therapy. We can use biomarkers for early detection. We can use it to reduce the cost of cancer diagnosis. So what we do in biosensor is that we now try to develop a biosensor that can target those biomarkers. A good example is carcinoembryonic antigen and so on and so forth. This slide is just trying to give some analysis of how much money we can save if we use biosensor for detection of cancer rather than the other methods that are being used. So we can, this is a simple scheme. Again, we can use dendrimer, we can use nanoparticle, then we can put an antibody that is specific to the biomarker. Okay, in this case, we have an anti-AFP specific to AFP. Then we can do some measurement and measure the amount of biomarker. So we've done some work in this area where we have been able to detect alpha fetoprotein using dendrimer as platform. We have been able also to use carbon nanodots and dendrimer as a platform for detection of this cancer biomarker, which is carcinoembryonic antigen cancer. We have also used some other nanomaterials to be able to, as a platform, to detect alpha fetoprotein in serum sample, which is closer to real sample. So a lot of biomarkers have been discovered, and possibly biosensors may be developed for them. We can also develop biosensors for other things apart from biomarkers. For example, in this case, we use an aptamer to detect cadmium, which is an ion. So an aptamer is a DNA that is able to fold around a certain analyte. So you could see here that by using gold nanoparticle, we can amplify the signal of our biosensors. And we have used a similar concept to detect arsenic in water. Let me quickly go to sensors. I have 9 minutes left. First, we can also simply, sensors are just biosensors without a bioreceptor. Okay, so we don't need any biomaterial, we don't need an enzyme, we don't need a DNA, but we rely on some electrochemical reaction that goes on the surface of the electrode. We have used nanomaterials such as bismuth nanoparticle to prepare a biosensor, to prepare a sensor that can detect these toxic metals simultaneously. So we did a work where we were able to detect lead, arsenic, and mercury simultaneously in water sample. And we can see here that nanomaterials can be used to improve our detection limit. Recently, we published a work where we were trying to detect bisphenol A in received paper samples. And we see from this slide that by using silver nanoparticle, we're able to markedly increase the signal of our electrode just by adding nanomaterial to it. And also nanomaterial helps us to separate the different peaks at which some materials can be oxidized or reduced. In this case, we prepared a biosensor that we can use to detect cholesterol, ascorbic acid, and uric acid simultaneously. And coming to the third part of my work is the area of electrochemical technology and for water treatment. This is very exciting. It's one area I'm trusting to push to the area of proper application in the industry. Electrochemical technology is the application of electrochemistry in the design and development of devices that can offer solutions to problems. We know we have water challenges, and the conventional method is becoming an issue because it cannot treat some certain pollutants in water. Some of them are recalcitrant. They cannot be treated by the usual method because they are very stubborn. So there is need for us to begin to develop new water treatment techniques that can remove these very stubborn organic product or organic pollutants from water. Not only that, it's good to have a mix of different techniques. Depending on the nature of the feed water, we can have a kind of a cocktail of water treatment approaches that can deliver water at rural areas and even in urban areas. So that is our area of research. And electrochemistry comes in handy because it is cheap. Okay, I think I'm having problem with connection. I think I've been logged out. My screen cannot be seen. It shows. Okay, I'm interested in seeing my slide, not myself. I know how I look.
ICT, please.
Okay, thank you very much for reconnecting me. I'm sorry for that little break in transition. Of course, it happened. All right, let me continue from where I stopped. So what we do is, many of you may be aware of photocatalysis. Photocatalysis is also one of the methods of treating water that is very common, where hydroxy radicals are produced, and this radical oxidize the organic in water. Now, but the challenge of photocatalysis is that there's the likelihood of recombination of the hole and the electron produced at the semiconductor. So what we do in electrochemistry is that we now add electrochemistry to this concept so that we can use our electrodes to drive, we can use potential to drive away the electron further from the semiconductor surface so that it reduces the chances of recombination. So in our research, you will see that for us to limit electron hole and for us also to be able to narrow the band gap of the semiconductor, because we don't want to use UV, we want to be able to use white light or solar light. For us to do this, you will agree with me that it has to do with a lot of understanding of electrochemistry, material science, and nanotechnology. So electrochemical water treatment technology is now becoming an interesting area of research, where we have electrochemical oxidation, photoelectrochemical oxidation, we have solar photoelectrochemical oxidation, and different types of approaches using electrochemistry. I'm still seeing that the screen here is different from the one there. Okay, so let me just give example of what we have done in this area of research. We used a semiconductor, but in a nanoparticle dimension, tungsten trioxide. So we prepared tungsten trioxide, we immobilized it, or we deposited it on an electrode surface. In photocatalysis, you have the semiconductor, you pour it as a powder into the solution. So there's a challenge in that, because after treating the water, how do you recover the semiconductor? How do you recover the photocatalyst? But in electrochemistry, it's a different approach. We do not just disperse the photocatalyst in water, we immobilize the photocatalysis on an electrode surface. So it's already localized, it's not all around. Then the reaction takes place at the surface of the electrode to generate the hydroxy radical that can treat the water. So what we do, we now use sunlight, or we use a solar simulator to shine light on the electrode surface. When we do that, we now begin to create hydroxy radical from this reaction. And the hydroxy radical now can begin to attack the pollutants in water, degrading them theoretically to H2O and CO2. So nanomaterial materials in the nano dimension have been used to enhance even the results in this area of research. One of them is this. If you look at it here, this is our electrode, our EG electrode. This is absorbance. So in the visible region, as you can see, 500 to 800, in the visible region, the electrode itself is not photoactive. But when we now put a semiconductor in the nanoparticle range, we could see that the absorbance increased. This shows that we have been able to prepare a photoactive electrode, which we call the photoanode. Then we now did different type of experiment to see the effect of light. So when we put off the light, we see this black. When we put on the light, we see a photocurrent generated. When we put the light off, it goes back. When we put the light on, it goes off, on. So we see that the electrode is photoactive. So we have used that to remove different types of organic pollutants from water, ranging from dye to pharmaceuticals and so on and so forth. And we've combined this method, or we've compared this method with photocatalysis. We have compared this method with ordinary electrochemical oxidation, and we have seen that photoelectrochemical oxidation has a lot of advantages in this area of research. So based on our analysis, we're able to remove 71% of the pollutants in the water sample. And we have also used nanomaterial to enhance the photocatalytic activity of our semiconductor by using dopants. So here we have zinc oxide, which is our semiconductor. We were able to now dope it with silver, and we're able to now use reduced graphene oxide as an electron sink to reduce recombination. And you could see from this result that we're able to improve the absorbance in the visible region, and we have a very high amount of degradation of the pollutant. Also, we have used materials in the nano dimension. When it comes to photocatalysis, titanium dioxide is the most popular, but the challenge is the large band gap. And from our previous speaker, we could see also that when you tune a material to the nano dimension, you can reduce the band gap. So here we prepared nanotube arrays. You could see the nanotubes of titanium dioxide. We now put copper 1 oxide on top of it. What we are doing actually is forming an heterojunction of two semiconductors. So by forming an heterojunction, we are able to now delay the recombination. Then we have improved our degradation capacity. So also here we use silver sulfide as a nanomaterial and a semiconductor to form an heterojunction with bismuth vanadate, and we have used it to remove antibiotics from water. And I'm just trying to round up. Here also we have used nanomaterial for electrocatalytic preparation or generation of hydrogen peroxide, because in Fenton process you need to generate hydrogen peroxide. So here, by modifying or tuning our nanomaterial, we can generate more peroxide, which can lead to more OH radicals to treat the water. In case you want to read more about our work, we have this review that tells you about some of the things we've done in this area of research. And lastly, we are looking at membrane for the treatment of water. The idea here is desalination. We know that when you want to remove salt from water, we have to use the reverse osmosis membrane and all the rest, which is very power intensive or energy intensive. What we want to do in electrochemistry is that instead of using pressure, as you see in reverse osmosis or arrow membrane, we are trying to use electrochemistry by putting different charges. And now we can use the charge to push a particular ion across the membrane and solve the problem of saline water. And in this is a simple example. We put salt here, then a second ion can flow through. So we select the material to permit a second ion to flow through while the remaining one stays there. So we have used nanomaterial in this area of research. We observe that by modifying nanomaterial, we can change our rectifier to either cationic or anionic, depending on what we are looking for. In conclusion, we can say that nanomaterials play a very important role in improving. There we go again. Just concluding. Let me see again what the problem is. Make sure I'm still connected. My apologies. We're trying to reconnect again. I'm concluding. It's important I conclude so that I don't keep you hanging. All right. In conclusion, nanomaterials play an important role in improving electrochemical processes. Nanomaterials can be used in immobilization chemistry, in temperature catalysis, and nanomaterials can be important tools in technologies related to health and the environment. And I would like to acknowledge the Nano Research Group, especially all the colleagues I know there, Professor Fabian Ezema, and the rest for inviting me for this conference. I'd like to, of course, acknowledge my university, University of Johannesburg, Electrochemistry Research Group. That is the group that I lead. And I want to say thank you to all my funders for their support in my research. I also want to acknowledge my family for the support, and most importantly, acknowledge God who has helped me thus far. Thank you.
Thank you very much, Professor Motayo Aroteba. So thank you very much for the presentation, and we will take another presenter before. Please keep your questions after the next presenter. We'll take an interlude of interaction between the presenters and those who are participating in this conference, whether from here or those who are joining us via Zoom. The next presenter we're going to take now is the presenter that was supposed to participate in yesterday in the presentation, but he obliged the other presenters to get involved so that we'll manage our time properly. And today we will have Kenneth Ozemena, who is a professor of materials for energy and electrochemistry at the University of Wits in South Africa, whose current research interests are on material science and electrochemistry with a focus on advanced materials for the next generation clean energy technologies, which includes lithium-ion batteries, lithium-sulfur batteries, sodium-ion batteries, electrochemical capacitors, and fuel cell technologies, as well as development of smart electrochemical sensors for health and environmental applications. May I inform you that Professor Ozemena got his Bachelor's of Science degree in chemistry from Abia State. From Abia State University, Uturu, MSc, University of Lagos, double MSc, MSc in chemistry, MSc in pharmacy, and his PhD from Rhodes University in South Africa. He is a certified renewable energy professional of the Association of Energy Engineers in the USA, a fellow of the African Academy of Sciences, a fellow of the Royal Society of Chemistry, and a member of the Academy of Science of South Africa. He has published over 150 peer-reviewed articles, anchored and edited books and book chapters. May we welcome Professor Kenneth Ozemena to make his presentation. Okay. Okay, I'm fine. Okay. Good morning, good afternoon, and good evening, colleagues all over the world. Thank you, MC, for the introduction. My presentation is, oh, no, not that one. This one. Okay. Okay, my presentation is simply, I just want to okay. Sorry for the interruption. I would just want to summarize some of the things that we are doing in my research group. So I'll just focus only on energy and health, but most importantly on energy today, because we have already covered a lot of health since yesterday. So as the MC says, my name is Ken Ozemena, and I'm from University of the Witwatersrand in Johannesburg, South Africa. I hold a research chair in materials, electrochemistry, and energy technologies. I will tell you more about that. This is our group website. If you want to know more about what we are doing, I don't know why my email is not there, but it's okay. Okay. Moving to the next. Okay. Okay. So first of all, before I continue, I would want to pay special tribute to these colleagues, Professor Emeritus Rose Osuji, Professor Fabian Ezema, and Professor Paul Ejikeme. These are the best in the world when it comes to this kind of thing here. Yes, I'm really very glad to partner with them. They have been holding the fort since the beginning of this Nano research group. People all over the world may think that this group has been here for more than 2 decades, but it's not. It's still about 7 years. But you can see what they have achieved within this short period of time. I want to thank them for their resilience. I want to thank them for their hard work. In fact, they are the definition of what hard work is all about. Their can-do attitude. They have been, it's not just getting money from the university. They have gone all over the world to get money to make sure that they survive. So anything can happen. If you are good, you are good. It doesn't matter where you are. So I want to congratulate them again and also to thank them for always inviting me to be part of this meeting. Okay, this is, since we started the collaboration, we have had several interactions, public co-authoring of papers, and last year we were involved in an EU application, research funding, and we succeeded. It's really amazing. And I think it's because of what they are doing here, because if it had not been good work, this proposal wouldn't have been successful. We got this funding for 5 years, and it is all about training of PhD and master's students, as well as their mobility, and then for academic staff mobility. And I tell you, there were, from the result, they gave us 117 applicants from Africa, and we were among the 6 that succeeded. So it was, success rate was just less than 5%. So you can see how competitive this thing was. And we are really glad to be part of the people who succeeded. So the project will be run by 5 African universities. My university, WITS, Addis Ababa, which is our coordinator. Then University of Nigeria and Soka, as you can see the logo, the Cairo University. And then there's another university that is Addis Ababa Science and Technology University. We have actually advertised for this
position, I just want to remind you, just take you can Google, look at everything is there, the web link is there. It is a 5-year program, so we train masters and PhD within these 5 years. The interesting part of this is if you are from Nigeria, you cannot study at UNN. You have to come to South Africa or you go to Ethiopia. So if you are from Ethiopia or South Africa, you can't be there. You have to come to Nigeria. So this is why we want our labs here to be functioning well. We don't want to bring somebody from South Africa or Ethiopia and they're complaining that they don't have research facility. You understand the rule? Okay. So I'm from Wits University. I know that some of you have seen this presentation before, so please pardon me. But we are celebrating our 100 years centenary next year. So I'm obliged to share the good news. The university has been around since 1992. It became a university in 1904. It was transferred to, it used to be a school of mines in South Africa, in Kimberley, and then moved to Johannesburg in 1904 and became a full-fledged university in 1922. So next year we will be 100 years and we'll be celebrating it. We have got so many accolades, I don't want to bore you again, but for now, everything we do is for good. People who have studied with us have gone on there to become the best in their career all over the world. We've got Nobel Prize, people who have won Nobel Prizes, people who have also got a Rhodes Scholarship, and so many of them. We have, it is a research-intensive university. We have over 80 countries, nationalities there. So it's quite a big university. And we invite everybody, if you qualify, please just apply and you get admission. There's no doubt about that. Every subject under heaven is done at the university, from natural science, medical, health, social science, humanities, engineering, and technology. So no excuses. Okay, so this is my own research chair. We started a new research chair this year. We were awarded a research chair this year that should last for the next 15 years, 5 to 10, 15 years, depending. So we call it a Materials, Electrochemistry, and Energy Technologies. That is the name of our research group, and is funded by these 3 organizations, South Africa's Department of Science and Innovation, the National Research Foundation, and the University of the Witwatersrand. So so we're really glad to be funded by these organizations. So the question is, what are we doing? We are focusing on, as the name implies, materials electrochemistry. Anything material science, we are involved. Then energy technology. So our team is all about electrochemistry and all about nanomaterials. So we have 5 different research clusters and activities. So for example, the first one there you see is the modern rechargeable battery. So we go from lithium-ion batteries to lithium-sulfur batteries, sodium-ion battery, zinc-ion battery, zinc-air battery, any type of ion battery, metal-ion battery. We are involved in. We also work in the area of electrochemical capacitors. So we research on supercapacitors, supercapacities, lithium-ion capacitors, sodium-ion capacitors. In the area of fuel cells and electrolyzers, we are involved in PEM fuel cell, polymer electrolyte membrane fuel cell. Just to generate energy, fuel cell is about energy conversion. We're also involved in alcohol fuel cell. Instead of using hydrogen as your fuel, we can use normal alcohol with oxygen, normal atmosphere. We can generate electricity. That's the kind of research we are doing. We are also involved in solid-state electrolytes. The problem with some of the energy systems is the use of liquid electrolytes. They are quite flammable. So we are trying to find an alternative. Can we use solid instead of liquid as our electrolytes? So that's the kind of work we are also involved in. And finally, we are involved in electrochemical sensor. My brother and friend, Professor Omatayo Arotiba, has already told you everything about electrochemical sensors. We are also partly involved, but we are focusing only on tuberculosis. We want to detect tuberculosis. Actually, recently, last week, on the 7th of this month, we got a patent on the detection of tuberculosis. International patent, we have now filed for international patent, PCT. We are also involved in detection of cholera. I understand that in Nigeria, in the northern part of Nigeria now, since this month or so, there have been, there's a cholera outbreak. There are 20 people have died, I'm told, and there are about 300 people who are hospitalized because of cholera infection. So we have also done since last year, between 2019 and last year, we published about 3 papers in this field where we can use antibody, antigen, immunosensing technology to detect cholera very fast. So, and now the other one is HPV, or human papilloma virus, that causes cancer, cervical cancer. We have some funding now from UK, from our colleagues there. It's going to be a 2-year funding program. We are working seriously on detection of using electrochemistry to detect HPV as fast as possible. And the last one we talk about, that is drugs. We also are involved in detection of drugs of abuse. Talk about alcohol, you talk about tramadol, any drug at all. We have a way of using electrochemistry and nanomaterials to detect them very fast in the environment. So our research, we work from basic science, from basic research, technology readiness level, from 0 or 1 to, we can go up to 7. In other words, we can go from basic to applied, prove the concepts, demonstrate the technology, and if possible, we transfer the technology to industry. That is our aim. So but today I'm not going to talk everything. I will just choose 2 or 3 areas and discuss with you. As I continue, lest I forget, this I think we should have I think by now we should be having a special issue for this conference. We have come of age. But this one I'm showing you is not for this particular conference, but just to tell you, if you are able, if you know that you are working in the area of electrocatalysis and energy system, look at the metal air batteries, metal sulfur batteries, any energy system that employs a nanomaterial for electrocatalysis, just you are invited. But this special issue is only for short reviews. We don't want original work, short reviews. So you are invited, you can contact me. If you're interested, my email is there. It is an open access. This is a very good journal, you know. I've been involved with this journal since 2007. So I've been an editorial board member, but this one I'll be the managing editor for this particular issue. And our impact factor is not small, at least 4.7, almost 5. So it's a very good journal. So if you are interested, we don't want to take more than 15. We want like 15. So if you are interested, please let me know. We want to do, the submission would end around November. Short review to the point. You will pay for that. It's open access. But you can also talk to me. We have a way we can reduce the price for you. But this is where the world is going, open access. There is no way you can't avoid that. Okay. There's another one that this will be happening later part of this year. It's called the catalysts. Again, impact factor of this one is quite high, over 4. It's another open access, but this one we would want both original submission and review submissions. So if you have more Any question, just contact me. Okay, so I've already shared this slide with you. So let's talk about advanced battery systems, advanced rechargeable batteries. There are so many of them in the world, you know, there are so many of them, I can't even mention all of them. We have the lithium ion battery has always been there, but we have what we call the next generation batteries systems like the lithium sulfur batteries. This type of batteries use electrocatalysis, employ electrocatalysis to do so. So you want to make, there is no way you can do them without making sure that your electrocatalysts are nanostructured. That's the only way you can improve their performance. So lithium sulfur is there. Lithium air battery is a bit tricky, it's still at the experimental stage. But lithium sulfur, we can get into that. There's the redox flow battery, there is the zinc air battery. I will talk to you about zinc air battery briefly. Then there's the sodium ion battery. These are green kind of batteries. Yesterday we heard about electronic wastes. If we are using, say, zinc A is your fuel. Ordinary A is your fuel, and then zinc is your anode. You can imagine what can be greener than that. And they compete with lithium ion batteries in terms of capacity and energy. I will talk about that. So this is, I've shared this slide before. So we have these types of battery from lead acid, which is the one we are used to, lead acid battery. We have the nickel cadmium, nickel metal hydride, then lithium ion battery, the conventional one. If you're using it to drive your electric cars, maybe you go up to 160 kilometers before you can recharge it. But if you go, we have what we call the future lithium ion battery, future ones. Those are ones with a high energy. I'll talk about that. Then there is the zinc air battery, the one I'm telling you about. Zinc air battery is purely, aqueous, but you can see the energy, high energy, the energy is much higher than that of even the future lithium ion batteries. And it's a research you can do here. It's not, you don't require expensive and fancy research equipment to engage in zinc air battery. All you require is your alkaline. Do you have an alkaline? Electrolytes, sodium hydroxide, potassium hydroxide. You go buy your zinc plates, zinc foil becomes your anode, and then you make your catalyst, nanomaterial as an electrocatalyst. You can make that. So I think Fabian, we need to talk about this. The nano group is, I think, is an easy research area in my view. Okay, then there is the lithium air, which is quite still is a very difficult research area. I don't encourage anybody to do that here. Lithium air, no. Okay, lithium sulfur is something we can also work on. So the reason why lithium battery has always been there is because of these properties, high energy, both gravimetric and volumetric energy densities compared to all the known batteries today. And the reason is because of what lithium ion battery has as its properties. Now we have the prices of lithium ion batteries are coming down, and of course the applications keep increasing. And this is from Bloomberg. They predicted that by 2030, you will see that we will have more passenger electric vehicles. Let's see how we are still in 2021 here. So it will continue to increase, followed by electric buses, followed by consumable electronics, like the ones all of us here have, and then stationary applications, the one you can use in your homes or your offices. You just use your store energy from solar, you store it. In the evening, you use the energy during the day, you use solar. So I'm glad that we have also covered that in the course of this conference. So this is what I was saying. In 2010, about 10 years ago, lithium ion battery price was $1,200 per kilowatt hour. Today is crashed. The price has crashed, and then the prediction is by 2030, in about 8 years' time, we can buy lithium-ion battery, barely $62 per kilowatt hour. Okay. And then because of that, electric vehicles will continue to increase. Okay. So according to the same Bloomberg, they said that wind and solar technology will supply almost 50% of the world electricity by 2050. So we better get prepared for this. I always try to give this information so that we prepare our mind and our research IQ. Where do we want to go? If they say that by 2050, 50% of world electricity will be coming from wind and solar, it would be foolhardy on you to be thinking about any other type of electricity. Okay. Then China will continue to dominate the markets in the area of wind and solar. They will grow by 48%. They will, almost half of it will be coming from China. By 2050, renewable will provide 96% of Germany's generation, reducing its emission by 97% of what it is today. This is the prediction. The whole of Germany, 96% of the electricity will be coming from renewables. The same thing happened by 2050, 40% of all battery deployments will be behind the meter technology. Behind the meter means you are not depending on NEPA or on grid to give you electricity. You have to generate your own. So you are actually behind the meter. Or you don't want to be in front of the meter. Being in front of the meter means that NEPA will be giving you, or grid system. I forgot that this is international. People don't understand NEPA. So I mean, I'm talking about on-grid electricity supply. So, and then the payback period, if you are into PV, solar battery, solar plus battery technology, if you start that business, they said by 2040, the payback period, you will get back your money by, it will reduce within 6 years. Today it is about 13 years. If you go into that business, it will take about 13 years to recoup your money, start making profits. But within 6 years, by 2040, it will be like that. And then by 2050, businesses and households invest $1.9 trillion in behind the meter technology. And this is, of which $50 billion per annum is on small scale PVs. So small scale PVs will dominate. You go, we were there yesterday where I think it's a small mall where people are doing businesses. They don't need this electricity. They can actually generate their own electricity. Okay. Let's say Africa is actually lagging in this field. So I don't know, it's not good news. Unfortunately, Africa is lagging in BTM, behind the meter, which is an important technology that has been predicted to create an additional $1.1 trillion in energy storage value by 2030. In the next 7, 8, 10 years, it's not up to 10 years, 8 to 9 years. This is happening. So behind the meter is coming. Okay, but I'm not going to talk about lithium-ion battery. One of my postdoctoral fellows, Dr. Aderemi Haruna, will be talking online. I don't know when he will be presenting, so you can listen to him. He will be talking about manganese-based cathode material for high-energy lithium-ion battery. He will be focusing on lithium manganese nickel oxide and lithium manganese oxide. Okay, so let me talk about rechargeable aqueous zinc air batteries. As I said, it is simple. It is indeed simple as simple can be. You see, you have your anode made up of zinc. You have your electrolytes, KOH. For KOH, is there anybody who doesn't understand KOH? Is potassium hydroxide. Unless you're in the physics, they don't understand chemistry too much. So it's a potassium hydroxide chemist. And then you require your cathode. Your cathode is air, ordinary air. As I'm talking now, the air is going into the cathode. But for that air, you have to do what we call ORR, oxygen reduction reaction. You have to reduce oxygen that you are generating, and you require electrocatalysts to do that. You have to also evolve. Oxygen has to evolve, and you have to do that by using electrocatalysts. And the best electrocatalysts for doing this reaction are those electrocatalysts that are nanostructured. Remember the theme of this meeting. So as I said, it uses your air, oxygen. The raw material is in abundance, is environmentally friendly, it's low cost, it's safe. The energy density, the specific capacity energy density is over 1,000 watt-hour per kilogram. People in electronics and physics will understand this. Watt-hour per kilogram of material, which is 5 times greater than that of lithium-ion battery. It is highly promising for renewable energy storage. The low cost, you can buy it $10 per kilowatt hour. That's the energy, which is a little fraction of that of the lithium-ion battery. And it is the best for electricity supply for your residential, building, industrial, for transportation. Transportation, yes, good for transportation, especially when we make the electrolyte solid. But for now, it is very good for, people are already using it for mobile and consumer electronics markets. So this is the chemistry. This is the chemistry. At the zinc anode, you have zinc will be oxidized, and then you get zinc oxide, 2 electrons generated. You see that, 2 electrons generated. The more the electrons, the more the electricity you generate. Then the A, there will be oxygen reduction, and then there will be oxygen evolution happening at the cathode side. And then the overall, zinc plus oxygen, zinc plus A gives you zinc oxide and generate electricity. The voltage is about 1.66 volts, standard versus standard hydrogen electrode. So, but the challenges now, there are so many challenges. We have the zinc. The zinc, I said, is a good subject. I talked about zinc foil or zinc metal, but the zinc metal can dissolve in your electrolyte. What do you do to prevent that? It can passivate, it can block the electrode surface. The zinc can undergo corrosion. So what are you going to do? These are the challenges that need a solution for. And then for the oxygen side, you require a very good electrocatalyst to be able to carry out ORR and OER. And also the carbon material we use also undergoes, the carbon materials undergo corrosion. So what do you do to stop that? And a lot of things happening there. Okay. So this is we have just written a review. We call it Effort at Enhancing Bifunctional Electrocatalysis and Related Events for Rechargeable Zinc Air Batteries. So if you want to know more about this, this is a very good review. We see that from 2010 to now, the research keeps increasing globally. This is what we have been in my group. We have, again, I'm going to summarize. Again, we use everything we use for the catalyst must be nano. This is a work by one of my PhD student, Leseho. She studied, she's making cobalt oxide. Very simple, you can make this cobalt oxide. And then she followed several techniques using microwave simply to increase the nanostructuring and the performance. And then at the end of the day, she made this material that is sitting on metal organic framework derived carbon. The paper has already been published, the synthesis has been published, but the work on zinc air has not been published. So this is the material, the initial one that was made. The second one is the morph. derived carbon. And then there is the cobalt. She had two types of cobalt here. One is she removed some cobalt oxide and left the other one. So we call it starved cobalt oxide and enriched cobalt oxide. So these are the same images. You can see the morphologies are quite different. She's tried them for oxygen reduction reaction because that's where you have to start. Is it good for ORR and OER? That she has done, and she proved that yes, they are quite good. Don't want to go into the technical aspects of this, but the work has not been published. So she's used it to also do OER and prove that one of them, the one that has a mixture of rich one and deprived one, both of them, if you mix them at some ratio, you get a good current response. And that is this one on green here. You look at even the conductivity. This is electrochemical impedance. We showed from impedance that the conductivity of the mixture is better than the other ones. And this is she tried the charge, discharge. Of course, you have your battery charge, you discharge, you charge. She did this several times. And I told you that we normally try from basic to applied and then to demonstrate. We have to get the prototype. They do that. She also tried to do that. She has to light electric bulb, LED bulb, to prove that actually this material works, can generate electricity. So the oxygen is coming from the other side, this side, and the catalyst is somewhere here, and then you see that. So because of time, I have only 10 minutes more, so I will have to rush. So she did this for 300 hours, about 12 days, and the thing was still running. That tells you that if you can scale it up, this is a good system. Okay, then we have another student of mine, Kelechi Lebechi. He's here, he's somewhere there. Kelechi, raise your hand. Where is Kelechi? Okay, Kelechi is there. He's a PhD student. She's also, instead of doing cobalt, she decided to do manganese. Manganese is cheap. So he tried that, and what he's looking at is what will be the effect of my support, the kind of carbon that I'm using. And we have done some modeling there. She will present this today or tomorrow, I think, but I will only show you one slide. So we have proved from DFT calculations, we have shown that the carbon nanofiber is much better than the carbon nanotube. That is what the DFT calculation is showing us here. And he has proved that also from his electrochemistry. So please attend to his lectures. Again, he has also shown that it can light an electric bulb. So you see, it was connected in series. He made two cells and then connected them in series to be able to power this bulb. Okay, supercapacitors. I talk about supercapacitors. This is another work done by my former PhD student who is now, I won't call him a PhD because he's still waiting for his PhD result. He has submitted his thesis. So he's a few days to becoming a doctor. So this was one of his doctoral research. His name is Tapelo Mofokeng. So he did some exciting work here. You can read this, and it's in carbon. So he was making nitrogen 3D defective 3D nitrogen doped carbon nanotube, carbon nanofiber network. And he used that. We published it in this journal. This journal is, I think impact factor is almost 9 now, or more than that. It's a very high impact factor journal. So this was the fancy material that he made without nitrogen and with nitrogen. And then to summarize, he did a whole lot of work. I can't present all of them. I wish he's here. So, but we showed that the nitrogen, the one that is done with nitrogen, has a way of enhancing the diffusion or Faradaic response compared to the other one. So he was looking at the diffusion control and the surface controlled reactions. So he did an excellent work here. Again, we see there that the nitrogen doped is the one that gave you the highest capacitance compared to the other ones. And then you can see again, he would light he lit the electric bulb again to prove that this is a good material. Okay, I talk about fuel cell. I'm not going to talk too much there, but I want to share what Adewale, this is another PhD student, former PhD student who is now a doctor. He's a postdoctoral fellow. He made nano palladium mixed with stannic oxide or tin oxide. And we proved that the interface between the two materials actually increases the electrochemistry and hydrogen oxidation reaction that you can use for fuel cell generation of electricity. And we published it in this paper, in this journal, and they gave us a cover page because of they think it's good. So we drew this thing for them. So we say here that with hydrogen, you can actually use it to power your transportation. You can use it, live in your house, electronics, and all those. Okay, so he will deliver this work online. I don't know, I think tomorrow also. So this is the summary of the work, but he will do that. I'm not gonna do that. Okay. Then this is another one who will also be delivering online. She also made palladium with Syria, nano Syria. Yesterday, Professor Maza was talking about nano Syria. So we didn't even know that Maza is working in that field. So we decided to make a palladium and nano Syria. And then we also did calculations to check two types of carbon. Is onion-like carbon or carbon black? Which of them would be better support? I must say that when Professor Ejikeme was in South Africa, he worked on onion-like carbon. So he's an expert in onion-like carbon. He worked there for 2 years. He was working on onion-like carbon. That's a very beautiful material you can use for electrocatalysis. Oh, Jorita, this is Jimodo. Some of you may know this lady. It is also part of our collaboration. I remember coming like this type of conference. We were here at the same time in 2016 or so. And I think she was sitting that place where our ICT guy is sitting, exactly that seat. So, and I was presenting. When I finished then, she was still an undergraduate. She did physics here. But in 2018, due to our discussion and everybody helping, wrote a good recommendation for her, and she finished her master's this year, with distinction. Summa cum laude, very high distinction she got. And now she started her PhD in this work. So this is part of her master's program. She will deliver this online also. I don't know when she will be doing that. I think tomorrow or the day after tomorrow. So you will listen to her. From what we have seen here, when you put this material on OLC support, it is much better than when you have it on carbon black support. Okay, so we have proved that again. She actually made a fuel cell. This is real fuel cell device. This is a 3D printed cell. And we can use that you can see the energy, you can see the power here. And when you compare that with palladium OLC alone, this one with Syria gives a more stable current response than the one with just carbon. The carbon will just crash after some hours. So we have not published this work, so nobody should copy it and publish. We haven't published it. So the last one will be sensors. The next one will be sensors. The last one, so like I said, I'm not going to talk too much about sensors. We are working in different areas of sensor. Like I told you when we started, Chief TJ Ehirim is working in the field of detection of drugs of abuse or substance abuse using nano-structured electrocatalysts. And this is part of his PhD. He's graduating this year anyway. He's finishing his PhD this year. I think I've seen his draft submission. So he worked on tramadol. You know what tramadol is in Nigeria? And then also on alcohol, just to catch drunk drivers. So this is a very big project. Actually, now we have a fund between my research group and the University of Antwerp. We got a 3-year funding to focus on this substance abuse using electrochemistry. So TJ will be talking on this. I don't know, again, I think tomorrow or day after tomorrow. So try to listen to him when he presents. So this is my research group. These are the people who are doing the whole work. I want to acknowledge them. I also want to acknowledge the sponsors. There are so many sponsors here for our work, too many to mention. They contribute in one way or the other. So what we do, we normally follow the money. If we don't have the money, we don't do the research. That's the way it is. Somebody has to fund it for us to do it. So I have a Department of Science and Innovation. We have this small-scale industry in South Africa that is helping us. They are funding 2 of our PhD students. One PhD student and 1 master's student from the Department of Trade and Trade, Industry and Competition. That's another department in South Africa. So they are funding us. Then we have the NIMISA, National Meteorology Institute of South Africa. Then I've told you about the Antwerp, I told you. Then we have this Coventry University actually gave me a fellowship this year for a whole year. So they are funding my research with University of Coventry Research Institute, Future Transport and Cities. Yeah, also we have the University College London. We're working with them on energy storage. These two institutions mainly on batteries. The University of Nottingham is the university we are working with. We are focusing on human papilloma virus detection. So we have a 2-year funding with them, with one Lola, a researcher in the university. And then the Qatar University is also helping us with some work in energy. Okay, so let me remind you again before I conclude. Please remember this ASIM START project. If you think you are qualified, you can ask Professor Ejikeme or Fabian Ezema. They will tell you more about this because they are involved. Unfortunately, you cannot study with them. You have to go out of Nigeria. That is the bottom line. I can come here and they can come to me. So that's the way. Then remember the special issues again. Remember this one also. Then thank you so much for your attention, for listening to me.
Thank you very much, boss, for telling us a few of the things you do at the University of Witwatersrand in South Africa. And if you listen to him very well, some of the last things he said were the most important things that he said. He said, you got the money, we'll do the research. If the money is not there, the research is not done. And that is what has propelled the University of Nigeria Nano Research Group from collaborating with a lot of people, especially in the industry and some universities. On the ESIMAT project that he mentioned, before the end of this conference, we will distribute something to the participants, and it's already on our website for people to apply, especially for those who are aspiring to do master's degree and PhD. You will see the areas that the project covers, and then if you are qualified, you apply. All those that will apply will be assessed internationally by a group, and then those that are selected will be part of the program. It's fully funded. And yes, and students earn for studying, not just that the fees are paid, but you also earn because you want to study. Let me say that this project, when we designed the proposal, And afterwards, the European Union added a little pepped it up and made it more like more favorable to women than men. Because any female that is involved in this program at MSc, at PhD level, for instance, earns almost twice what their male counterparts will earn to run a PhD program following this SMAD project. And that is also to encourage female scientists, upcoming female scientists to do their work. On that note, we'll say thank you again, Professor Ken Ozemena, on your presentation. A round of applause for him. And may I very quickly, a tea break will be served when Professor Rajan Jose will be making his presentation, so that we warm our stomachs while the presentation is on. May I introduce the next presenter? ICT, please, can you arrange to get Professor Jose online? Okay, I'm seeing him already. Professor Rajan Jose is currently the Dean of Research and a member of Senate, a senior professor at the University of Malaysia. He supervises the Nano Structured Renewable Energy Materials Laboratory in the University of Malaysia in Pahang. He investigated nano-structured perovskite ceramics for microwave and superconducting electronics during doctoral research at the Council for Scientific and Industrial Research in Trivandrum, India, and received PhD in 2002 for his work on superconducting and microwave electronics. He was employed as a scientist at the Indira Gandhi Center for Atomic Research in India, AIST in Japan, Toyota Technological Institute in Japan, National University of Singapore, before joining the University of Malaysia. He has published over 160 papers in Web of Science, Thomson Reuters Index journals, cited over 6,400 times with an H index of over 43. He holds over 21 patents nationally and internationally, and his current research interests include nanostructured materials and renewable energy. May I inform you that during the meeting we had in India, January last year, that Professor Rajan Jose hosted us. We enjoyed his company during that visit to India with the leader of the Nano Research Group of the University of Nigeria, Professor Fabian Ezama. So may we have Professor Rajan Jose talk to us on the work he is doing currently. Thank you very much. A round of applause for him.
Thank you, Professor Paul, for the nice introduction. Even if you read some of the things about 5 years back, I am no longer the Dean of Research. And currently, I have over 12,000 citations, and my H index is 60. So you probably have to update the biodata with you. But that's all right. I always like the companionship of almost entire team. A lot of people here, Prof. Ken, Prof. Fabian, and Dr. Ahmad, Dr. Elim from Indonesia, my close friend, Dr. Reddy, all are here. So nice to see you guys once again. Let me quickly glance through, quickly present my paper to you. In fact, this is not a paper. I am going to speak more about on general aspects. And of course, there are some examples from my research as well. So I would be speaking about material sustainability. This one, when you look at these slides, there are so many problems that we need to solve immediately. One of the first thing is the global, addressing the global materials demands that you would see in the left panel, saying that in 1970, we needed only 26.7 billion tons of material. And in 2015, it's become almost tripled. And it is predicted that by 2050, we need about 150 to 180 billion tons of material. So the population is growing and we need more materials. Where do we go to find them? The only thing that we receive outside the planet is sunlight, nothing else. So we probably have to make use of the sunlight to create materials for our future needs. And the next panel you see is a mine from where we used to get a lot of our primary materials. And this activity of mining has been there for centuries. Now we started seeing the adversities of large mining. For example, the recent floods in Germany and many parts of Europe, and so many floodings happening, extreme weather, and these whole things are related to our habits, and one of them is mining for our essential material. The third panel you would see is a child sitting on a heap of waste, and that is a cover page of the magazine Geographical, published by the Geographical Society of London, and that is a tipping point confronting the global waste crisis. Almost the waste is doubled almost every decade. And what are we going to do with it? The waste is doubled, and if we need to mine again to make things waste, it thinks the life in this planet is not going to be sustainable. The fourth one, many advanced countries started facing the production lines of minimal human hands. Means that you need to look for new jobs and new opportunities for your future generation. Where do we go for that? And on top of everything, you would see that nearly a new billion population in every 10 to 15 years of time. So we as academics, researchers, we have a lot of responsibility to address these issues in a systematic way and help the planet to sustain. Every one of us have a role to play there. And that's where we would like to speak more about. When we think about materials, they are the index of human progress. Or even the civilization, human civilization has been coined in terms of materials like Stone Age, Iron Age, Bronze Age, Steel Age, and more recently one Smart Materials Age and Nano Materials Age. There are two types. One is we mine and the other is we grow. And what if we mine? If we mine, what you see on the right-hand panel is a mine filled with water. And when we mine deeper and deeper, it makes the groundwater level to go down deeper and deeper. Means that water is no longer available in the surface. When it is no longer available in the surface, we cannot use them. We cannot very economically dig a hole like a petrol, like what we are doing for petrol mining and get our water. And that will create in a system, in a situation called the day zero. Means your municipality or your corporation is saying that we can no longer worry about your water, you worry it yourself. And it actually happened in South Africa, Cape Town, in mid-July 2017. They declared day zero. And recently I read that 21 cities will run out of groundwater by 2020, last year. So those are the cases with the mining. And very interestingly, last year there is a paper published in Nature saying that the global human-made mass exceeds all living biomass. And that is pictorially given here. You will see that the left hand, all the human-made mass, and all these mass, where did we got from? We mined them. And when we mine them, we destroy the arable lands. So the amount of biomass get decreased. In effect, the global man-made mass exceeds all the living mass in the planet. And 2020 is a crossover time where this equals. And now it is going to be more and more deeper, and we have to face more and more consequence of it. And this also means we, as academics, we really have that responsibility to play our parts. Now, the significant question is, where do we go for them? When we look into certain statistics like electronic waste, there is about 15 million tons of electronic waste produced every year. And that contains about 60 types of elements. Not even 20% of it is recycled. So if we make up strategies like, rather than we make, use, and discard, we consider or we develop the used product as the resource for the next industrial raw material. Means treating waste as an industrial raw material so that every atom present in a used product, we extract it efficiently and deliver back to the operation, or we make a circular path for the materials. When we can create anything circular, it will sustain and it will go circle and circle without losing it. So that's the best way we can sustain the material availability in this planet given a growing population. And that protocol is called the circular economy. We have recently written an editorial in the journal, Circular Material Economy, which I am the associate editor-in-chief, showing what should be the significance of the research on sustainability. I'm not going to the details of it. The details of that article is here. I would request you to go and read it. So let me share with you some of my laboratory experience. My laboratory has been developing materials, mostly metal and metal oxide, chalcogenides, carbide-based materials. So all of them, one thing common is metals. They're all derived from metals. And we have all kinds of morphologies like nanofibers, nano and microtubes, nanowires, multitubular nanofibers, nanoflowers, and a lot variety of nanostructures with excellent properties and usefulness. Two significant things I would like to highlight here is, it is in our laboratory, the world's first nano road solar module was produced with a 15% efficiency, which received gold medal for engineering excellence in INPEX in 2016. And in our laboratory, we developed a supercapacitor with power density up to 5,000 watt per hour that received a gold medal and invention of the year from British Invention Show 2015. So with all these kind of materials with outstanding properties, devices that can deliver functionalities or they are novel in some respect. I have spoken to a lot of industries, including industries in China, and they were really not ready to adopt these materials because there are two reasons for that. One is high materials cost. Most of these materials are made from metals using highly sophisticated processes, and eventually leading that the cost of the material is too high. And second is that most of these materials are derived from polymers. And if we have to develop 1 ton of this material, we probably have to burn another 5 or 6 tons of polymers, and that adds huge environmental load to the planet. So high material cost and high carbon load. These two things made this, even if all these papers are published in excellent journals, they are cited very high, but it hasn't eventually reached to the commercialization stage because of these two aspects. One is high material cost, and the second is a high carbon load. So for the young generations here, that's my advice. When you start doing your research, these are the things you need to consider. If I develop these materials, how expensive it is going to be, and how environmental friendly this material processing is. If you have the answer is no, then better don't waste your time. Invest your time which on more useful things. That's the point where we started looking into materials that can be renewably produced. So when we look into the renewable materials realm, it is trees, plants, and their products. In Malaysia, Malaysia is the largest producer of palm oil and second largest producer of exporter of palm oil. This largest agricultural sector make a lot of waste. And why can't we hear this waste? This waste is good lignocellulosic material. We can get carbon and cellulose from them. And the next issue is how do you functionalize them to deliver specific task? Not only palm kernel shell, we have looked into very many variety of agricultural waste. We did not use any edible part of this agricultural sector, only waste. And we started developing either carbon or cellulose, and then started developing energy devices using them. The first thing we did is to look at oil palm plantation and got the hard central core of this one. I think Nigeria also has a large oil palm plantation. A central core of that is the palm kernel shell. It is a good source of carbon and kernel oil. About 5 to 6% of the waste from oil palm is this palm kernel shell. We have developed carbon from it and studied its structure and properties very clearly. We find that there are actually the nanographitic domains with the domain size is too small, like 3 to 4 nanometer layer width and 1 to 2 nanometer layer height. Means it's in principle it is amorphous, but when we look into very clearly the X-ray diffraction pattern, we can see that they are really crystalline, but their degree of crystallinity is very small, and they are all graphite carbon. And when we start making the energy storage devices and comparing with the commercial carbon, you will see that the table here, commercial carbon is much better than the palm kernel shell carbon we have developed. And we find that it is because of the resistance. So how to get over this resistance? We did two approaches. One is heat, find out what is the source of this resistance. We found that the excess oxygen present in this carbon is actually the source of resistance. And remove them out by means of heat, either heat it or by using other methods. The first experiment we did is heating it out. And when we heat out most of this oxygen, we got a carbon that is much superior than the commercial carbon. And when we did this work, and when we speak to industry, and they are interested, and a Japanese company, Noritake, is currently investing on this project, and they are going to commercialize this product. And when we compare the properties in these two materials domain, like inorganic material and organic material derived from agricultural waste, this is what comparing the top blue, green, and yellow is the energy density of metal oxide based electrodes, and the black one is the energy storage, specific energy and specific power of carbon. You'll see that the energy storage capability of inorganic material is way ahead than the materials in the organic from the organic domain. Demonstrated in many situations. The details are here in these papers. Then we find that how do we mix them, make the best use of materials from both the domains? Like most part of it is carbon and lowest part from metal oxides or metal based compounds. There then we have developed a system where the carbon, the surface of carbon is given a thin film is developed on the surface of carbon. Like the carbon surface is painted with a metal oxide, and the amount of metal oxide used for painting this carbon is only 10% of the carbon itself. Means that we have 90% carbon and 10% metal oxide painting or painted on this carbon surface. And when we look into the energy storage capabilities, when we have the energy density of pure carbon about 8 watt-hour per kilogram, when we paint this carbon using metal oxide, we have the energy density 3 times higher without any appreciable loss in the charge storage, means power capability. So that works. And this one we have extended in place of metal oxide. We have developed a metal film. In this particular case, we have developed a cobalt film on it and shown that the same thing. We can, using 10% metal covering on porous carbon, can increase the energy storage capability of carbon electrode almost 3 times higher without any appreciable loss in the power capability. There are a lot of these ways manipulating this strategy, means the minimum amount of metal oxide. In all these cases, we have optimized it to be 10 weight percentage of that composite, 10 weight percentage carbon metal oxide, and 90 weight percentage carbon. Found that this strategy works well. We can functionalize carbon using metal oxides or metals with minimum quantity and uplift the performance of carbon to a very superior level. And currently what we have is a battery supercapacitor dual hybrid device with energy density something like 160, about 60% of that of lithium ion battery. This a lithium ion capacitor Prof. Ken was speaking about. This lithium ion capacitor is giving us about 3.5 volts. Yeah, in principle, it can have up to 4 volt, but there is some loss. We are still adjusting that, reducing that loss so that we can have a 4 volt battery, 4 volt lithium ion capacitor with about 60% storage capability of the lithium ion battery, but about 10 times more power capability than lithium ion battery. This paper just today accepted in an ACS journal. Not only on materials, we developed green processing also. The latest work in this area is using sunlight to purify or remove oxygen content from carbon. So here we have used either laser or even a lens, using which a Fresnel lens that can have large area, using which we can concentrate large amount of energy on a given surface and remove most part of oxygen from this surface. That paper just appeared in Sustainable Energy and Fuel. When we speak about renewable materials, we cannot ignore this metal organic framework, where we still use very minimum amount of metals or its compound to functionalize a large organic framework, and we create a material with more exposed metallic centers so that the functionalities will remain. In this particular case, we have developed a metal organic framework with a triple cation, and that triple cation metal organic framework is shown to be a good energy storage material, both in the supercapacity one and lithium ion battery one. Lithium ion battery work is handled by Prof. Arotiba, in the special edition published last year on in electroanalysis. And in another event, we have shown that this triple cation metal organic framework is very good in sensing nilutamide. Nilutamide is an anti-cancer drug used to treat for prostate cancer. So when it is diagnosed and how much of it is being expelled, if you want to sense them, one of the best sensors that can used is a triple cation metal organic framework developed in our laboratory. So this work is done by my doctoral research Noor. And some of you of my colleagues are extensively working on getting useful components from renewable materials, from algae. What you see in the left side is Dr. Fatmawati Adam. She has developed a completely hard capsule that we used for wrapping our medicine capsule from a completely bio source like algae is a seaweed. And the right hand side, you would see Dr. Nano he has developed an algae that consume carbon dioxide to a large extent and become fattier. And this algae when it become fattier, we can extract the fats, the lipids, and can develop healthcare products, food, environmental protection, equipments, biofuel, and so on. So a lot of my colleagues and most part of our university is presently working on materials renewability so that we can supply materials sustainably to the next generation industry. One another work that we have done towards it is extracting cellulose from from a palm oil waste. In this particular case, it is empty fruit bunch, and we have extracted cellulose from this empty fruit bunch using a patented technology process. And we have added some curcumin in that cellulose, developed them into a fiber clothes that you're using a large scale electrospinning one. So no your losses here. This is the pure cellulosic fiber, and this is the cellulosic fiber with a small amount of curcumin, 1% amount of curcumin. And when this curcumin loaded cellulosic fiber is used as a wound dressing medium, this done by my master student Noorul Nadra. She has shown that that kind of wound dressing medium cures wounds very faster, and the cell viability in that one in her scaffold is much better. So there is plenty of ways we can functionalize material. And in this particular work where we have designed a material using completely organic source to absorb light and emit heat. And that is used in a process like photoacoustic imaging. So my doctoral student, Dr. Amina, currently she is a postdoc there. She has designed molecules with that capability using density functional theory, how a molecule can be engineered in such a way that it absorbs light and emit heat so that it can be used as a photoacoustic imaging medium or non-linear optical medium. So this paper, the details are available in this paper. One another work that we have, my two other students have done is developing renewable materials as a filter membrane. In this particular case, it's again the cellulosic membrane, and they have developed a water filter which can even filter seawater into pure water, but currently the filtering efficiency is too small. It is not a pressure drop membrane. You need to apply good pressure to get pure water from it. We need a lot of optimization there. Means the proof of concept device is already there. We need to further engineer for further development. Towards the end, I want to introduce you for a few journals. I am either editor-in-chief or co-editor or associate editor-in-chief. One is the Current Science and Technology, published by UMP Publishers. I request you that you consider sending some of your papers in this conference to this journal, Current Science and Technology. And the another journal I'm co-editing is Associate Editor-in-Chief is the Material Circular Economy, where we address the material sustainability issue. How can we develop materials in a more sustainable way? We have published 2 issues by this publisher is Springer Nature. We have published 2 issues with some highly accepted papers like producing sanitary parts from knitwear waste in Bangladesh, and challenges in the post, how do we address the waste challenge in the post-COVID era. So these are the type of papers that we are publishing in this journal. I request you to submit some of your articles towards material sustainability to this journal. And finally, this my team Nanostructure Renewable Energy Materials Laboratory. The lower one, the bottom panel is the currently existing students, and all the above in the first 3 rows are graduated and they are working somewhere. And thank to my funders, I did not list my funders here. There are a lot from Ministry of Education, University of Malaysia, Pahang, Noritake, and very many universities around the globe. So thanks to all of them, and thank you very much for your attention. Thank you.
Thank you very sincerely for this presentation. And as usual, you remember that the last time you were here for this conference, that the members of the Nano Research Group and some other interested persons were connected with you, those who are interested in your area of research. And be rest assured that by the time the curtain is drawn on this conference for this year, that some persons will also get in touch with you.
That would be amazing. I am glad to be part of this big team.
Thank you very much, and we hope to continue to work with you. Thank you very much for the presentation once more.
Thank you. Thanks again.
By the time the next speaker finishes, we will put questions across to both yourself, Professor Omotayo, Arotiba, and then the next speaker. I want to introduce Professor Justice Ndukife, who is with the Department of Electrical Engineering and Computer Science at the Vanderbilt University. He's a faculty member of the Vanderbilt Institute of Nanoscale Science and Engineering, and has been partnering with the Nano Research Group of the University of Nigeria. May I also inform you that his research works have been published in the top peer-reviewed journals that includes the Nano, Nature Nanotechnology Science, and ACS Nano. He got his first degree from the University of Lagos, Nigeria, with first-class honors in the Department of Electrical and Computer Engineering. His research at the interface between fields of nanophotonics and microfluidics, as well as novel bio-inspired soft actuators and robots. Professor Ndukife's research interests include nano-optical trapping with plasmonic and resonant dielectric metal surfaces, programmable self-assembly of nanostructures for energy harvesting and on-chip light sources, discovery of novel emergent behavior in nanoscale motors, and nano biosensors for water quality monitoring and point of care diagnostics. So may we have Professor Justus C. Ndukife provide some of the works he's doing. A round of applause for him, please.
Okay, good afternoon, everyone. Yeah, can you all hear me from the back? Okay, terrific. Well, it's a pleasure to be back here again. I was here back in 2018. So it's great to come here to talk about our research. So I'd like to thank Professor Fabian Ezema for a kind invitation, and also for all the organizers for putting together this amazing conference. So today I'd like to talk to you about the work we've been doing. And the title of my presentation is There's Plenty of Room for Optical Nanotools in Biology and Medicine. And I actually borrowed this title from a famous lecture that was given by Richard Feynman, who used to be a professor at Caltech in USA, and actually won Nobel Prize a couple years back for many of his works. So he was a very, very prolific teacher and a very famous physicist. And he gave a very famous lecture when he talked about there's plenty of room at the bottom. And that was actually what gave rise to the field of nano, which is now touching our lives in several ways. So I'd like to talk about opportunities for optical nanotools in the field of biology and medicine, and some of the exciting developments we've made in this area. So I'm from Vanderbilt University, which is located in Nashville, actually at the heart of the city of Nashville, which is also the music city. For those of you who like country music, so you may know about Dolly Parton. She's actually from Nashville. And this is within the southern part of the USA. And my lab does a lot of work with light, basically light at the nanoscale, which is referred to as nanophotonics. So we design nanostructures which are made up of metals or dielectrics with high index, which can enable us to confine and manipulate light at very, very small volumes. And with this, we can enhance light-matter interaction. We can use this to develop new kinds of optical nanotools. And I'll discuss in a little bit what I mean by those. And I'm also very interested in the field of bionanophotonics, where we are now working with some very small nanoparticles, which are released by our cells, known as extracellular vesicles. So this used to be thought of as a means for cells to expel waste, but now researchers have found out that these actually contain important biological information molecules, and cells can use this for long distance communication. So very interested in harnessing these extracellular vesicles for non-invasive liquid biopsy. So you don't have to cut up someone open to detect cancer, for instance, but can actually detect cancer at an early stage. So I'll discuss some of our activities in this area in a little bit. And also another area we work on is in the area of on cheap and non-classical light sources, such as single photon source or entangled photon sources. So as I begin the presentation, I'd like to play you this quick video, so which will summarize most of what I'm going to be talking about today. And this is a new approach that we've introduced, which enables us to use light to manipulate particles, but from a distance. So here, what we've done is we have a gold film, and then we poked tiny holes on the surface of the goals, nano holes. So thousands of those. I will show that we can illuminate a portion of these nano holes with light from a laser beam. And then far away from this laser spot, we can manipulate a single nanoparticle, like a single protein molecule, which is actually below 10 nanometer in size. And that's something that has not been done before. So I'll discuss why this is important and what we did to accomplish this. So let me get this out of the way. By the way, is anybody familiar with a dish called a sushi? Okay, awesome. Yeah, Professor Zomara here knows that. Okay, very good. So this is a special dish, and I think it came from Japan. If you want to eat it, you can use a fork, or you can actually use this kind of chopstick, which Asian folks, like to use. However, the constituent of this sushi is actually made of rice. But if you want to pick up something like a small grain of rice, you probably use some kind of tweezer to do that. What if this grain of rice becomes way much smaller, like the size scale of cells in our body? How can you manipulate things that are that small, like a single cell? Obviously, you cannot use a regular tweezer. So it turns out that you can actually use light to move them. You can use light to generate forces on these objects. And this was what the Nobel Prize in Physics for the year 2018 was, recognized. However, if these particles are even much smaller than cells, like on the size scale of small protein molecules, so let's imagine that you take one strand of the human hair and you slice that into about 10,000 places. So you can imagine something that tiny, such a small nanoparticle. How can you move and manipulate things that are that small so you can analyze them? So obviously for that, we need a nano tweezers. And I'll be discussing how we can develop those kind of nano tweezers and some of our activities in this area. This is very important because with this kind of capabilities, we'll become able to study small molecules like proteins, DNA, or virions, or exosomes, which are very important for understanding the pathogenesis of diverse diseases like cancer and Alzheimer's. So as I mentioned earlier, so the 2018 Nobel Prize in Physics actually recognized tools that are made of light. In particular, one half of the prize was awarded to Otto Ashken. He was at the age of 96, becoming the oldest person to win the Nobel Prize. And that was for developing what is called an optical tweezer. So basically the work Ashken did back in 1986 was introduce a way for you to use light to actually manipulate and move very small particles. So what he did is as follows. So he took a laser beam and then he focused the laser beam using an objective lens. So at that focal spot, if you bring it close to a particle, that particle is going to feel a force just from the light alone, which is quite intriguing. And you can use that light to actually move the particle in place in a very non-invasive manner. So you don't need to touch the object with any physical object, just simply by using light. And the force which enables this trapping is the so-called optical gradient force, which in the quasi-static limit, when the particle size is much smaller than the wavelength of light, is proportional to the particle size to the third power or to the volume of the particle. So that means that if I have, say, a particle size that is 1 micron, which is 1,000 nanometer, you have a certain force. If you reduce the size by just an order of magnitude to, say, 100 nanometer, that force is going to reduce by 3 orders of magnitude, by 1,000 times. So that's a big deal because of this volumetric scaling. So it becomes very difficult to trap very small objects, with optical tweezers. But most particles like cells, you can trap with optical tweezers, which is why this was given Nobel Prize. But to address much smaller particles, we need to develop new ways to do that. Another important thing is that the optical trap is also proportional to the gradient of the light intensity, which is why we have to focus the light, very, very tightly. If you have the best objective lens, you can get in the market, there's a limit to which you can focus the light, and that is called a diffraction limit, which says you cannot focus light about half of the wavelength of light in a given medium. So let's assume you have, say, something like red light. So the wavelength is about 700 nanometers. So you can only go down to about, say, 350 nanometers to focus light. That might appear to be small, but of course, in the exciting world of nano, we're interested in going to, say, on the sub 10 nanometer size scales. So 350 nanometer becomes really large compared to, say, sub 10 nanometer. So because of this so-called diffraction limit, it becomes very, very difficult for you to harness this Nobel Prize winning optical tweezers to address particles that are in the sub 10 nanometer size regime. Hence the need for nano tweezers. So as I mentioned, with optical tweezers, we can really address things like red blood cells in our body or bacteria. So those can work with those. But when particle sizes become really, really small, we cannot work with optical tweezers. And very, very importantly, there are a wide range of particles that are of great interest. So example are things like DNA molecules or viruses or protein molecules, for which case we like to use nano tweezers to address those. And also very crucially, there are some new particles that have been discovered within the past decade, and that are known as extracellular vesicles. It's a very, very active area of research now in biology. So people typically thought initially that this was a way for cells to expel waste from themselves, but then they found out that these extracellular vesicles actually contain important biological information molecules like DNA and protein that cells can release into the extracellular milieu, and they can diffuse and get internalized by another cell. So it provides a way for cells to package information and communicate with neighboring or distant cells. So these particles are really, really small. They're on the size scale of, say, about 30 to 100 nanometers. And even my colleague at Vanderbilt told me that they recently discovered another one that is really, really small, even down to about 20 nanometers. So obviously we need a nano tweezers to address this. So what is the challenge? So the key issue is that you cannot squeeze light to the nanoscale using conventional free space optics. And the reason is because light has big wavelength. So the wavelength of light is on the order of hundreds of nanometers, which is kind of large if you're talking about nano. So red light has like wavelength of 700 nanometers. However, interestingly, electrons have very small de Broglie wavelength. So the wavelength of an electron is on the Armstrong scale, which is like a fraction of a nanometer. So what about if we can find a way to combine light with electrons so we can create a new kind of wave, which is called a plasmon. So this plasmon wave allows us to squeeze light to the nanoscale. So we can use that to generate very, very tight trapping potential waves to address particles that are very, very small. So this is one of the actively studied areas in the field of nanophotonics. And it's really the idea of generating this plasmon wave. So how can you do that? So one of the simplest ways to do it is to simply take a gold nanoparticle, which you can get from most places. So if you take a gold nanoparticle, you illuminate with light. That gold nanoparticle has plenty of electrons, which are actually free to move. So the electrons are loosely bound to the inner core. So the electric field from the light can displace the outer shell electrons, and then the electrons try to get pulled back again because the nucleus is positively charged. And again, the electric field displaces the electrons again from their equilibrium position. So you basically set up an oscillation of these electronic charges. So when the frequency of the oscillation of the electrons matches with the frequency of the incident light, we have resonance, which is called localized plasmon resonance. And this provides a way for you to have light that can be localized at a nanoscale. And not only that, you can also amplify the light intensity by several times. So imagine that you have this bulb which has a certain intensity. If I use the same light intensity to excite this plasmon wave on the surface of my metal nanoparticle, I can amplify this intensity by a factor of about 1,000 times. So you can basically make this bulb to be 1,000 times brighter at the nanoscale. So with this, you can use that to enhance light matter interaction. You can also reduce your energy requirement, which is extremely useful. So very crucially, with this plasmonic traps, because of the fact that we can confine energy to very, very small tiny cavities, we can generate very tight trapping potential wells to address particles that are very small. So if you look at a potential well for an optical trap, you see that it's diffraction limited. It's limited to λ/2, whereas the one for a plasmonic trap is much more confined. So a nanoscale particle can be more stably trapped in this kind of tweezer. So of course, several groups around the world, jumped on this idea and explored several designs. So you can use like a gold nanopillars, you can use an aperture like a hole in a metal frame, or you can use like a coaxial antenna at a nanoscale, the same kind of antenna that carries light for TV signals. Or you can also make something that looks like a bow tie to trap things that are very, very small. And there are several groups around the world that are working in the area from several universities. However, there are actually two main issues from the use of these plasmons. So one of them is the following. You remember I was telling you that with the plasmon wave, to excite them, we have to have electrons that are oscillating. So when electrons are oscillating, they're going to scatter with themselves. They're also going to scatter with the lattice of your atoms, and that is going to result in energy dissipation. So anytime you illuminate something like gold nanoparticle with light, you always have heat dissipation. So some people leverage this thing for photothermal cancer treatment, to destroy tumor cells. However, if you're interested in trapping and studying very small biological molecules, you wouldn't want to, heat them up, because DNA, for example, can have a surface melting, or proteins can also get denatured, and that's going to change their molecular function. So you don't want to do that. So it's important to, mitigate any excessive heating effects, and there are ways to do that. And the other important issue is that these metal nanoparticles for generating this plasma wave, we usually fabricate them on a substrate using electron beam lithography. So it's actually on a substrate, and then you illuminate that with light. So the particle that you're going to trap, or the biomolecule, must diffuse from wherever they are, hundreds of microns away, and come close enough to interact with one of these enhanced electromagnetic field. And that can be a really slow process. You may have to wait for several tens of minutes, even an hour, for that trapping to occur. So we wanted to speed up that process, and we actually solved that problem by introducing a new design paradigm that we refer to hybrid electrothermoplasmonic tweezer. And the idea in this case is we simply illuminate this metal nanoparticle with light, and then we apply an AC bias. When we do that, we can induce a hydrodynamic flow in the fluid, which is known as the electrothermal effect. So this fluidic motion in the fluid can transport the particles and make them to be trapped within seconds. So rather than waiting for, say, several tens of minutes or an hour, you can do this within a seconds. So this work gave rise to what is now called electrothermoplasmonics in the literature, and several groups from all over the world are adapting this design to improve the performance of a lab-on-a-chip optical biosensors for detecting biological molecules. So the other issue that I mentioned about heat dissipation, you can actually address this problem by simply eliminating the heat by placing your antenna on a high thermal conductivity substrate. And that is what was done by this group a couple years back. However, the kind of nanotweezer that we would like to have should have several desirable features. So one of them is that we should have the capability to trap particles that are both in the sub-100 nanometer size regime and those in the sub-10 nanometer size regime with high trapping stability. We should also be able to rapidly transport nanoscale objects that want to trap, let's say the biomolecules to the trapping site within seconds. And we should have a mechanism to achieve dynamic control over the objects that we're trapping. And it also be nice to ensure that for biological objects that they do not experience any detrimental heating effect. And we should also be able to sort particles, let's say based on their size or their charge or properties. So can we actually realize such a nanotweezer that has all these desirable features? The answer is of course yes. So we recently introduced a new design which appeared in Nature Nanotechnology just last year. And this is something we call optothermal electrohydrodynamic tweezer, which enables us to trap particles that are in the sub-10 nanometer size regime. And we can trap them far away from the laser spot where they experience just ambient temperature. And when you move your laser spot from one position to another, you can also make the molecule to move alongside. But the molecules do not have to reside at the position of your laser spot. Okay, so it's basically like an action at a distance. It's like you're moving something here, your laser here, and your object is far away. It's actually feeling the force from a distance. So I'll show you how we're actually able to make this to work. So basically the way the device works is as follows. So we take a glass substrate and we deposit a thin film of gold, about 100 nanometer thickness. And then what we do is that we poke some tiny holes, about 200 nanometer in diameter, thousands of these holes on the surface of the gold. So when you poke holes on gold film and you illuminate the gold film with light, those holes are basically serving as antennas for light. They're basically capturing the light and funneling the light on the surface and the vicinity of the holes. And they're also amplifying the light intensity because we're exciting these so-called plasmonic waves. So when we do that, because of the fact that this is a metal film, so we're going to have some heat dissipation. So this heating is going to induce a change in the temperature-dependent properties of your fluidic medium. So namely the permittivity of your fluid and also the electrical conductivity of your fluid. So if I have that condition whereby I have a change in my conductivity, a gradient in my conductivity, and also a gradient in the permittivity of the fluid, if you apply an AC bias based on charge conservation principle in electrostatics and Gauss law, we should have the generation of a body force inside the fluid, which is known as this electrothermal body force. So this volumetric body force is going to act on the fluid and basically induce a vortex. So it's basically like a tornado, but on the micron scale. So you can induce that inside your microfluidic device. And this microscale tornado will capture nanoscale particles and transport them close to where your laser spot is. But interestingly, yet another thing that happens is as follows. So if you're hearing talks about capacitors, so the very simplest configuration of a capacitor is basically to have two electrodes, like a gold substrate and a top layer. You apply an AC field, right? So what you should know is that electric field should be normal to the surface. There shouldn't be any tangential component. Everything should be normal to the surface. That's what you should expect. However, if we poke these holes, because of the presence of these holes that we have on the gold film surface, these nano holes are going to distort the electric field lines. And then we're going to have both a normal component and also a tangential component. Okay. So the tangential component can then act on the charges induced in the electrical double layer, which is generated at the interface between the gold nanohole array surface and also adjoining fluid medium. And that is going to induce something called AC electrosmotic flow. And that AC electrosmotic flow is actually radially outward. Now the original flow we induce, which is the AC electrothermal flow, is radially inward. So at some point, both flows are going to balance, and that is somewhere away from the edge of the nanohole. And when they balance, the fluid velocity is going to go to zero. So we can create what is called a stagnation zone. And at this stagnation zone, we can trap and localize a single particle. And interestingly, this stagnation zone occurs several tens of microns away from your high intensity laser focus. So by so doing, your particle never needs to get to where the laser is, but it can actually be trapped far away from that. And as you move the laser beam from one point to another, we can dynamically manipulate the particle. So that's basically the idea. So of course, there are quite a lot of interesting multiphysics phenomenon going on. So this was what I mentioned earlier about how you can induce this tangential component of your AC electric field when we have this nanohole array, which is needed to induce this AC electrosmotic flow. So for us to actually model this problem, because we like to see and predict this flow, we have to couple all the different physical phenomena that are actually taking place, starting from when we illuminate the gold nanohole array with light. So we can model the response of that by solving the electromagnetic wave equation, which is derived from Maxwell's equations. I'm sure those of you in electrical engineering or physics that's taking a course in electromagnetism, will know about the wave equation. So this is a famous wave equation. So we solve this numerically so we can find the electric field distribution in the system. Once we know the electric field distribution, then we can compute the heat source density, which gives us the heat dissipated inside the field by using this expression. So it's 1/2 the real part of the current density with the dot product of the complex conjugate of the electric field. And then for us to find the temperature rise in the system, we solve this heat equation. So now we move from electromagnetism to heat. And after solving the heat equation, we can find the temperature field distribution. Of course, of interest is to find the velocity distribution in the fluid. And to do that, we solve the Navier-Stokes equation, which is given by this expression here. So the forcing term F is comprised of two parts. So one is this convection force, but that's not what we're interested in, but that is pretty weak. But it's really due to this electrothermal body force, which is given by this expression. So you see the temperature gradient comes into play, grad T. And this is the electric field from the AC field. So all these partial differential equations can be solved readily using a software called a COMSOL multiphysics, which enables us to model these problems. And you can actually predict how your device is going to perform before you go to fabricate them. And I should mention, my group is now launching an initiative whereby we would like to introduce this idea of how to model this kind of problems in COMSOL to students, in Nigeria, starting from here at UNN. And we're also going to be uploading some, lecture series on our website that students can follow along and actually learn how to do this kind of modeling. So actually very, very useful in the field of, nanotechnology in general. And for the AC electroosmotic flow, we actually take that into account by using a slave velocity, a slave boundary condition, given by this slave velocity, which is given by the Smoluchowski slave velocity, and that's given by this expression. E sub t here is simply the tangential component of the electric field. So we're not taking the normal component, just the tangential component. So when we solve that, so we can generate a plot that looks like this. So you can see here, I think it's a little bit difficult to see on the screen, but the arrows are pointing in opposite directions. So that's where the stagnation zone is generated. And when you move the laser spot, you can transfer that and make the particle to be transported accordingly. So here's a video showing the transport of a single particle. So you see your laser beam is illuminating this region of the nanohole. So it is a region with the gold nanoholes. And here is just the metal film area. So when we illuminate and apply the AC electric field, a single protein is transported and it gets trapped far away from the laser spots. So it never gets trapped close to the laser spot. So you avoid any heating effect. And as you mentioned, this size of particle you cannot trap using the optical tweezers, which was awarded Nobel Prize in Physics 3 years ago. You cannot do that with conventional optical tweezers, but you can do this with this kind of device. So one can also trap and dynamically manipulate a single protein from one position to another. And additionally, we can also sort two particles. So this is of interest because in extracellular vesicles, they're actually heterogeneous. So you have different sizes. So of interest is to be able to sort them and be able to analyze them based on their sizes, which still remains an open question in the field now. So by simply tuning the frequency of our AC field, we can actually sort, initially trap both 20 and 100 nanometer size particles. We raise the frequency, we can release the 100 and keep the 20. So we can do this. So what can this enable us to do? So these are some of the things we're beginning to look at now. So one of them is being able to analyze extracellular vesicles which have been released by single cells. So we can determine the molecular, the information contained inside these extracellular vesicles, like what kind of proteins are contained as cargos in them, or DNA, both non-coding and the coding DNA. And this is very, very important. It's still not yet known whether all cells secrete EVs of all sizes, and also what is the role that size plays in dictating the cargo content that EVs contain. So that's a very key area we want to be able to help to answer by using this new capability. And also very crucially, for liquid biopsy, so if for cancer patients, there's a very big interest to be able to detect cancer at an early stage, because this can actually improve survival rate by as much as 90% and also enhance outcome, patient outcome. So for some kind of tumors, like brain tumor, like glioblastoma, one cannot keep on doing resection in the brain. It's a very painful process. And so it would be very useful to have a mechanism to, just by taking bodily fluids, like blood samples, or plasma, then one can actually collect these EVs, analyze these EVs from them, and tell how patients are responding to treatment, as well as also to be able to detect this at very, very early stage. Unfortunately, something like glioblastoma still has very high, very, very poor prognosis. Survival rate is still about 15 months. Because it's the first stage of brain tumor. So it's very, very important to find this out way ahead of time. So that's an area that we are beginning to explore now. And in the area of single molecular analysis, like four-star resonance energy transfer, this technology can also be combined with different kind of spectroscopies. So one can analyze proteins that are associated with neurodegenerative conditions like Alzheimer's. And this will also begin to explore. And very recently, we're also working on advancing the design, like using a concentric nanohole, where we can even create multiple trap sites. And with this, recently, we're able to show that we can sort small and large EVs, one from the other, in a spatially dependent manner, by simply tuning the frequency using this kind of configuration. So to kind of give you a brief summary of some of the milestone accomplishments in the field of optical tweezers over the years. So back in 1986 was when the first single beam optical tweezer was invented by Arthur Ashken. And for this, he was awarded Nobel Prize in Physics in 2018. But before then, optical tweezers were also used to trap cold atoms for quantum simulators. And this was awarded, recognized with the Nobel Prize in Physics in 1997, which was awarded to Stephen Chu, who was actually the former Secretary of the Department of Energy under the Obama administration. Then also awarded to Kohen Tanoji, also a very phenomenal scientist. We actually, and also William Phillips. Yeah. And in 1998, the idea of implementing a tweezer on the tip of an optical fiber was introduced by Lucas Novotny. He used to be at Rochester and now at ETH in Zurich. And then in 2009, doing these chip scale tweezers using plasmonics. So that came about by works from several groups, including the Roman Quidant, Greek Oracle, Crozier. And then in 2012, plasmonic trapping of single protein was demonstrated. And in 2016, I was responsible for introducing these electrothermal plasmonic tweezers for my team. And for that, we were recognized with the Chorofas Foundation Prize in Physics. And also very recently, we were awarded the Rising Star of Light Award, a global award. And then very recently, just last year, we introduced this optothermal electrohydrodynamic tweezers. And these works have been published in Nature, Technology, and also Science, and highlighted in Nature. So I do encourage you to take a read. So to summarize OTT, this optothermoelectrohydrodynamic tweezers, provides a lot of interesting opportunities for bio applications. First of all, you can achieve transport and trapping within seconds. You can also trap sub 10 nanometer size biological objects, which is something that is not possible using conventional optical tweezers. You cannot do that. And you can also trap particles far away from the laser focus, so you prevent any photoinduced damage. One can also achieve dynamic manipulation of trap biological specimens, and we can also achieve sorting of biological objects based on size. So most of the work has been done by some terrific students in my lab, including Chuchuan Hong, Rene Ju, Sen Yang, and Yujin Jiang. And this work was funded by the US National Science Foundation under the Electronic Photonic and Magnetic Device Program. And we've been working very closely with the Vanderbilt Institute of Nanoscale Science and Engineering, as well as the Oak Ridge National Laboratory, which is also in Tennessee, very close to us. We have collaborators there as well. So I will stop here, and thank you.
Yeah, thank you very much, Professor Justice, for this presentation on on how far you have gone with optical tweezers. It's shown that it's clear that nanotechnology, nanoscience and nanotechnology doesn't know boundaries. Now, an electrical engineer by major training has got a lot to tell us on how nano systems can be tweezed to do a lot of work. So we want to say thank you very much once more for the presentation. Now, the next person will make a presentation before we take questions. And the next presenter is Professor Emeka Oguzie. Professor Emeka Oguzie is the team center leader for African Center of Excellence in Future Energies and Electrochemical Systems, the SCE Fuels, and has been appointed the Deputy Vice Chancellor, Research, Development and Innovation of the Federal University of Technology, Owerri. He has garnered a lot of experience working in the industry, having been engaged as research advisor, health, safety, and environment of Shell Petroleum Development Company, Port Harcourt in Nigeria. He is the founder of the Multidisciplinary Electrochemical Energy Interfaces and Nanotechnology Research Consortium that actually was responsible for the attraction of the SCE fuels to Federal University of Technology, Owerri. And then Professor Oguzie has a lot of administrative experience, which he is bringing to bear in managing the various centers that he has been appointed to manage by the Federal University of Technology, Owerri Futo. So here we present to you Professor Emeka Oguzie, a corrosion expert, to deliver his lecture. May we please welcome him with a round of applause. Professor Oguzie, you can start now. You have about 30 minutes to make your presentation. Thank you.
Thank you very much, Professor Ejikeme, good friend and colleague. So I would like to thank the organizers of this program, thank our partner and good friend, Professor Fabian Ezema, for inviting me to give this talk at this fourth African Nano Conference. Interestingly, Professor Ezema is very much part of our Center Ace Fuels. He's one of our instructors and research collaborators. So first, I'll just give a brief about our university, the Federal University of Technology, Owerri, is Futo. It's the first university of technology established in Nigeria in 1980. So we're not very old. We have now 9 schools as faculties, I think about 53 departments, a number of full-time professors and other ranks of lecturers. We have a huge undergraduate student population. And Futo sits on a very large expanse of land, all green and all lush, about 5,000 hectares. And over time in Nigeria, we've become one of the major suppliers of manpower to industry in engineering and science and technology. And like Prof mentioned, we have in 2019 received funding from the World Bank to create an African Center of Excellence in future energies and electrochemical systems. It's called ACE Fuels. And the center was established primarily in a proposal we made it clear that Africa needed to find homegrown solutions to the energy crisis in Africa, and which is even more pronounced now with the current move towards sustainable energy sources. So we requested for the grants from the World Bank, and we got the funding to establish a Center for Future Energies and Electrochemical Systems. And the center's activities is, as depicted in the image on your right. First is education and training. We have research and development. We offer commercial lab services. We do information dissemination in our core areas, and we'll do tech transfer. And the ACE, we are part of a larger ACE impact project of the World Bank. It's an Africa-wide initiative. And the focus of that center, of that project, is to deliver excellent education using excellent faculty based on excellent administration in an excellent environment. This is what the World Bank is supporting African nations to achieve with almost $300 million continent-wise or region-wise. So for us in ACE Fuels, we have an MSc and PhD in future energies, in nanotechnology, in electrochemical technology, and in corrosion technology. I think we might be one of the few, if not the only centers or institutions offering this kind of degrees in Nigeria and maybe sub-Saharan Africa. And currently we are accepting applications for the second cohort of students. Our focus is on the West African region and Africa, and we have a number of scholarships available to our students. Both full and partial scholarships are available. And the website is there, so you can apply online at no cost. And those of you at the conference venue can talk to professors to know about ACE Fuels at the center. In terms of research, our research areas are well defined, quite ambitious. We have areas in solar PV, solar thermal, electrochemical storage, biomass transformation. We have a good program or good research experience on corrosion and works on CO2 capture and utilization, doing some work on environmental electrochemistries, nanoscale technologies, and catalytic phenomena, just to hold the broad spectrum. So I'll just take you around some work we've done in the area of corrosion, right? Sorry. Earlier work was on the corrosion using different kinds of organic materials. We've done some good work in that area, quite some good publications. We also we've done a lot of work, maybe
ICT, please. Okay, it's been restored. It's just that we've lost his voice. I guess ICT, is this something we can resolve from this end?
Okay, good. Thank you, ICT.
Okay.
Yeah. Sorry about that. So I will say that we pioneered the work using DFT computations to describe the anti-corrosion performance of a wide range of materials. We've also been able to do some work using the biomass inhibitors in drilling fluids. And I think this particular project, we just got a patent for that, for using some biomass materials to control corrosion in drilling fluids. That's part of the work we've done, part of the applications of our work so far. We've also done some work involving biomass inhibitors, corrosion inhibitors in anti-corrosion coatings. Got very pronounced anti-corrosion effect in this regard, and we're also preparing this particular set of data for another patent. We've done some work on superhydrophobic coatings. We're providing coatings that are very resistant to water absorption, and these have been quite effective in controlling corrosion in several kinds of environments, particularly in marine environments and the like of that. We've done also some work on what you call the self-healing coatings that are able to, because the main problem of coatings in the service is when the coatings are damaged by any physical forces, and we've developed coatings that are able to heal such damage on their own and maintain the integrity of the coatings, particularly in saline environment and other marine kind of environment. We've done that already. And also we are involved in certain studies to look at how this metal surface microstructure modifies or influences the performance of different anti-corrosion interventions. And this is closer to the focus of this conference on nano technology, nanoscience. We're able to determine how making a surface nanocrystalline or microcrystalline will influence the performance of any additive you add into the system to control corrosion. We've also done some also nanotech kind of work in looking at trying to discover the atomic scale origins of corrosion. We've done some work in this regard, and we identified several atomistic, we call it atomistic galvanic cells that actually drives the corrosion process. In this paper, we are saying that although we classify corrosion as uniform and localized, that at the atomic scale, every type of corrosion is actually localized because initiation is at those atomistic galvanic cells. But for this talk today, we'll just present some of our results on passivity. Many of us in the field of corrosion are very familiar with the phenomenon of passivity. In fact, it is believed that our metal-based civilization is made possible by the ability of certain materials to passivate under ambient conditions. And in doing this, they become immune. You know, the passive film tends to protect the metal or the alloy from further corrosion. And certain transition metals are very known very well to have this capacity to undergo passivation, and that is the main reason or the main property these metals are expected to play in different kinds of alloys, especially the stainless steels and other high tech steel alloys. But the problem is that the passive film is also prone to degradation. So what we talk about today is what is how are these films formed and how are they degraded or destroyed, right? And in the past, there has been several theories focused on passive film formation and passive film degradation models. Most of these theories and models are not based on very hard experimental evidence. Some of them are from computations and from theories, as is the case with science, or as was the case with science in the 19th and 20th century. So, but recently, we have this capacity now to look at materials with sufficient detail at the nanoscale, and this is what we've adopted to try to explain how passive films undergo degradation, especially in the presence of chloride. Because the biggest danger, the greatest, let's say, challenge of passive films is the effect of chloride ions. Chloride ions they have no mercy on passive films. So this is just a summary of the existing models, what they call the classical models of passivity breakdown, starting from the penetration mechanism model, where it is believed that the chloride ions will penetrate through the film and attack the interface here. You have the points defect model, where it is believed that passive film destruction is initiated at a certain defects in the film. We have the dissolution model. We have the film breaking model. So we have all these models for passive film degradation, which are not based on hard experimental evidence. And that's what we try to address in this presentation. So it's the questions that have not been answered, or that have not been answered in terms of passive film degradation what? In the presence of chloride ions is one, are chloride ions actually present in the passive film? And if they are present in the passive film, at what locations are they present? What are the atomic scale interactions that occur between chloride and the passive film? And these interactions, what structural evolutions do they induce on the passive film? Does the chloride affect the interface? And what kind of stresses? What kind of stresses do chloride ions induce on the passive film and on the metal film interface? So we are nowadays, due to increased availability of high definition, high precision techniques, it's possible to address some of these questions with some certain experimental exactness, if I was to take those words. So I'm just having this slide. This study, we relied a lot on transmission electron microscopy, particularly the aberration corrected scanning transmission electron microscopy. And people had given several testimonials on the importance or the capacity of this technique to provide information, on materials at the atomic scale. And it is this kind of information, this kind of capacity that we hope to rely on, right? To probe how the chloride ion modifies or affects the passive film on a metal. So the approach we used in this study was to combine the aberration corrected TEM with super X-ray EDS. using 4 detectors. And using this technique, what we observed are that there are atomic scale segregation of chloride ions at the metal film interface. We also observed some fluctuations on the metal matrix to passive film interface. We observed some modifications of the interface zones due to lattice expansions induced by the chloride ions. We observed some undulations at the interface, and we observed certain structural homogeneities on the passive film side. And based on these observations, we are proposing, a mechanism for passive film breakdown. So the approach we adopted was to grow first of all, grow a single crystal nickel chromium alloy of steel, and we formed a passive film on that single crystal in 2 different kinds of environments, in an environment that contained chloride ions and an environment free of chloride ions. So we formed the passive film on the 001 and 110 plane of the single crystal alloy. But this gave us the freedom, to investigate and to obtain the kind of well-defined passive film and interfacial region that we needed to do these experiments. And we're able to use different environments to look at the effect of chloride. First, we did a passivation in sulfuric acid. Then we did it in sulfuric acid with sodium chloride. Then we did an initial passivation in sulfuric acid before we now added sodium chloride into the system. So we have 3 systems that we're looking at. So in preparing the nickel chromium alloy single crystals, we observed clearly that it was mainly an austenite phase. It was a gamma steel phase. Then in growing the passive film, like we said before, we did a passive film on different kinds of environments. One is 0.5 molar sulfuric acid, which is the green one there, the green curve here. And then 0.5 molar sulfuric acid plus 0.3 molar sodium chloride, which is the blue curve here. And from both curves, we're able to determine that at 640 millivolts, we have a good passive region here. So we chose this 640 millivolts as our passivating potential. And the passive film formed as expected was very clear, very well defined, right? Had very clear the very straight and well-defined interface with the metal matrix. And this was what we needed. This was the main reason why we had to use a single crystal material for this study. You had a film of thickness of 4 to 5 nanometer with a straight and sharp interface. Next, we looked at the chloride-induced structural evolutions on the passive film. Like I mentioned before, we had passive films on in 3 different environments: sulfuric acid alone, sulfuric acid plus HCl, then sulfuric acid with subsequent addition of sodium chloride. So there's passive films we formed under these conditions. We are looked at using a super X-ray EDS mapping. So if you look at number 1 here corresponds to the passive film formed in sulfuric acid without any chloride. Number 2 is with sodium chloride, and number 3 is with addition of sodium chloride. So you see that for this number 1, there is no evidence of chloride enrichment in the system. But for 2 and 3, we can see that there is chloride enrichment in the inner layers of the passive film formed in the 2 environments that contain chloride. And if you look at the cross-sectional image of the films, right? You observe that for the film formed in system 1 without chloride, the passive film is straight and intact, as shown. While the films formed in the presence of chloride, we see that there is some there's some undulations, right? In this system where the film is formed in the presence of chloride, and in system 3, where chloride was introduced after the film had been formed. We also observe the same interfacial undulations, and we also observe the presence that chloride actually penetrates this film. So these are clearly observable experimental phenomena. So the question is now, how or why did this happen, and how did that happen? So we tried to look at the chloride transport mechanisms within the passive film for those systems that contain chloride. For instance, in the system where we observed that there was chloride penetration, that's system 3, we looked at it closer. Here. And we observed that one, the chloride does not occur all across the interface, right? The permeating chloride just appears at certain regions of that interface. That's one observation. And two is that it is not all the chloride that permeates the passive film, right? Also,
There is a break in transmission. So bear with us. Thank you. Maybe Emeka has logged out or something.
Yeah, sorry about that. Having some net muted. Yeah, look at the trans. So like I was saying before, we identified these nanoclusters within the passive film that acted as parts, that acted as a pathway for the chloride ions to permeate the interface and get, or permeate the passive film and get to the interface. So the point is it is only those chloride ions that are able to find direct paths from the film through the film to the interface that actually get to the interface. If the path to the film is truncated at any point, then you have the chloride ions unable to get to the interface, right? So that it's only those. So that is why you have the chloride ions not all across the interface, but only at certain locations on the interface. The next approach was to look at the interfacial strain distribution. We did this by using the simulation, the LADIA simulation. And we consider the three kinds of interfaces again, right? Again, we observe here the straight interface in the chloride-free environment here. Then in the interfaces in which we have chloride, you also see clearly, the model describes clearly these are undulation, EM. And you see that lattice expansion, which is more clearly explained in this particular image. There's lattice expansion due to the presence of chloride. And this induces some kind of strain on the passive film. And it is this strain that contributes to the adverse effects of chloride in this system. We also observe that chloride ions surfaces beneath the passive films, that the non-homogeneous CL gives an undulating interface because the chloride ion doesn't only accumulate at those regions that had a clear path from the passive film to the interface, to the metal surface. So there are some regions that had high chloride absorption, right? And we observe that in these regions, you had regions with high chloride absorption had faster film growth, and where you had less chloride, you had lower or slower film growth. So you had what they call the concave and the convex sites on the interface. So you also observe that the film doesn't break down where you have the most chloride absorbed. Rather, its film breakdown is initiated at the convex sites with a minimal chloride absorption, which is wasn't expected, yeah? So in the concave sites with high chloride presence is these sites. You have more film on these concave sites, but on the convex sites where you have a thinner chloride absorption, this is where we observe that the passive film breakdown is initiated. So these are the mechanism of passive, or the processes involved in film breakdown from our studies, right? In the sulfuric acid system without chloride, we had the very straight and very clear interface. No undulation at all observed because there was no chloride. But in the second system where the film is formed in the presence of chloride, we observe these undulations, right? We had regions with more chloride, the concave sites, and regions with less chloride absorption in the convex sites. And it is this, these convex regions that the breakdown of the passive film is initiated. In the system where we form the passive, you also observe that chloride does not get, chloride does not penetrate all through the passive films, that there are certain favorable sites, favorable paths that channels for chloride transport from the film to the interface. And it is at these sites, once the chloride gets to the interface here, you start to form the concave sites. And where there is chloride depletion, you have the convex sites. And where there is no chloride presence, where the paths are truncated, you have an unperturbed interface. So this is the model we are proposing for on passive film.
Oh.
Okay, so I was saying we observe that the chloride ions are accumulated at the metal film interface. So there's what atomic scale interactions occur between chloride and the passive film. So the passive film has these nano clusters that provide the that form interface with the film and provide the path for chloride transport. Do you observe that? Does the chloride affect the passive film? No. The effect of chloride is mainly at the metal film interface. So what chloride-induced evolutions occur at the metal film interface? We saw that non-homogeneous absorption of chloride yields the passive film with irregular undulating interface. And what stresses are present in the metal film interface? We saw strain-induced lattice expansion on the matrix side. And this is a stress that leads to the effect or the pronounced effect of chloride. So most of this study, we did it with our collaborators in China at the Institute of Metal Research, where they have a total of 13 TEMs, quite a lot, and they have 2 aberration corrected TEMs. So that's the group of Professor Ma that work strictly or using only the TEM to develop or to define or to probe several several processes that are not yet well understood. So they have the capacity, they have the equipment to look at the atomic scale interactions involved in all these processes. And this is part of the PhD work of Dr. Zhang here now, and Wang here. So thank you for once again to the organizers, Professor Zema and co, for inviting me to talk in this conference. Thank you very much.
Thank you. Thank you very much. Thank you, Professor Guzie. Thank you very much. Okay, the next presentation will be given by Professor Henry Isaac Elim. After him, we will have Professor Balasubramania, and then Professor Manikandan. After Manikandan, we have Professor Dare. After Professor Dare, we have Dr. Reddy. After Dr. Reddy, we have Dr. Tochibweze Amachuku, I think he's a professor, I don't know. So after this, we will then go for lunch. So I hope these presenters are available and they are ready to give their presentation. So the first one will be Professor Henry Isaac Elim. I've been seeing him, he's been around since. Okay, just a brief introduction. Professor Elim is a creative Indonesian physicist with a theoretical physics background. Obtained his master's and a bachelor's of science degree and master's of science degree from two of the best Indonesian universities of Gadjah Mada, UGM, and Bandung Institute of Technology, ITB, respectively. Furthermore, he has conducted a series of multitasking scientific development of nanoscience, nanotechnology, and herbal nanomedicine in the last 21 years with a distinguished 6-year research background in his PhD and postdoctoral work at NUS in the University of Singapore, as well as his 4.5 years position as a research professor in a mega project of super hybrid material at Tohoku University in Japan. In addition, Dr. Elim is the founder of the first Nanotechnology Research Center and Innovative Creation, PPNRI, in the eastern part of Indonesia, and has educated over 75 physics research students in the last 6 years, as soon as his opening of the PPNRI at Patimura University on the 24th April of 2015. Therefore, we can say without fear of contradiction that Dr. Elim has achieved an incredible output of over 85 high-quality works published in about 34 Q1 journals, according to Sinta Scobus Web of Science, with H index of over 25 and citation of nearly 4,000. Professor Elim, we are happy to see you here, to welcome you to Nsukka, Nigeria. The ball is now in your court. Hello, can you hear me, Professor Elim? Professor Elim?
Our Wednesday morning course. So quick look at the course today, they can see that was.
Yeah, it seems there is a communication disturbance or
somebody who is on to Zoom, just talk to him. Maybe he's not hearing me, but others may be hearing people who are also connected. Is he muted or what?
No, I'm not muted, but the communication is
in a hotel on the other side of the province now. And as
Henry, better you stop your video plus start your presentation, and that will be better. So that okay, that will be better. Thank you.
Thank you. Thank you. Ready.
I will stop my Zoom. Okay. I will start my Zoom. I will restart.
If this thing continues, we may have to go on unprepared lunch and then come back. Hopefully the ICT people would have resolved the problem. But let's give it a try again, another try. Dr. Reddy, can you hear me?
Pop can? Yes. Yes, I'm able to hear. Yeah, your voice is clear. It's not a problem. Luckily, nice connection. I think. Thank you very much for all Nigeria for IT support. I think they have done good job. I think thank you very much for all you people. Okay, great people and great friends. And then thank you.
So when we spoke to you, say they
Dr. Elim to start. Good. Okay. Can we then do that? Okay. Professor Elim, if you don't mind, we have your presentation. We can help you here with sharing it while you speak. If that is okay with you, we can do that.
Okay. Good evening, ladies and gentlemen. Can you hear me? I just restart my computer.
Okay. Okay. So is that Dr. Elim, Professor Elim?
I'm here.
Okay. So can we share your slide for you, or can you still share it from there?
Maybe you can share from there. So because sometimes there's a trouble from here. So
okay, we'll be happy to do that for you. Okay, thank you very
much, Professor.
Guys, please, Professor Elim has kindly allowed us to share his slide. Okay, your slide is here now. Can you see it?
Okay, thank you very much. This is my first time in the Africa scientific meeting. So I'm very, very glad to meet you, top scientists from Africa. And I was very impressed to the sharing of Professor Kenneth and another professor from Africa, Professor Ezema, and also Professor Jose. And it was incredible scientific sharing. I already learned a lot of things. So in this opportunity, I also would like to share to you guys from the all over the world, especially from the Africa side, because this is about the Nano conference. And this evening here in Ambon is already 9:34 in the evening. So over there we have 8 hours difference. And organizer from University of Nigeria in Nsukka was built since I checked from the internet, it's about 1955. And our Patimura University, the largest university in the eastern part of Indonesia, with over 24,000 students from 9 faculties and institutions. But our university is not as large as the African university. I saw the university in the Africa is about 5,000 acres. So huge. Maybe the largest in the world. So I'm very impressed. You guys are very, very big continent with ancient history. The first human being God created in your area. So this is a very incredible talk. So my file of talk is already sent to the audience. If not, I will try from here. Maybe here is how to share. Maybe I already sent my presentation file to Professor Fabian Ezema. Maybe it is better Professor Fabian can share from the Nigeria, so it is easy to see from all over the world, because the host is in Nigeria, in the Nsukka. I like the name of Nsukka, because N refer to the ant. You know, the ant is a very, very tiny animal, but a very hardworking. And Sukka in the Indonesian language means like. So like an ant like. So it's a very interesting name. So are you still try to share my file from there?
You see the slide. Can we move to the next slide? Do you want us to go to the next slide?
I can't see the slide from here.
Wow.
What's up? I don't know how to see the slide from here. Wait for a while, maybe I can. No, but you guys from Africa can see my presentation file?
Yes.
Okay. If you can see, so I can use another computer from here. So let's say that is the first page. So now, okay, now I can see. Okay, very good. Now is the second slide. So it is the first nanotechnology research center and innovative creation. It was founded by me when I just returned from Japan for about 4.5 years as a research professor at Tohoku University, the third best university in Japan. I was working in the mega project, 5 biggest project in the whole Japan about super hybrid material. We try to develop the best super hybrid material by combining the organic and inorganic nanoparticles. And we get the highest one, almost 2.0 in the refractive index. And the very transparency is almost 99%. And after such a long work, I returned to my hometown and we start build the first nanotechnology center from scratch. And we already built about 7 years. and we already have many good achievements. This is all the situation in our campus. These all our students. I actually built my center with garbage. When I started build nanotech center, we changed from stone to be super fiber, from leaf, from all the garbage become very super fiber, very good mechanical and optical properties. And we move on with the liquid energy, battery, so many things we work. Okay, but today I would like to share about the new discovery. And this discovery can handle to mitigate the war disaster problem due to the use of the energy with the radiative impacts, such as presented before by Professor Jose. Due to the increase of the human being on Earth, almost 8 billion men and women. So the environment of the Earth is getting broken, and the instability happen in the environment, and then the production of the lot of energy makes the global warming, and then make a disaster. You see, yesterday we saw the floods in Germany that never happened before. Germany, Netherlands, and Belgium, and also in Salzburg, Austria. I went there before. I was very surprised. So they also blame this is due to the weather problem. But actually, if we see clearly, when I was in Japan at Tohoku University, there was a huge tsunami due to about 8.9 Richter scale earthquake, and on 11 March on Friday 2011. Since that time, the Germany government closed up their old nuclear reactor, and they start to build the renewable energy by using the wind, the solar, and biomass, biofuel, and so forth. And just yesterday, they already get big flood. So this is all related to use the energy actually. So what I will explain here, I will offer a new way to use the gravity energy. Gravity energy, there is no radiation at all. So there is no impact in the radiation for the environment. And also it's very cheap. And also they no need battery. I saw Professor Reddy, Professor Jose, Professor Kenneth, other big guy in Africa. They are very, very good in making a very excellent battery. And as the battery expert in the world is already very, very well known. But today I will offer the energy, the new energy, which is I call the stomach gravity, stomach gravitism mobile perpetual device. I and my bachelor student in physics, we try to develop the theory, how to use the gravity and make a design, and then make the device is working forever. And the electricity will produce without like a solar system in the renewable energy, you need the energy storage to store the energy in the daytime and use it in the nighttime, because in nighttime there's no the light anymore. And also the wind also only working in a certain time, not working forever. So this is new technology will be very useful. This whole slide, how we can do that, because I have a theoretical physics background in my bachelor degree and my master degree in two best Indonesian University of Gajah Mada University and Bandung Institute of Technology. And my PhD at National University of Singapore, the best university in Asia and Australia. During the time, actually, I want to continue my theoretical physics work, but there is no professor who is fit with my background. So I switched to the experimental physics. So in 2001 is the beginning of my experimental to investigate the many different nanomaterial, from organic nanomaterial, inorganic, hybrid material, and a lot of many novel nanomaterial investigate the optical physics parts and also the linear as well as optical emitting properties. Okay, so you see that slide. If you see the whole universe, so this gravity is in the beginning of the creation, and this all renewable energy is coming behind. And if you see the general physics like in the slide, so we actually have a microscopic physics, which is classical physics, microscopic physics, quantum physics, and the physics with depends on the speed, which is special relativity. And by understanding this, the whole integrated physics, we can use our wisdom wisely to discover something new. So, for example, when you see this in this slide, the renewable energy we can use, especially on Earth, the solar, the wind, the hydrogen energy, the ocean, and the geothermal and the biomass and so forth. But the gravity is much larger because the gravity moves in the whole universe. And the gravity was generated depending on the two nearest mass, depending on the how big, how heavy the mass, and also depending on the temperature and also the interaction. Okay, move to the slide. So we can see the two different between confined energy and absorbed energy. In nanotechnology, we use the confined energy. All the electron in the 100 to 1000 atom become one scale. All the electron we confine like in the jail. So they are very sensitive. If there is someone come, they will interact very fast in the ultra fast time. But the absorption thing is you absorb anything. So there's two different things between the confined energy and the absorption energy. So this gravity is a kind of like absorption, not like a confined thing. So it's moving, absorb everything. So that's why when something feels the gravitation, is like gravitation can make it fall down. Okay. And okay, that was my PhD supervisor, Professor Jiwei. And that is when the first time I was in Tokyo, I attended international conference. I saw the Liberty Statue, and just 2 years back, I came to New York in 2019 to be invited speaker there. Before I went to Harvard and MIT, meet some important chemists and catalyst expert from Harvard in the Massachusetts Medical Hospital. I didn't get the Liberty Statue in New York, but it was in Tokyo. This is a bit smaller than that in the original one in New York. Okay, so that is the gravitational mapping from NASA, from satellite rotating over the Earth, and you see it seems like gravity is a very big one on top in the north part of the Earth and also in the Latin America. So this because from this mapping of the gravitation of the Earth, we can see the heavy mass in that area. The heavier the mass in that Earth area, the gravity is a little bit larger. So when we put this standard gravity equipment there, of course we can get better or larger electricity we can produce. And the gravity in the moon, which is rotating or surround the Earth, is about a few times smaller. If I calculate, there is 1.666 meter per second square, and on Earth is a 9.8. Okay, next, please. Okay, this work was done with my student. She just finished her bachelor degree in physics. That is Joshua. It is in our teaching lab. We have an integrated lab consists of the teaching lab. If you enter our integrated lab, we have left side is the teaching lab. The right side is our research lab. The behind of our lab is on the second story. The behind part, we have a nano medicine garden. And in the connection between the left, the right, and the behind is we have a creative living room. Professor Jose already visited our laboratory after we invited him for our international conference on basic sciences, and he is full of love because our laboratory is the very unique laboratory on Earth, probably because I built a lot of things with our hand from garbage, including table, chair, and so forth, including our lab. So if somebody came there, one day there is a group from Australian University of South Cross University of Australia. Is there with one big bus. Wow, it was very inspiring, very inspiring. They never saw our laboratory something like that. This whiteboard also is from garbage. I collected from garbage and I clean up and I make the frame and then I put there. Okay, okay, next please. Okay, so the first electrical generator was made using gravity energies in UK, but what they did is they dig the hole down to the earth about 150 meters, and very heavy load things will be put down due to the gravity, and it will be stored. The energy will be stored connected to the wind renewable energy and also the generator electrical system. And what we thought, this we will use too much effort and a lot of big risk because this the bottom part that uses the gravity is very heavy. So what we will do is we will make a mobile because our Maluku province has a lot of small beautiful islands. So we have to move the electricity from island to island, from area to area. So what we do, we have to do to solve the theoretical problem first, using very simple physics understanding, and then make the design, and then make the device. Okay. So next, please. Okay, the second part of my talk is the comparison between this is a STIMEC gravitism mobile perpetual electrical generator with renewable energy. Next, please. Okay, according to this energy mapping, last year I had a master student from Germany, Nordhausen University of Applied Sciences, the area where Martin Luther, the founder of the Protestant religion, they have a very good university there, named as Nordhausen University of Applied Sciences. They sent one master student to me for 2 weeks, and I educated him to be my student to map the energy in the whole our province as a prototype for the whole Earth. So, and when we collected the many data in our province in 27 institutions together, and one of the work we already mapped this whole thing, and also her master thesis already offered. And if we see the whole Earth, of course, the renewable energy is much better than the nuclear energy, because the nuclear energy will produce, carbon, a lot of carbon, and this will make a global warming. Okay, this is a danger for the environment, and also we see our province. There are many very beautiful islands, very small. Dr. Reddy has visited a few islands over there, so he must be very happy. Because when I went to NASA Germany in 2017, there is a very experienced engineer working in NASA Germany. NASA Germany is located just next to Humboldt University, the #1 university in Germany. He told me, I found heaven. I found heaven in your area. Really? So I asked him, do you believe in God? No. He said he was atheist. So why you said you found heaven in our area? He told me, I already visited all around the world. I work in NASA Germany already 35 years. My small device already fly to Mars and take a photo in the whole Mars for 1 year. And we make the prototype of the surface of the Mars. But I never saw the area which is very beautiful, like your area. So he also saw a few different islands near Ambon City. And so he said, I'm just walking like in heaven. So it was the first video show to talk to me in NASA, Germany, that our area is like heaven. Okay, so this is the mapping of the whole renewable energy on Earth. So you see in the reverse triangle there, this is your area, the African area. You guys very, very small use the renewable energy. You see the America, the South America, or the Latin America, the China, the Australia. So this is a big opportunity. Before your area was broken due to the use of the radiative energy, including renewable energy, it is opportunity to you to build this stomach gravitism mobile perpetual device. You can generate the electricity and you need to use the battery. It will work forever. It will rotate the electric generator and work forever. Okay. So it's not, this is my first time to tell this in the international forum. So you guys are very lucky to listen this for the first time, because our paper just published, and when I did present it a few months back in the Indian International Conference, I didn't expose the detail of the calculation, but this is the first time I expose everything here. So it's an opportunity for you guys to develop it. Okay, next slide, please. Okay, so if we compare the Asia energy, China uses a lot of energy. Okay, so maybe one day they will have a environment problem, and they will face the very, very big disaster like flood, or maybe a lot of landslides and a lot of very, very big wind, or maybe extreme weather. This is all due to the radiative energy using. Okay, next, please. Next slide. Okay, so this is the mapping of the renewable energy in the whole Earth, and also the mapping of the whole Earth population. So I did presented this in the India conference a few months back. And there is a question, how about we make the energy without radiation, and it is eternal? So the answer is gravity. Okay? The gravity, no radiation, and it is free. You can use any time, whether in the day, at night, and it never stops. It moves in the whole universe. Okay, our universe has now, according to the NASA observation, is more than 4 trillion galaxies. So maybe if they have a better technology, they can see more. Okay, next slide, please. Okay, that is the difference between eternal energy-based gravity and renewable energy. So I mentioned the eternal energy-based gravity, we have free of radiation, no need battery, and less global warming. So this is the mitigation. If you can imagine, if everybody used the energy without radiation, so we can reduce the global warming very dramatically without any carbon, all the radiation. Okay, then we can start to enjoy our nice environment. We can enjoy we don't need to worry about flood or landslide. But earthquake, it never stop, because more human being, broken environment, the earthquake is always increased, never reduce. Okay, and renewable energy, you will face the radiation problem. You also need the energy storage. That's why many people working with the energy storage to store the energy and use it anytime. And we will face the big global warming with many different disasters. So that's the problem of the world disaster caused by the use of the radiative energy. Okay? So the question is how to face this whole thing. So the question is in this talk tonight. We should develop this stomach gravitism mobile perpetual electrical generator, so that we can generate energy without any radiation, and we can use it forever. You don't need to pay anything, you just have the device and you can generate electricity. In this talk, I will talk. Okay, next slide, please. Next. Okay, so this is my first time. We actually already have a very close chat between Professor Fabian Ensema and me, but we haven't met before. I believe next time I will invite him to be in Indonesia. We can have a very good collaboration, and especially there is an international conference annually. So, but I already involved Professor Ensema in our Science Nature journal, the first international journal from our university, and it's an inventor journal. So we have a lot of work to do that. If somebody didn't contribute, our laboratory ourselves will contribute to the whole work. So we come to contribute, not to ask other people and burden them. Okay. Okay. Next slide, please. Thank you. Next. Next. Next slide. Okay, so the important thing is how about your theory and how about your design? Okay, okay, I will explain it in the next few slides. Next, please. Okay, so this is the theory and design of our stomach repetition mobile perpetual electrical generator. Next, please. Okay, before we try to derive the theory, very simple mechanical thermodynamics and also statistical mechanics theory integrated one another, we have to understand this system. Okay, you see I draw the Newton and Robert Hooke. These two guys saw the force from different view. One Newton see from the mass and the acceleration, while Robert Hooke saw the vibration of the mass due to the spring. Okay, but these two different systems actually has same one another. Okay, so just like we see a house, one from the east, one from the west, but actually they saw the same thing, the house. Okay, okay, this is the so I call this century, many other people say 21st century, sophisticated nanotechnology century. I saw it's the truth century, because the knowledge of the human being is already very close to God knowledge. You know, you see everything. Okay. So I saw it as the truth century. Next, please. Okay, so from very simple this understanding, we can apply to anything like now how to control the society 5.0, which is already implemented in Japan, and the industry 5.0. Everything will be just you program the robot and robot will do everything for you. Okay, it's a 5.0. Not now Indonesia is still use 4.0. Everything will be in digital file. So I describe it like the electrical system, which is with the circuit, with the resistor, with the inductor, and also with the capacitor. And also we can use like we make the super fiber. It depends on the structure. So that's why I explained with mathematics. If you talk about the structure, you should understand the theory of number and the algebra that make the structure of the mathematics of the whole universe. Okay? And applied mathematics, you can use the statistic and also probability. And from the combinatory, you can use the discrete of mathematics. And from the geometry, you can make the space. And from the logic, you can make the foundation and the philosophy of mathematics. So this all in nano structure, different properties, different material, different behavior. So we can explain it like a spring, you know, a spring with the different spring constant like K1, K2, K3. Okay, so this is all physics. So physics is very amazing. Okay, I didn't want to be a physicist, but our Father in heaven guided me to be a physicist. You know, when I was a bachelor degree, I entered in the agriculture faculty. After 1 year, I suddenly get offered to study physics at Gajah Mada University with the Canadian scholarship. So it is not my eager. It is just planned by the God Almighty. So that's the reason is because He's eternal. He created all the eternal rules, all the conservation laws in nature. From the tiny smallest thing, charged particle is a conservation law, never change in time and space. until the momentum, which is accelerated by the speed, and also until the energy, the momentum accelerated by the velocity, they become the eternal energy from the, dark energy, which is 95.1% much larger, with no radiation on the universe, and the very tiny 4.9 bright energy. It was created after, like the first slide, I described the light wave just created, about 10 to 5 seconds after the Big Bang. And before the Big Bang, God already have a dark energy, nothing, just dark everywhere, and God alone over there. And after the creation, the time just started, and the light started later after 10 to 5 seconds. Okay, next. Okay, this is how our plan to solve how to use the gravity, just by simple understanding in the integrated understanding of mechanical rotation. Why? Because God make everything in order by rotating everything. For example, the moon is rotating the earth and the moon rotating the sun, and the sun, the solar system also rotate in our Milky Way galaxy, and the Milky Way galaxy is also rotating in another galaxy surrounding the Milky Way. So this is the thought of God to make everything eternal. Nothing can stop, okay? It will be work forever, okay? So that's the original thought of the God Almighty. So we learn from this idea, and then we understand the thermodynamics. Thermodynamics, you're talking about the entropy and enthalpy, and statistical mechanics about system with the many particles, how to arrange this all statistically mechanics, okay? And we get this connection, and from this all connection, we get the formula, and we can design the equipment, okay? So the equipment is very simple, okay? We can, how to rotate this equipment, like, for example, like you have water, and you generate, fall water to that, the blades, and the blades is rotate, and the rotation will generate the electrical generator. But this way, it's not by using water, not using by wind, not even from the light, but it is from gravity. So once you put things, and the gravity will make it rotate forever. And then this rotation will connect it to electrical generator, very simple one. You can use the couple of wire with a certain number of wire, and then you can connect it to in the, depending on what is your purpose, you make the alternating current or direct current. This is the system of wire will be moved by the gravitation behind among the magnetic field, and the wire will be connected to the light. So the light will so we can from our formula we can do the numerical, and we can get the best parameter. From the best parameter, then we can make it become a reality. Okay, next slide, please. Next slide. Okay, so this is a very simple stomach gravitation equipment. So just done by me and my very simple bachelor student. Okay, so that's the rotation. You can just do that, and it will move the wire over there, and the wire among the magnetic field. Okay, this is a very basic physics. The only thing is how to explain the theory of this rotation, unstoppable rotation due to the gravitation. Okay, that's the whole thing. The other thing is only basic physics. Okay, so next, please.
You summarize.
Next slide. Am I still have time? Okay, next, please, because maybe time is very limited. Next, please. Yes.
You summarize in 5 minutes, please.
Okay, I will summarize in 5 minutes. So this is our important paper about this stomach gravitation. We publish in our International Science Nature. Next slide, please. You guys maybe has a question. So one of the discovery in our theory is the definition of the constant temperature. Until now, nobody can explain what is the definition of constant temperature or temperature in the isothermal condition. So we discovered the very simple formula by derive this whole connection in physics, basic physics, and that's the formula. So there's actually the constant temperature is actually the definition is like that. Okay. Next slide, please. So this is the way how we because time is very limited. So I just show you. You can, if you need the whole things, you can just upload the journal in our Science Nature paper. It is open access, so it's free. Everybody can download freely. Next slide, please. Next slide. Okay, next slide. So this is the just very simple way to obtain the accurate power of the electricity due to this stomach gravitation profile mobile perpetual device. Next, please. Okay, so finally we get just very simple formula to our stomach gravitation mobile perpetual electrical generator, which is only depends on this the number of turn of the wire. Depending on the best wire, you can use the copper, the magnetic field, and also the area of the wire that move rotation among the magnetic field. And these all the other just simple parameter in our device. Next slide, please. So, okay, this is the best numerical. So from our 5 kilogram mobile equipment, we can generate at least 100 watt alternating current with 50 hertz alternating current. So this is, so about 5 kilogram, we can carry, we can use the electricity everywhere, okay? If you want to generate a city, then you can just enlarge the equipment, or with a certain development of the research, you can improve the material of the device, even the same 5 kg, but you can make maybe 200 watt, 500 watts, or maybe 1 kilowatt, okay, in a 5 kg equipment, okay? Due to this gravitational force. Next slide, please. Okay, so it looks like something like that. Okay, next slide, please. Next slide. Okay, so this is just I already told before. So the problem of the disaster in the whole Earth actually because of the use of the radiative energy too much. That's all. That makes the problem of the everything on Earth. Next slide, please. Next slide. So this is the impact in the nanotechnology, okay? So this is the whole thing about nanoscience, from the quantum theory of and nanotechnology, the implementation of the theory, and also the nano medicine. We make our own nano medicine garden. I was invited in Las Vegas, in New York, due to this nano medicine, okay? Due to this nano herbal medicine. So that can have a multitasking healing, okay? Including the problem of COVID-19. You know, our COVID-19 medicine from herbal was rejected by the scientific reports. After minor revision, it was very funny. They just changed the editor from Italian editor to the Polish editor, and the Polish editor rejected it without any good enough reason. But it was very important. You know, the COVID-19, it attacked the lung. You know, the lung, there's no blood. So you have to kill the virus, you have to stop the virus with the gas, okay? Not with from the blood to blood, but from the gas. So we use the gas from herbal medicine to stop it, okay? And we already try to implement in our family and other friends, and they get healed without any injection or without any vaccine, okay? But the paper was rejected by the scientific report after the minor revision, and they changed the editor. So this is why Jesus said, you will be rejected, because I already have been rejected before. Okay, next slide. That's all. The thing is about your smart thought. your efficient of discovery, your excellent discovery. So this is the impact. So this device will be implemented in everything, okay? In your laboratory, in your government, in your university, in the whole earth, even in the space, okay? In another planet, in another galaxy, okay? Next slide. Okay, this is the last slide. Thank you very much for your attentions. Okay, God bless. Thank you very much. I will return the talk to the moderator.
Okay. Hello? Okay. Thank you, Professor Elim. Thank you very much. Sorry, we are running late with time. I would like to appeal to our future presenters to please be mindful of the time. We don't have a way of controlling your time there. And it would be very rude for us to cut you when you are still talking. So we hope that you will help us as colleagues. Thank you very much. But you didn't spend more than your time, Professor Elim. You did very well. Yes. Okay, sorry, we can't take questions now. We want to finish before we go for break. The next presenter would be Professor Balasubramanian. Professor Balasubramanian. Is Professor Balasubramanian there? Eh? Okay. Can we then ask for Dr. Reddy? Are you available? Would you be able to?
Yes, I'm available.
Please, Reddy, we know you are a very gentleman. We know you very well. Please, if you don't mind, help us with the time. We want to recover some time. If you can do it in 25 minutes, that would be awesome. Thank you. I will read his short CV.
Okay, I can.
Okay. No, don't worry. Let me read their short CV. Colleagues, Professor M.V. Reddy obtained his PhD in 2003. He has been a friend of the Nano research group here in Nigeria at UNN. He has been working with us. Every time we do this, he's always there to assist. He obtained his PhD in 2003 in the area of material science from the University of Bordeaux in France. He spent some time at the NUS, the famous NUS National University of Singapore, doing a lot of work in various areas of lithium-ion batteries, from cathode to anode, supercapacitor, and the solid-state electrolyte. He is a highly published. He has published. Dr. Reddy has. Hello. Professor Reddy, can you hear me? Professor Reddy has published over 160 research articles in high impact journals. He has given a lot of presentations nationally and internationally, including plenary and keynote lectures. His impact factor at the moment is more than 50, and with over 9,500 citations. Presently, he is in Canada, he's now in Canada at the famous Quebec, Hydro-Quebec, as a senior researcher there. We want to welcome Professor M.V. Reddy to the conference. Professor Reddy, you are on.
Whatever, hello?
Yes, we are hearing.
Okay, whatever, Professor Ken, hopefully my voice is audible.
Yes, we can see your presentation and also your voice.
Okay, thank you. Once again, thank you very much. So since I don't want to introduce too many things, so just I'd like to, since I'm almost like, I missed this conference. In fact, last 3 conferences I've been attended organized by Professor Ejima and then all the organizer. And also I'd like to thank Professor Ken. Actually, he is a person introduced me to visit the African soil. In fact, first time was in South Africa and we met Ken and all the team, including Paul and all the, in fact, especially University of Nigeria. And I think we had a nice opportunity to visit the good peoples. Again, I think, again, we would like to remember the CEO of the Oil Soros sponsoring the previous events, and then this event also, I think they're able to supporting this event, and all the university for the sponsoring, especially this type of events. I think this is very important, especially Nano conferences. I can tell that in Africa, first time, I think in the University of Nigeria, you people have done continuing. I think this is good, keep continue. Okay, again, thank you very much, Professor Ken, for his, I think, for his attendance virtually. So especially he is able to travel from South Africa to Nigeria. I think thank you very much for his interest and then support for this conference. So presently based in Quebec, where the French and English speaking colony. So here, so again, we can see the extreme climate. For example, the temperature minus 20 to 30, depending on the, and some other beautiful seasons we can see. Especially now it is summer. I think it's almost a nice, beautiful climate. These are my outline of a presentation. In fact, I think this slide is very important for all Nigerians. I don't think you might have not seen some young people today. I don't know. I'm not able, by seeing that video, not see any young students. Especially you can see here, first time when I came to 21st conference at the time, I didn't see, I used to print some Singapore high school kids and all the stories. I didn't see, maybe after 3rd time, I think people were motivated. I think Professor Ken, I think a lot of school students have been, I think 3rd conference, I think they have almost 1 week or 4 days, they attended all the talks. In fact, clearly indicate that I think you actually with the conference, you motivated the young researcher. I think hopefully they're going to do future in terms of nano research, or if you go for any type of engineering, nanotechnology, it applies to for all their, not only science, physics or chemistry. It looks like all, in fact, I think this is one example in 3rd conference, already you have been demonstrated, especially young researcher. So it clearly shows the importance of this conference. In fact, and also I can see actually these are virtually we are presented, and also you can see some beautiful gift given put on the shirt with the conference organizers. Still we love the things, and then thanks for the hospitality. And also I'd like to see our close collaborator and a friend, Professor Joyce Rajan. In fact, he has given me excellent talk in the before. So also another our close friend from India, I think he is not able to present this time. I think thank you very much all the people, including some other people from, including Rav and all the people from India, etc. So again, these are my small contribution. In fact, we have been trying some lot of school students. Again, idea is that nanotechnology, anybody can learn, only we need some good facilities. That's why all the students can learn. Only idea here is that I think we have proper facilities. I think that is very important. Still, I think based on my experience, you see the first visit and second visit, there is a lot of improvement in, especially in university also. Hopefully keep on continuing further this type of outreach and more research oriented university you're going to do. I think thanks again, International Collaborative Agency. I think Professor Ken, I think is helping a lot, especially a lot of African Nigerian students have been interacting and they're visiting his laboratory, and many students have been trained under him. I think we would like to thank Professor Ken for his constant support. Still, we need this type of faculties. I think we have to motivate the young researcher. That is my personal opinion. Again, some students were able to present the national, and for example, some publication as well as a conference presentation. Especially, you can see some students are able to present it like national conferences, science and engineering fair, and also some other conferences. Like, so I think there's an opportunity for them to present like us. Some, for example, instead of we are presenting in 30 minutes, they're able to present their presentation, almost 1 year presentation in 10 minutes, like that type of thing. And few students are able to present in various Intel International Science and Engineering Fair, as well as some other competitive exams. And these are the small, we have done some outreach with various parts of the, including our neighbors, Indonesia, as well as some local students, etc. These are the small students have been trained. In fact, 3 to 4 students from NUS only. In fact, there are nice opportunities with some few exchange students, including I think Nitya is also, Dr. Nitya is going to now presently, she is I think she supported with Professor Ken, I think during his time, and then now she is a senior researcher in the CSIR. I think she's going to present some of the our work today, tomorrow, some kind of some presentation, and some few other people from Iran and some small work we help them. I think these are my small collaboration. As you can see clearly. So again, we had some few publication based with Fabian with other team, Energy Center Nasuka, and also including other part, especially Professor Ken and different. I can see that Professor Ken and other part of the, including, I think you may see the presentation that Professor Josh Rajan, and also we are working closely, and a few other collaborators within Singapore as well as a different part of things. I think these are my small interests today. I think we focus on something like some novel, maybe lithium-based materials. I think Professor Ken, I think all the other topics has been covered with different speakers. So since I don't need too much introduction, I think all the people know the importance of nanomaterials. Again, energy, water, and healthcare, and especially we know that these are the very hot areas of top worldwide people are concentrating. Especially as a researcher or any human being, it is our responsibility to maintain the healthy lifestyle, reducing the pollution, especially if we talk about the smart city development. Again, materials are broadly classified based on the utility and based on the physical properties. Again, I think all the area nanotechnology will play an important role. I think since we see that previous speaker have talked about different areas, I think maybe we focus about mainly battery or again energy storage or different topics have been covered with a different. So I'm going to focus with a small, since they've given me 30 minutes, so to make sure that everything should be proper. So these are the very important areas. If you talk about the smart materials in terms of civil engineering and then thin film technology, or sometimes electronic material for photovoltaics, or for example, resistive switching memory, LIDAR technology, graphene, and 5G, 6G, these are all very hot areas. I think people, again, depending on each areas, I think somehow nanotechnology will play an important role. So if you talk about the green energy, so we have a lot of different type of sources. I think solar, hydro, and different, depending on what type of natural sources available. I think again, green means it is like renewable, and then we don't see any what they call as danger to the pollution, etc. Again, energy storage is interdisciplinary area of physics and chemistry. That's why we need science and also engineering. You see carefully, if you talk about electric vehicles or hybrid autonomous vehicles, again, we need importance of the different type of the researcher. Again, research is needed. If you talk about novel materials, it depends on what type of expertise and for future energy storage applications. This is one small slide. I think already people have talked the importance of energy. If you talk, you want to store the battery, for example, batteries are very important devices. You want to store solar energy or wind energy or to run the electric vehicles. And again, we can reduce the pollution, etc. So another important point, if you talk about the small autonomous vehicle, again, so here I'm telling that some people are electrical engineer, mechanical engineer, all people are play an important role. You want to develop, for example, computer or the sensors, or for example, suppose you want to develop engineering, mechanical engineer or automobile engineer, etc. So it clearly indicates the importance of science and engineering in the area of electric vehicles. I think these are the different type of opportunities with the different type of worldwide companies. I think these are the different, I think all people are carrying this type of mobile phones. I think we may see this type of positive, negative electrode. and sometimes cylindrical cell. And future, if you're running with electric vehicles, it looks like again, materials are same depending on the packs will be different. Again, the safety aspect people are going to concentrate. So these are very important factors. If you talk again, we need to look for high energy density, high capacity, and long life, and adapt the climate condition. Again, the way to assess temperature means low temperature, high temperature, and good coolant efficiency, and resistance should be lower, and fast charge is very important. Always people want to charge within 1 minute, 2 minutes. Is there any problem? There is a things again here importance of nanotechnology will play an important role. Again, after looking for safety, cost, and toxicity, again always I think Professor Jose already mentioned that importance of sustainability. I think that is very important. Not only batteries, any type of the technology or anything, I think we need a green and sustainable recycling. If you don't recycle it, again, you are making the environment, I think, pollution. So that's why these are very important points to take into consideration. I think these are general slide. I think I don't have much time. Quickly, I'll go through, as you know, since many talks are going to cover by the different speakers. Again, it contains the cathode, anode, and there is a separator. Usually, if you call it a positive electrode, if you talk about lithium battery, lithium containing materials. If you talk about sodium battery, sodium containing metal oxides, or if you talk about potassium battery like that way, or different type of things, etc. Again, anodes, we use negative electrode if you talk about lithium or graphite or sodium or potassium, depending on which type of the ions you're talking. Again, some metal oxide, or sometimes people are talking about calcium, aluminum, and zinc. And again, you have to remember, go to higher ionic radius, there is a mobility issues and then the voltage problem. So anyway, still a lot of fundamental things is going on. Sometimes, although criteria is that the energy density, we cannot solve all this one. Still, there is a nice opportunity for us to understand, especially academic researcher, we can do things. Again, the oxidation, we call as anodic scan, a positive current state of charge. Some engineers, they would call discharge means reduction. So, and electrolyte, we use something like liquid-based electrolyte and ionic liquid and etc. Again, current correctors, we use some copper-based, and again, we remember copper is good and it will not reduce further. Here, aluminum, if you use, means aluminum is stable up to 5 volts. Copper only up to 3.5 volts. Again, binder is the things it will stick this sample in the current collector. I think this is a way, if you talk about any big type of device, the only thing is that depending on the package, people can do the thing. Again, if you see this very importance of the 2019 Nobel Prize is given by one of the well-known three both physicists and chemists. In addition to this one, French Michel Armand also play an important role in the early development of the, you can see the early history. I think intercalation concept was developed in 1972. So that's why also I think is also one of the early contributor and developing the, for example, polymer electrolyte, etc. I think the principle of the batteries, again, nothing but shuttling of the lithium from the cathode to anode, where the electron will pass to external circuit during charge. During discharge, reverse reaction is occurring. Again, remember, so same thing. So if it is the metal ion is cobalt 3, it becomes 4+, which is oxidation. Same thing if you remove the lithium, for example, current versus voltage plots, cobalt 3 plus to 4. That's why we call as oxidation and reduction. So that's why always people will call as the rechargeable, means you have to get positive current, negative current. Similarly, if you take the same material, what I have shown, that's cobalt oxide, we remove the lithium capacity over voltage versus capacity by galvanostatic mode, you may get almost 3.9 or 5 volts. So usually voltage of the cell is nothing but charge minus discharge. So there is a difference. So that's why always you to look for the higher the voltage difference and extended plateaus, in the sense that if you want to be high energy density, always if we are able to discover any new material, maybe go for 400, 500, it will break through materials. We can again, there is a lot of interest. In fact, if anybody has new ideas to produce new materials, extended plateaus, I think this is really interesting for the future applications. So I think mechanisms we broadly classified into intercalation, deintercalation is the most commonly used reaction, because here we don't see much volume variation. And also interestingly, remember, so here we don't see much. The reason here is that usually any batteries should be less volume variation during cycling. I think this is very important criteria. And you talk about silicon and tin will undergo alloy forming elements. Again, here the importance of nanotechnology. People want to make some nano sizing or some carbon current collector. Again, you have to need it. Again, here also importance of nanotechnology. Talk about the conversion based oxide, and then again So I think this conference is being covered with a different type of materials with a different speaker. Either you can do lithium, sodium, and potassium, etc. I can do. I think quickly I'll go through ideal materials, always very important. In new students, you want to start research, you look for the low atomic weight, 26,800 number of lithium into molecular weight of any material. It will clearly show that always you have to look into the atomic weight. I think that is very important. And already discussed, anode should be able to get lower discharge potentials and cathode should be higher charge potential. The voltage of the cell is nothing but charge. When it's discharged, you will get some voltage. And if you talk about energy density, the voltage of the cells multiplied by capacity. So that is the way usually we'll do. And then now people want, depending on the requirement, they can pack 18650 cell, and depending on that one, whichever the requirement type energy people can do. That is the way UV, you need a big, so many cylindrical cells are needed for required energy. Again, you have to look for the material should be stable with the solvent, in the sense that electrode, electrolyte don't react. And we need some good, because people always talking about fast charging, discharging rate. We need a mixed ion conductor or sometimes conducting carbon coating. Again, here in nanotechnology would play an important role. Okay, in summary, if we talk about other type of batteries, again, because of lightweight and design and flexibility, we can use it for different type of applications. Electrolytes, we use something lithium-based electrolyte. Again, advantage is that liquid electrolyte has good conductivity, and there is a problem with the flammability issues. And again, not avoid that one, people are using some polymer electrolyte and some solid electrolyte. In fact, the solid electrolyte covered by our colleague, Dr. Prasad Rao, in a detailed presentation is going to discuss what are the different type of solid electrolyte and what is the status of the, since I don't have time to discuss on that one, so I'm going to skip the detail. Again, the separator to avoid short circuit, and these are a very important point to take into consideration. Why I'm telling that, since some chemists are there is opportunities for you polymer chemist. You can think about separators or lithium cut or inorganic chemist. Look for some good stable electrolyte more than 5 volts or 6 volts. I think that is really challenging for the any nanotechnologies or any chemist during this in this conference. I think these are the usual way that are depending on applications. I think always identify the materials, and accordingly people are looking for processing and then study the characterization, etc. Again, I think these are all things I don't need to explain, and the various application. In fact, this conference is being covered with the different topics. I think this is very important conference. I can tell that with thanks for the organizer inviting for the wide variety of speakers with a different type of the topics. I think this is very useful for the. So these are the various material synthesis and processing. Again, either you can do chemical method or physical method, or sometimes you're a metallurgist or, for example, mechanical engineer. They want to material should be more compact and good mechanical properties. For that case, they will use hot press or spark plasma sintering. I think this technology, if you want to talk about peroxide fuels or all solid state battery, I think this technology will be very useful. So due to time limitation, I'm going to skip a little bit details. Again, thin films, either you can do chemical and physical methods. Again, so advantage is that each technique, depending on to optimize thickness, we go for industry, electronic industry, composition, and these are all the things where we're going to do more details once you into the detail, especially if you work with electronic or IC industry. There you have to learn ALD or, for example, PLD or something, MBE, etc. More fancy techniques you're going. Again, you remember some of the techniques already people are, you're going to learn during the EEE course or from the electrical engineering courses or different type of the areas. So again, so as a physicist, you can take, if you talk about, for example, RF sputtering, you can open the glove box, everything, you can open the cells, everything there. You can do various physical parameter and vary the composition, deposition rate, and we can understand the various physical and different type of applications. Again, advantage of the depending on technique, we can do understand the various deposition rate, etc. Since I have another 12 minutes I have, so that I quickly will go through. These are various nanomaterials. If you talk about energy storage, either nanoparticles, plates, again, it depends on which type of chemistry or which type of recipe. We can use that one. Accordingly, appropriate techniques you have to use. So I think these are very important techniques. I don't have time to discuss more detail. Again, the XRD is a very useful tool to understand the cation mixing. And for example, thin films, we need RBS sputtering technique. And if it's a battery, we need something like galvanostatic and impedance analyzer and some of the other well-known characterization techniques. So these are the various tools, for example, XRD, Raman, and then some characterization tools. If you talk about the battery testing, I think you need some battery tester or impedance analyzer or something like cyclic automograms is useful. So what I'm telling you, X-ray, if you talk about the materials are the polycrystallines or nano size or amorphous, I think that is very useful tool. So again, if you want to see nanocrystallite size, if it is a nano, so I think X-ray is very useful. Or if you have thin films, you can do layer by layer deposition techniques. So usually, and also sometimes TEM, it will tell if it is nanomaterials or sometimes depending crystallinity, amorphous, nano, and then submicron sized materials. Usually the distance diameter divided by 2, then 1 over d, and then you can calculate the d value obtained by TEM, and then XRD we can calculate. I think these are the various, since your physicists are there, you can, I think 7 crystal groups are you going to use. I think what you learn from theory, later you are going to learn all the importance of this particular structures for the future applications. So since some physicists are there, usually thin films, how we can do within RBS spectroscopy. I think this technique is very useful tool to understand when the helium beam meets on a particular thin film with the backscattered energy. We know that atomic cross-section is directly proportional to the atomic number. It means the higher atomic number will come to higher channeling energy. From that, we can, by knowing the RAM program, we can calculate the composition thickness. In fact, there's a nice opportunity for me during my PhD, France as well as NUS, we have our own in-house Van de Graaff generator. I think RBS, that's why we're able to access the instrument very easily. So in fact, for thin films, I think this is very useful tool. It's not so easy. All people cannot access because of the this source is very difficult to get all the people. Again, we need something like central facilities to do this type of research. So now quickly I'll go through, if talk about cathodes, I think as I mentioned that capacity is limited. So we don't, that's why the major challenge. So we have to extend this capacity limitation. Anodes, these are the limits. I think people that are doing with either by chemical methods or sometimes optimize the performance by using surface coating. Again, the importance of nanotechnology here. I think people always want to nano coating to cut the to surface protection or improve the conductivity of the sample. I think these are the various, I think the important cathodes, for example, what they call a NCM, depending on composition, nickel content, and there are some of the compositions have been commercialized, and iron phosphate and some other type of the cathodes, etc. Again, I think they're all known, it is not really new things. So I'm telling about, since I talk about some new example in later slide, again, use of the tube furnace, and then sometimes you can do carbo and graphene thermal reduction method. So again, we need something like argon gas to purge the things to maintain the atmosphere. So again, is very important. If you want to reduce any metal, accordingly calculate amount of carbon you can put, and we can reduce and we can get a respective metal oxide. Again, it is very important. So again, this is one example, lithium vanadium fluorophosphate. I think we can try to prepare the sample. Advantage is that vanadium 3+4+ Rux couple, as well as we were able to do XRD as well as. So this is the usual way. I think this, quickly I'll go through, since another presentation also is going to be in the same topic. Usually depending on you make some active material binder and current collector, and finally coated on the aluminum or copper foil, depending on which type of the cathode or anode, and roll it, and finally make it circular disc. Again, pass in the glow box, or if it's a big common, like big industry, they use something like all the automated, everything they will do depending on which type of size and which type of pack, accordingly they can cut the electrode. So these are the way how we can do coin cell. You can put something, this type of cell, put it somewhere here, and then separator, and then lithium metal. Finally, the cell is ready, and we are able to do this particular cell. And this one you can do what they call as fast charging, discharging, or any type of the simple electrochemistry you can do in the laboratory. So what I am telling that if you compare with other type of cathodes, again, always we have to look for the voltage means 4.2. That's why vanadium seems to be slightly higher voltage. As a consequence, you can get high energy density and also reasonably good cycling stability. I think we are able to run almost like 6 months with the low current rate of the battery. Again, you can do some impedance and then some more if you are physicist, depending what type of facilities you have, you can do things. So in summary, I think energy density is also very important. That's a very good point I want to tell. Some, if you talk about novel cathode vanadium based system, among them tetragonal waste LiVPO4, and then some metal organic framework material. So if you compare with lithium iron phosphate, 3.5 volts we can get. So the same new materials we're able to go to 4 volts. So advantage is that although voltage is higher, again, sometimes now there is a scope part to these materials to look for the high energy density. Again, due to time limitation, I'm going to skip the details of how we can prepare materials in a green synthesis with a simple. So again, to remember this type of MOPs, you need to remove the water. That's why So we have to heat the sample nearly for 150 degree. And anyway, we can do other characterization techniques, for example, SCM and XPS, etc. So interestingly, we are almost reasonably 4 volts. The really cathode, just to remove the lithium from the structure, is not like discharging the switch. So, and reasonably almost like 120 or 110 is not really high. Still, there is a scope for the people to reduce the low molecular weight material. So automatically we can get the improved. So if you talk about potassium ion battery again, so you know that potassium is little bit due to mobility issues and then electrolyte. Sometimes we don't see much high capacity. Based on our experience, lithium is good, followed by sodium and followed by potassium. So I think another new compound with early in 2012 we've been done, and afterwards I think the one of the well-known group including Manthanam and some including Nobel laureate from good enough. I think they're already working on the system. I think they've extensively used this one with a different and more detailed studies. What I'm telling that is very important. At least look some new material that will be interesting for it. Although we don't claim that is very still there is a lot of opportunities as academic researcher. I think just to present and then just to do some new yeah. So these are the way you try to prepare a sample. Either you can do as chemist or simple physicist. You can try to prepare a sample using the simple equations with hydrothermal bomb, or sometimes you can use it by a simple beaker stirring. Also, you can try to prepare a sample. So typically, I told you that we have to get nearly 4 volts is reasonably good when compared to iron phosphate. Again, is interesting, and then reasonably good capacity. Still, it is nice. We need further improvement in the capacity. I think again we took phosphate and HPO3 also is possible again. So we try to the sodium, potassium. I think these are all the ions is possible to remove from the structures, and these are other things have been already done. I think the early report with our group followed by from Komaba group from Japan, they've been done with extended this work on this material. I think I'll go through again. I think some other talks also will be there in sodium, so I don't want to have time. So again, one summary is that if you compare lithium by sodium, we can get lower energy density because of the lower potential. So I have another 4 minutes, so that I'm going to quickly go through some other example. Again, if you talk about anode materials, so people are talking about graphite. Again, still graphite is champion because of the lower discharge potential. Again, if you talk about graphene alone, I don't think it will be, although we get high capacity, we don't see this type of lower potential. I think these are a little bit challenging. I think this we look for the, again, these are the various, yeah, 2 minutes, I'm going to finish, okay? So these are the various applications. I think I'm going to tell that importance, something like either new materials, either they can do a tin-based compound. There is a lot of scope, I think, depending on either you can reduce the materials in the large scale, etc. I think I'm going to one example. If we go for nano size to submicron size materials, again, we as a physicist, we can do the interesting thing. Again, there is a lot of scope. I don't want to tell more detail. Sometimes people want to look for supercapacitor. I think these are some examples. We can look into literature. So I'm going to skip the details since they've given me another 2 minutes I have. I'll skip it. Again, importance of the, if it is nano-based, some nitrate-based system, it seems to be nanoflex seems to be good when compared to the bulk and vanadium. Titanium is a little bit hard and it is not be interesting. So I'm going to quickly leave again the importance of nano is everywhere. It is not like all the materials. Still some example TaO2 also. If you talk about nano size to submicron size, again we see the importance of the capacity. And also if you talk about sensors and then. So I'm going to skip since there is a very important conference, and then I think other people are going to cover with a different synthesis. I don't need to tell all the stories. So what I'm telling that there is a lot of scope for the people in the nanotechnology at the students. I think nice opportunity for you people to utilize these opportunities, and then you can do at least you can learn something with the experts and make a good collaboration. Especially, I think good person. I can tell that Professor Ken, since he's an academic professor, I think he's able to motivate a lot of young researcher. I think so that way. I think we need this type of people, and I can tell that by my experience can help a lot of people. So I know them. He's really kind and nice to work with. These like this type of mentor, and also he's a good people. And okay, again, last word is that again the material recovery is very important. Always you to recover the materials in a proper way. And I think I'm going to skip the end. Instead of since I have almost 1 more minute, so these are my small conclusions. Again, although we climb so many materials, among them only promising materials are this one for real applications. Again, Especially for academic researcher, always there is scope for new materials to discover. And then if you talk about chemical engineers, people are looking for greener synthesis and then electrode, electrolyte, etc. I think, thank you very much. So I think I'm almost finished my things, all like 29 minutes. So thank you very much, Professor Ken. Okay. Anyway, I can talk the story so many times. I think this is more than enough. Okay. Thank you very much.
Thank you. Thank you, Professor Reddy.
Yeah, thank you.
Thank you. You recover some time for us. Thank you.
Yeah. Because it's very important, so we have to maintain the timings, and also it may not be good for you to, okay. Thank you.
Okay, bye-bye.
Yeah, bye-bye. Thank you.
Hang on, don't go anywhere. Okay. Okay, do we have Professor Manikandan? Professor Manikandan. If Professor Manikandan is not there, we go to Professor Dare. Yeah. But it's not time for Chibeze. It is Professor Dare. Is Professor Dare there? I haven't seen him. Yes, in Enoch Olubenga Dare. He's not there. He doesn't seem to be there. I can't see him either. ICT, can you see Professor Enoch Olubenga Dare? Okay, if he's not there and Professor Manikandan is not there, so we can go for Chibeze V. Amachukwu. Chibeze Amachukwu. I don't have your... Yeah?
I can. Yeah, I can share my screen.
Okay, Chibeze, sorry, where are you coming from?
From Chicago in the US.
From the US, okay.
Yes.
So, okay, thank you very much. I don't have your short CV here. Maybe you will help us by introducing yourself within 30 seconds, please. Thank you, that would be nice.
Okay, I can do that.
Very much. You can, the phone is in your court now.
Okay. So get this. Okay, good evening. It's good morning here. My name is Chibueze Amanchukwu. I'm a professor at the University of Chicago in Illinois in the US. I also have a joint appointment in the Chemical Sciences and Engineering Division at Argonne National Lab. I got to actually meet Professor Ken, I think 2 years ago at a conference in Tanzania in Arusha.
I remember.
So my talk today is focusing on controlling electrolyte molecular structure and nanoscale ion solvation effects for lithium metal batteries. So I hope there will be questions. So I don't know how easy it is to ask me questions for those that are currently present in the room there. But this is my email address, my lab website, and we also have a Twitter account that you can reach out to us through. So this is just one slide about my department. We are at the University of Chicago, so that's the picture you see on the right-hand side. So I can actually see that from my office. So it's a quite beautiful campus. You have the city of Chicago that is just behind here on the clouds here. So it's roughly a 15-minute drive to downtown Chicago. And so we are the Pritzker School of Molecular Engineering. We are interested in how can we tackle grand challenges across the world. So this could be in materials for sustainability and health. This could be in developing quantum technologies. So I'll give a quick snapshot. I left Nigeria when I was in SS1 and then moved to the US. I did my first degree at Texas A&M in chemical engineering. I went to MIT for my PhD. So I did that also in chemical engineering. I was a postdoctoral fellow at Stanford University for 2.5 years, and then started my professor career last year in January 2020. So this is my young research team. We have 4 PhD students who are currently working on several different projects within the group. We have a number of undergraduates who are also doing research with us, and a number of different funding sources that I would like to acknowledge that have supported the work that you'll be hearing about today. So Dr. Reddy just talked before me, so I won't belabor the point on why we are interested in different battery chemistries. But I think it's very exciting to emphasize how much batteries really permeate our world today. From what we are already familiar with powering portable electronics, and then the new industries that we are hoping that batteries can help displace the current technology. That would mean having batteries incorporated in vehicles, so electric vehicles, so that would displace internal combustion engines. And how can we start integrating batteries or energy storage in the power grid so that we don't have to build pipelines that carry gas from one location to another? I don't know who is writing on my screen. And then also, how can we actually incorporate energy storage within the power grid? And the reason this is quite important is it allows you to incorporate solar and wind, which are technologies that are very intermittent. Okay. And so lithium-ion batteries, so when we say batteries, there are different ways to store energy. So batteries is just one form of that. And there are different lithium-ion batteries are currently state-of-the-art. And you've seen from Dr. Reddy how important it is to work on different aspects. So you work on different anode technologies, you work on different cathodes, you work on different electrolytes. And so here the working principle is that you have an anode, for example, and you oxidize it. You have electrons that go through, and here they could power your light bulb, but we're interested in doing more than that. We're interested in powering vehicles. We're interested in powering cities and nations. So you have these electrons that go in at the cathode. So this is number 2. You have reduction that would occur. And what we are very interested in my lab is in this number 3 here, the electrolyte. So the electrolyte allows for lithium-ion transport between both electrodes. So it could be lithium-ion transport for a lithium-ion battery. It could be potassium-ion transport for a potassium-ion battery, etc. And so that's the general working principle of a battery. So within lithium-ion batteries, the framework is more specific. And so you have here, these are graphites, these are graphene layers within graphite. So that's the blue that you have seen. And you have lithium-ion transport that can go in between those layers. And so when you discharge or when you're using your phone or you're extracting energy from the battery in your phone, you have lithium ions that move from the anode to the cathode and then intercalate between both. And so the working principle of a lithium-ion battery really depends on how much of this green dots you can store within that battery. If that's the case, then I hope the question you have for me and you have for Dr. Reddy or Professor Ken, all the researchers that you hear, so how can we store more energy in these batteries? So one of the many approaches is to say, okay, so what are all these blue components here? What are all these red components here? They don't necessarily contribute to the energy density that you can extract from your battery. What really contributes is how much lithium ions you can pack in that system. And so that's what a lot of researchers around the world are driven to study. So when Dr. Reddy talked about, some lithium phosphates or some lithium vanadium oxides, or trying to extract or trying to move to silicon anodes or trying to move to tin alloys, all of these are strategies to increase the energy density that you can get from a battery. So what do we have a roadmap? There's a roadmap that has been talked about for decades now on how we can move further right here to the top right-hand corner. So how can we increase the amount of energy we can store per mass? And how can we increase the amount of energy we can store per volume? And if you look at on this, we're very familiar with how much technology has really changed. So going from phones that we might have had just 5 years ago or 6 years ago to phones that we have today. And a number of that is really enabled, a lot of this transformation is really enabled by the battery chemistry that is being used and how we've changed lithium-ion batteries even within the 30 years it's been invented. But we're interested in doing more. We want to store more energy because we want to actually start integrating batteries within electric vehicles. And how do we do that? So you can look at this. If we're trying to move to the top right-hand corner, there is something called lithium metal that allows us to replace graphite in a lithium battery and store more energy per mass and also more energy per volume. So there are many different ways to approach enhancing energy density. So energy density is related to the specific capacity of both the anode and cathode that you have and the voltage difference that is between the two electrodes. So if you want to enhance energy density by specific capacity, you look for high capacity electrodes. So on what you're looking at here is just very simple. We are comparing the specific energy in blue. And you can just, let's pick the blue. We can say, okay, this is carbon, so this is commercial graphite. This is what people currently use. But we're interested in going from graphite to lithium metal. So why are we interested in this? Because you can see this significant increase in theoretical capacity. So an order of magnitude going from roughly 372 milliamp hour per gram to 33,860 milliamp hour per gram. So that's one way you can increase the specific capacity of your electrode, or you can actually increase the voltage difference. So here is moving from, we have things like lithium iron phosphate that is currently used today, things like lithium cobalt oxide that's currently used today, but you could be interested in moving to high nickel cathode material. So this could be NMC, NCM811, or you could be interested in moving to much higher, just higher voltage, but lower capacity. So lithium cobalt phosphate, for example. So we focused on a lot on how to develop electrolytes that really allow you to do both, that allow you to use a lithium metal anode, but also allow you to use a higher voltage cathode. But there are numerous with none of the promise. It's not difficult to see, to look in the textbook and know why this is exciting. But there have been numerous challenges that have prevented us from actually using lithium metal batteries. So one of that is it's really summarized in the chart here in the far left on the different challenges that are facing lithium metal. So one is typically high reactivity. Lithium metal is a very reactive compound. It will react continuously with anything that you put in contact with it, one of which is the electrolyte. So what does this do? This leads to what is called a solid electrolyte interface that is very heterogeneous. So you have inorganic components, so something like lithium oxide. You have organic components, some polymeric compounds. You have different inorganics, so lithium fluoride, lithium oxide, lithium carbonate. So this heterogeneous interface really does control how efficient you can deposit or strip lithium from the surface. And then because lithium continuously reacts, you continuously form this solid electrolyte interface. So it keeps increasing with cycle. You might have what is called dead lithium, so lithium that is no longer electrically connected to the battery cell. And so continuous degradation and continuous loss of the electrolyte and also of the electrode will lead to cell death. Beyond that, remember the anode is just one component of a battery. You also need the cathode. And so there are lots of challenges with that too. So here, we can simplify this. So you always want your electrolyte. So you want your electrolyte to be able to be stable against oxidation. And you want your electrolyte to be stable against reduction. The window that you can operate in, so that is called the electrochemical stability window, you want that to be as wide as possible so that different redox reactions can occur within that window while your electrolyte is stable. So you have to balance all of these. So this is our challenge. And so our challenge really here is how can we develop novel electrolytes that can control the nanoscale solvation properties at the different electrode surfaces. So one, you want an electrolyte. So the goal is, can we design electrolytes that enable efficient lithium metal deposition and stripping? So that's one. Two, is it actually an electrolyte? Can it be conductive enough? Can you actually have ion transport through that electrolyte medium? And then three, can it enable higher voltage cathodes compared to the commercial electrolytes that we have today? So these are very demanding requirements for a single compound. It needs to be very stable reductively, but it needs to also be stable oxidatively. But it also needs to conduct ions back and forth. And so this is a lot of the challenges that we are very excited to work on and develop new ideas on. So this is our approach. How can we do this? So one is, you can start with a molecular structure. So I will motivate why we chose this molecular structure. But then it's not only enough to have a new molecule. You really have to control what is happening at that interface within the lithium metal anode or your cathode and the electrolyte. And so this is where controlling ion solvation, which are nanoscale effects that you're trying to control. And then how can you combine knowledge of molecular structure, knowledge of ion solvation structure to improve performance? So can you actually go across these very, very wide length scales? So going from something in the nanoscale in terms of ion solvation structure to going to something that is bulk. So bulk could be ion conductivity. How do you actually have ion transport across the entire electrode surface? And also, how does it actually affect the battery cycling? And we can go backwards too. So if I know that I want to improve performance, how can I actually change the molecular structure and the ion solvation? So this is the motivation for working on fluorinated compounds. So one is, it is known that fluorinating compounds significantly increases oxidative stability. So we can take a normal ether here. If you fluorinate, here you can fluorinate the ends of both of them. And you can see you can increase the oxidative stability by just under 2 volts, which is it's a very massive change. And so this gives us a platform to work on. So we are going to start with compounds that we already know can give us high oxidative stability. But now, can we get the other part? Can we get ion conduction? So this compound that I have on this slide does not conduct any ions. Can we get ion conduction? And can we get improved cycling on the lithium metal surface? Remember, the goal is understand the molecular structure, nanoscale interactions at the electrolyte interface to enable lithium metal batteries. Okay, so there's been recent success. So in my past work, we've been able to work on a new class of electrolytes that were able to kind of put us on the right step towards accomplishing these. And so here you see that in current conventional lithium metal batteries, ethers are the electrolytes of choice. So they're very good in ion conduction. So that means they can work with, they're good electrolytes. They're actually quite good with the lithium metal surface. They enable high efficient lithium metal deposition and stripping, but they are very poor on the cathode. So I told you I'm motivated that we love working on fluorinated compounds. So, but fluorinated compounds actually, in the ones that are currently used in the literature, do not support any ion conduction, but they are great oxidatively, so they can be used in high voltage cathode systems. If I asked you what's a possible approach, you could probably say we can mix them, and that's a good approach, but it doesn't actually solve our problem, because if you simply mix, let's call this A, let's call this B. If you simply mix A and B, you will still have these compounds finding themselves at the interface and still degrading. And so what we've been interested in my lab, and it's also designing new molecules, new solvents that can dissolve salts. So they're actually ionically conductive. So you can imagine the end groups here support ion conduction. But then the middle part enables high oxidative stability. And so these are the kind of class of compounds that we've been very interested in studying and really probing what is it about the molecular structure that's important? How does it control ion solvation, etc. So this is the first kind of preliminary work that was done. and then my student has taken it much further. And so here we're trying to take a step back and thinking of these as building blocks. So if you had Legos, for example, and you're mixing and matching different properties that you want. And so we can go from left to right. If I had two blocks, for example, so a block that is in blue that gives me ion conduction, and a block in red that gives me oxidative stability. How do you attach these? And is the attachment, does it actually control any relevant properties of interest? And so here, this is the previous work I just talked about in the past slide. You will see that in the building blocks, we had all the oxidative components in the center, while the ionic conductive components were the end groups. Same thing that has also been done in the previous work. So in this work, what we did was, if you flip the building block connectivity, so now in the middle, you have all your ionically conductive components, but in the end groups, you have your fluorinated components of oxidative stability. How does it actually change the ion conductivity properties? How does it change electrochemical stability? How does it affect lithium metal battery cycling? So this is what I would focus the remainder of the talk on, and really understanding this new class of electrolytes and how do they actually influence battery cycling behavior. So this is now we're putting some molecular structure on these, so not just schematics. And so with this now we synthesized actually eight compounds, where I'll give you the naming nomenclature, so I don't want to lose you for the rest of the talk. So when you see a compound like this, we call it E3F1. So what that means is we have 3 oxygens. So that's the 3 part here. And then the E is just an ether. And then the F1 means we just have a CF3 group, as compared to an F2 compound that has 2 carbon containing fluorine groups. And so if you see the E3, E4, E5, E6, that means we are just increasing the length of the ether units. And then the F1 means we are still keeping a CF3 group as the end group. And then same thing here also. So what we're interested in is, now we have a set of molecules that allow us to do molecular property relationships. So how does changing the molecular size, how does changing the ether length, the end group, how does that affect relevant electrolyte and battery properties? So the first thing anybody should show you when they work on electrolytes is conductivity. Is it actually an electrolyte? Can it conduct ions? And so what we've been able to do is study these, and they all are a good electrolytes, so roughly 30 C. You can see that they are roughly at a 1 millisiemens per centimeter. So that's actually quite high for these electrolytes. And one thing is, if you increase the end group, so from a CF3 to a CF2, CF3, you get punished in terms of ion conductivity. So ion conductivity does reduce when you go to when you increase the fluorinated length. Okay, so this the figure on the far right summarizes our observations in terms of the effect on conductivity. And so here we are showing that as you reduce the weight fraction of fluorine, so going from right to left, as you reduce the weight fraction of fluorine, you tend to see an increase in ion conductivity at multiple temperatures. So these are at 80 C, you see an increase in ion conductivity, as well as also at 30 C. So now we know they are conductive. So now we're interested in studying how stable they are oxidatively. So these experiments are done quite simply. You have a lithium metal electrode as your anode here in excess. You have your electrolyte in the middle, and then you have an inert electrode. So yeah, it could be stainless steel, for example. And you're trying to see at what voltage. So this is called a linear sweep voltammogram. And how you interpret it is saying, at what voltage, so you're looking at the x-axis here, which you are in control of, at what voltage do you see current rise happening? And so based on that, we can pick an arbitrary number of current density. So here we pick 0.01, and we can draw a straight line, and we can say, okay, what voltage do we see the curve hit that current density. And so then we can extract and say, okay, well, this is the control. It degrades at roughly 4.3 volts, which is already known. So all of these new compounds have much higher oxidative stability compared to the control. So that's good. But the trend is unusual. So what we see is that the oxidative stability increases with molecular size, which was very shocking to us because we are increasing the fraction of the weaker components, but the oxidative stability was increasing. And so we spent a lot of time trying to understand why this is. So this is a summary of our work plus work in the literature. And this is the part that took us months to really try and understand and explain why this was occurring. So what you look at here is that as you go from left to right, you're increasing the weight fraction of fluorine in the molecule. And in previous work in literature, you see that the oxidative stability increases. So this is known, this is expected. In another previous work in the literature, you see that it increases as a weight fraction of fluorine. In another work in the literature, it increases. But in our class of families, it decreases, opposite. So we had never seen a phenomenon like this before. So we spent a good amount of time trying to understand why was it that as you increase the weight fraction of fluorine, so there's more fluorine in here, the oxidative stability of these fluorinated ethers actually were worse than expected. This is also opposite to what you would predict using first principles calculation. So my student was also able to do density functional theory calculations. So I'll draw a line here in the middle. When you look at it, I want you to focus on the orange bar graphs for now. So as you increase, the fluorine concentration, for example, or as you decrease the fluorine concentration. So if you decrease the fluorine concentration, you see that the oxidative stability goes worse if you use first principles DFT calculations. And the same thing again here. But if you look at the blue now, so if you focus on the blue bar graph, you see the opposite is the case with experiments. That you reduce the fluorine content, as you decrease the fluorine content, the oxidative stability actually increases. Why? This is where really understanding how molecular structure affects nanoscale ion solvation is very, very, very important. And so what we've been able to do was here do Raman spectroscopy. And in figure A, we are looking at the anion. And figure B, we're looking at the molecule itself. So figure A, you can see that the nanoscale ion solvation structure is actually quite different as you go from, if you look at this. So if I go from bottom to top, I am increasing the fluorine ratio, the fluorine weight content. You can see as I increase the fluorine weight content, I start seeing significant ion aggregates that form between the lithium and the anion. So which is known because the more you fluorinate these molecules or the higher the fluorine weight fraction, the worse their chelating ability to lithium. But what you also see on the right is that because the lithium ions and the anions are in ion pairs here, there is a lot more free solvent available here, because that solvent is actually not participating in ion solvation. So that has a profound effect on the electrochemical stability. So now we're showing a different plot. We're rounding up quickly. Yes.
5 minutes.
Yes, yeah. So I have like 2 more slides and we'll be done.
Yeah.
3 more slides.
Yeah. 3 here. People have not had lunch.
I can see some of them eating already. So some of them have. So I'll try to be as fast as I can.
The child will not eat. You know, I'm not gonna eat.
I try. If you started eating, I will stop sharing then. So. So this just really summarizes what I've been spent some time talking about. So as you increase the fraction of free solvents, so going from left to right, you see that the oxidative stability decreases. So even for the same molecules or the same molecular structure. And so the summary was that the larger the molecules that we had better ion solvation. So there was less ion pairing, but that led to less free solvents that was available and increased oxidative stability. This is in contrast to what has been seen in the literature before. In the literature, the only really way to do this is to increase salt concentration. And if you increase salt concentration going from red here to blue, you increase oxidative stability because you allow all your solvents to participate in ion solvation and decrease the free solvent amount. But what we've been able to show that we can actually see that in just for the same concentration across different molecules, and you can also modulate the amount of free solvent, and actually that also modulates the oxidative stability. And so these actually have impacts on long-term cycling. So we've been able to show that we can actually cycle lithium metal batteries. Here we're using LFP cathode, for example. And then what you're looking at in the top is just lithium half cells. I show that we can actually cycle them reproducibly over hundreds of hours. And this is the second to last slide that summarizes the work today. So what we've been able to show is that this is not increasing salt concentration. So we have different molecules here, not necessarily taking one molecule and increasing salt concentration. Is that if you increase the amount of ion pairing in these, you decrease the overpotentials, which is good for lithium metal deposition, and increase the cycle life. So this is quite profound. Just by changing the molecular structure, we change ion solvation or ion pairing interactions, and that has significant impacts on actually the battery cell. So our ends, our contributions are really designing fluorinated electrolytes that can combine high conductivity with high electrochemical stability. We're able to show that building block connectivity for these compounds are quite important. Ion solvation structure plays a pivotal role even across different molecular structures, but the combination of understanding molecular structure plus ion solvation can really significantly extend lithium metal cycle life. And so this is kind of our research vision. This is the last slide I will show to everyone. So we're doing more than just what I talked about. So I told you about this middle part on how we are synthesizing new electrolytes, but we go across a lot of different approaches here. So using data science and machine learning to generate new electrolyte ideas. We make new electrolytes within my lab. We're also able to characterize using many different tools, the electrolyte interface, and then we also incorporate them within batteries and also electrocatalytic systems to improve long-term cycling. So with that, I will stop sharing.
Okay, thank you, Chibeze. Please, a round of applause for him. Thank you very much. Chibeze, thank you.
Yes, thank you.
We're going to take just one presentation before we go for proper lunch. When we come back, Damian Onwudiwe will present. Kinsley Onyebuchi Obodo will present if they are here. Mesfin Kebede, if he's here. Usama Mutanabir will present. And then if Professor Dare is here, then he can present. If Professor Manikandan and Professor Balus Brahmania. See, I'm hungry now. So if they are here, they will present after lunch. But for now, we would want to give the floor to Dr. Ifeanyi Ochonogo. Doctor, are you there? We know him very well. He was here yesterday. He talked about e-waste briefly, and the big people shut him down before he could finish. So today we're going to pay him back because he's our good supporter for this conference. He supports us very well, morally and otherwise. Is Ifeanyi Ochonogo here? If he's not here, where is he? IT, please help us check if Dr. Ifan Ochonogo is here so that he can present. If not, this will be the best time to go for lunch, and then we come back after. Yes, after 30 minutes lunch, we're going to have a rushed lunch. Okay, it doesn't seem to be here. So I think we should go for lunch now. We will start again in, can we say 45 minutes time? Yeah, okay, 30 minutes, 40 minutes, yes. Yes, we'll start at 4 o'clock Nigerian time. Yes, when we, no, we'll manage that. Yeah, so we will come back at 4 o'clock. We'll start exactly at 4 o'clock Nigerian time. We will allow somebody to take for 30 minutes, and then our friend from Canada would want to start at exactly 4:30. So thank you. Enjoy your lunch. Somebody lost his fancy Samsung phone here. Very fancy Samsung. Please, if you're looking for a Samsung, or if you know anyone who's looking for his or her Samsung, the person should come and take it. It's quite beautiful. If you come here without your identification card, oh, something, what I would do, you must come with a proper identification. You may even tell when you bought it. Okay. Prof, should I leave it with you? Okay, good afternoon, guys. Welcome back from lunch. Okay, we're all right. So we have to go for the next, the final session for today. Before we went on break, we had invited Dr. Ifeanyi Ochonogo, and we said so many beautiful things about him, but he wasn't here. Is he here now? Is Dr. Ifeanyi Ochonogo here?
Yes, I'm here. I've unmuted myself. Can you hear me?
Yes, I can hear you. Thank you, Doctor. We had wanted you to present before we went on lunch, but we didn't hear from you. Actually, somebody would want to present now from Canada. He actually fixed this time for him. I'm not sure how we're gonna do that.
Wow.
Would you mind?
Oh,
Okay.
I don't mind. I don't mind, to be honest. He came. Go ahead, sorry.
Okay, please. Somebody from Canada said he would want to join at exactly our 4:30, and it's exactly 4:30. But let me ask, if he's not there, is Usama Mutanabir here? He's not there. Okay, that's good. Thank you very much. Thank you, Professor Ezema. He's not here. Okay, Dr. Ifeanyi Ochonogo, I was saying that everybody knows you already. You were here yesterday, but the big people didn't allow you to complete your presentation. So that was why. So today we want to compensate you to complete it because you are a friend of this conference. You have been very generous. You support us both moral and otherwise, according to Nigerian English. So thank you so much. So we would want you to go ahead and present, but if you can help us, would you please keep it for 30 minutes? If you don't mind, we will appreciate that, sir. Is that okay?
Well, I will fast track it. I will fast track it as much as I can, I promise.
Please, please, if you don't mind, sorry, I'm just, I'm pleading with you. Sorry, okay. So the floor is yours now. Thank you, sir.
Okay, good afternoon, everyone, or good evening almost. My name is Dr. Ifeanyi Ochonogo, as our host, our honorable host just said. I'm the electronic waste recycling gentleman that was partially introduced yesterday. As I said, I brought solution provision for the electronic waste crisis and also the wealth generation aspect of an electronic waste industry. I helped to define it for Nigeria and extension West Africa, because ECOWAS is looking up to us to lead the way. So as was previously mentioned, I have to go as fast as I can, and I would like to go straight into my presentation. If I can just look at sharing the screen. I think that's it. Control share. Okay. Is everybody seeing my slideshow or from beginning? Is the slideshow viewable? Hello, is anyone talking? And then the slideshow, is it showing? Is it only showing for me or showing for everyone?
So you are, yes, we can see you. We can see your
okay,
also your face. Yeah.
Okay, you can see the two of them, so that's good. Yes, so eTerra Technologies Limited is, as it says on the tin, it's currently Nigeria's leading electronic waste recycler and data destruction expert. We've brought not only electronic waste recycling, but we've defined and brought data destruction. That's the permanent destruction of electronic waste. Now, when it comes to waste, I mean, nanotechnology and all of the the other developments. I mean, it's a fantastic thing. But one thing that scares me is that we have not finished dealing with the crisis that is befalling us. So I am very, very happy. I can't tell you how happy I am that Professor Eze called me and asked me to come over to this so that we're all carrying along the whole ship, not leaving the disposal and recycling alone, because disposal and recycling, by the end of this this presentation, hopefully you will understand how damaging it is and how it's hitting us hard in the health region, and all whatnot. You'll be hopefully will be positively enlightened going forward. So carrying on. So I start off with this picture. It says, according to the US EPA, 530 pounds of fossil fuels, 48 pounds of chemicals, and 1.5 tons of water is required to manufacture only one of your computers. Just one of your computers, the amount of resources that one uses. Imagine the amount of nanoparticles and all whatnot. It's amazing. I mean, when I think about the nanotechnological sphere, I mean, correct me, forgive me, but I just say we're bringing a problem and turning it into a nano problem. It's going to be to the billionth level if we don't deal with the situation now. And again, I thank the conveners of this event for bringing me on board and taking it seriously. Says basically we're living on this planet as if we have another one to go to, and I don't think anybody has tickets to Mars or any other planet. So the challenge that's befalling us, the reason for the bad news, if I could briefly introduce electronic waste. So electrical and electronic equipment, such as all the computers, fans, fridges, phones, have significantly improved our lives, but unfortunately, when they become obsolete, where do they go? Where have all the old computers and phones that you've ever used in your life gone? Where, even was thinking, where are the old batteries, the batteries that we use as children, where have they gone? Because there is not one single battery recycling or refining organization, even today. There's no battery plant, even in many developed countries. So you can see how serious the issue is just by basic definition. So e-waste is an acronym of electronic waste. Two major challenges emerge from e-waste when electronic and electric devices reach their end of life or become unwanted. How to dispose of them, as I mentioned before, and how to protect what? Your confidential data, because all your life, all your bank details, your life details, your school, the school of yourself or your brothers and sisters, your children are all online now. It's not like paper anymore. So according to the United Nations Development Organization, about 1.1 million tons of e-waste is generated in Nigeria annually. And that's actually an up-to-date fact to me, because it must be approximately 1.5 or 1.4 tons today. Most end up with unprofessionals, which are the informal sector. So that's the opposite of e-terror technologies. Hence, dangerous toxic material handling, dumping, burying, burning of e-waste to extract precious metals. If anybody knows about Computer Village, if you know about Alaba International, then you'll have heard of some of these things. Large-scale landfill disposal and incineration, confidential data theft from computer scavenging, lastly, because that is an issue that I'm going to dwell upon later. Now, the life cycle of all forms of electronics, including nanotechnology, electronics that a lot of people are swooning over in developed nations, and we are beginning to look towards, which is good. It's good to look to the future, but we have to look at where we're coming from at the same time. You look at the diagram, simplifying it for time purposes. Material processing. This material processing is what happens in developed nations mostly. I mean, I do know that we have some OEMs here, but they're few. High intensity, high resource consumption, occupational exposure. That's occupational health and safety standards in long form. So high energy consumption, again, occupational exposure, that's in the manufacturing stage. In the usage, this is where the exposure to humans and the environment. I mean, even while we're using the devices that we're talking about, I mean, some people will have heard of the batteries that have exploded in the hands of people. You might not have heard actually of the implications of heat, of keeping your electronic device in a heated area. All of these things are what cut minutes, if not hours away from one's life. But it can be more worse than that. That's a simplified, the most gentle example that I'm giving you. Then finally, the end of life, the difficult to recycle, non-biodegradable and possible toxic releases to air, water, and land. Human health impacts. Now, those are implications of all forms of e-waste. Now we have to look at where exactly the 1.1 million tons or 1.1 million plus tons of electronic waste that surrounds us is coming from. It's coming from us ourselves, but majorly also is coming from abroad. Okay, as you see the diagram over here, you see the major producers of electronics, Japan, South Korea, the European Union, United States, Australia, some of whom, or most of whom, have signed decrees and conventions that they're not going to export electronic waste to developing nations or less developed nations, whichever one you choose. It's very, very hard to hold down, apparently. And United States, for example, said no, flat out, that they're not going to stop their citizens from dumping electronic waste on us. But obviously that is something that's a discussion for another day. But what we are looking at, what I looked at as a CEO, as the person who created the company, was just an answer to this kind of thing and to our lack of knowledge of what is going on. So speaking of knowledge of what is going on, here are some alarming pictures of improper e-waste handling and disposal in Nigeria. In case you don't know, this is what happens wholesale across the country. They say now that cancer is now like the common cold. I don't want to say it out loud, but I have a very close person of mine that actually has caught cancer, and she does not smoke or anything. So, and she does not live anywhere even near any of these things. But she and one other person that's not close to me, I know 2 people have caught cancer. So, and I'm hearing that there's a cancer epidemic, and we have actually gone to the authorities in Yaba, to be precise, and they said that it's increasing. It's increasing sporadically. It's increasing terribly. I mean, in 2015, our yearly cancer rates were 200,000 fresh cancer cases a year. As of 2018, that number had doubled, and by now it's probably tripled or approached triple. So it's a very big issue. So for your knowledge, some known toxic elements inside computers, printed circuit boards, as you know, are required to make it work. Lead and cadmium, lead oxide and cadmium is there in CRTs, which is one of the treatments that my company actually chose to go into, even though it doesn't generate that much revenue. It's a sacrificial and a human investment to actually say we need to deal with this crisis as well as generate wealth, because that's what electronic waste recycling is all about. I mean, there's another classification for it. It's called urban mining. It's your kind of mining and acquiring all of the good parts of the waste, the gold, the silver, the palladium, and all the different. Let's say palladium. I'm thinking of another another one. But anyway, I'll stop at gold, silver, copper, etc. But unfortunately, all of those are glued or soldered to very, very toxic components like gold, brominated, plastic, brominated flame retardants, etc., etc. So swiftly moving on, these are the damages that are caused by improper electronic waste, recycling or handling or treatment. But even though you're not doing any of that, we are all breathing the same air, and whether or not we know it, some of these things might be the reason why we are having bad health. This is what for example, dioxins damage the immune, nervous, endocrine, and reproductive systems. I'm going to rush on. I can send this over to the convenience of this event, and so that we can spread it around, because the knowledge and awareness creation is very, very key for us to understand and take this seriously. Because to be honest, the target of the company of eTerra Technologies is actually you, and also the future, the youth, because we're really, really strong about teaching schools and universities like the ones that we are, but then even younger than that, the primary schools and secondary schools, the children, for them to really, really see the issue and to be raised with knowledge of the issue. So onward, the environmental impact of e-waste. Okay, it affects everything. You know, groundwater contamination, landfill, runoff, seepage. It's all, you can see it's as clear as it is on the tin. Groundwater contamination from a waste disposal site, as you see in the diagram. So in short, air pollution, groundwater contamination, food pollution as plausible radicals in the human body, nationwide ecological pollution. Now, the nanotechnology aspect, I count nanotechnology as part of, I mean, it is technology, it's the same electronic waste issue. If it becomes minute, it becomes nano. I mean, if you grind electronic waste down into nanoparticles, for example, in your process lines, which I'm going to discuss very briefly and as fast as I can with you, then it can bring benefits. Yes, it can definitely bring benefits. But yes, it can also bring issues, because a lot of these things are I mean, obviously nanoparticles, they can be very, very poisonous. They can be beneficial. So it has to be dealt with very, very carefully. So nanotechnology and nanoscale materials promise a great deal of societal benefits, as I've said, but also threaten the health and privacy of the individual. Toxic effects produced by nanoparticles have been recognized for pulmonary, reproductive, digestive, cardiac, cutaneous, and immune levels. So it's basically the same issues that diagram of the lady that I just showed you shows similar issues. So nanomaterial can cause air, water, and importantly, a sole persistent form of pollution, just like usual, which is too small to be detected unusually easily, making nanopollution another man-made unwanted environmental impact with uncertain effects in the long term. And this is all while what? While we don't even have an industry, a solid industry to defend ourselves. So you can understand my worry. Larger and multi-center source studies are needed to determine the human reactivity before large-scale nanotechnology is settled. So please forgive me for saying this. I know that something new is good, and we must always perform strong research, and we are performing strong research and progress, but we must look to what we have left behind in our past or our present. If we cannot, we need to open our eyes. So sorry to solutions. This is where we're going. We're not going to give all the bad news all the time. We have, as I said, eTerra Technologies is what I created, and an offshoot of eTerra Technologies, because of the scope of the issue, is a major part of it is awareness creation and support for government. I mean, we're talking of support to the federal government, their arms, government parastatals like NESRIA, Federal Ministry of Environment, NESRIA. We have state ministries, La CEPA. So these are all, we acquire permits from them, but we work with them as well. So wherever they need awareness creation, whenever they need anything, then eTerra is there. And we dedicated, the first ever foundation dedicated to the electronic waste crisis is also there. And the chairman of that is the leading chemical, oh gosh, how am I going to put it? the top chemical, what's classification? The top chemist. I'm not going to say, but he's a top man I don't know if you recall, if you've heard of Professor Olodele Osibanjo. He have taken his advice from the start, from 2013, when I wanted to tackle this problem. And he's the chairman of the E-Waste Relief Foundation. And I thank God that he accepted it and is part of this battle that we're fighting. So eTerra Technologies is Nigeria's leading world-class electronic waste recycling company and data destruction experts. Our vision is to be the leading eco-friendly and profitable e-waste management company in West Africa, commencing in Lagos. We are registered with all federal and state ministries. In short, we have 3 ISO certifications. Just to tell you the magnitude of the issues that we're faced with when I was looking at starting this. I mean, quality of service, that's not ISO 9001, but critically, ISO 14001 and Occupational Health and Safety Assessment Series, that's OSAS 18001, is very, very important. So while we're doing what we're doing, we can't be like the informal handlers and everyone else who are trying to make money for their families, but then poisoning themselves and the environment and their loved ones at the same time. So with this ISO certifications, we can never be guilty of that, because we're assessing ourselves and we're internationally assessed at the same time. Yes, it costs money, but it's worth it. eTerra actively engages in community e-waste education, detoxification, and corporate social responsibility initiatives through a sister charity, as I've mentioned before, E-Waste Relief Foundation, the ERF. You see the logo on the right of LASEPA, Lagos State Environmental Protection Agency. So, yes. So just really quickly, our service offerings, e-waste evacuation and eco-friendly disposal. We have data degaussing and destruction service. This is the actual hardware. I mean, you have hard drives for a reason. It's very, very tough to destroy the information within hard drives. This is what we said to Defense Headquarters. Right now, our mobile data destruction truck, which is a mobile plant, is in Abuja, about to perform a proof of concept demonstration, which it has already done for nearly all federal ministries, okay, to show them and finalize what's data destruction, so that the awareness creation for data destruction is well known, so that we can be protected. We can be protected from losing our livelihood, our money through the banks. We can be protected from losing our lives, because even our defense headquarters, they need to protect the secrets of their strategies, which is what data destruction does. Because all people need to do is get an old computer or laptop, and all your secrets are on there. So and this is what has been happening all over the world, And there are so many examples for it, but I don't have the time to tell you. I used to say it in all of my presentations, but like I said, I was given 30 minutes. So let me press on, take my word for it. Refurbishing of near end of life gadgets for reuse by organizations. That is to keep the electronic device, the dead or dying electronic device, out of the landfill, to turn it back into a valuable device, so that companies or charities or churches or mosques or anyone can give it to their followers, to their people, as a corporate social responsibility if you're a business. So this is what the refurbishing sector of the company does. IT asset decommissioning is when we allow companies or people to be lazy, or to say that we will send our team over to you to actually organize the whole pickup arrangement to take the electronic waste away from your site. Now, e-waste export supports, because as long as you are performing, whether it's nanotechnology or, a nanotechnology is electronic waste anyway, it's still electronic. So if you're going to perform exports, you're going to need to have a lot of certifications, a lot. So you're going to need to at least have a transboundary Basel certificate, permits. And that is very tough to get. You're going to need that transboundary Basel permit. It brings on board all it brings on board state and federal state and federal government agencies, as well as international government agencies, United Nations, to be precise, UNEP. So we are bringing, what we're trying to do, our strategy is this. We want to say, okay, we will help you export instead of allowing all informal or semi-formal people who know about this industry or this business and want to just perform exportation, which is allowing people continue to poison themselves while they get rich and poison they themselves, the people who are getting rich as well. So it's really sad. But this is our answer to it. So we want to actually say, okay, we will help you. You can use our permits and you can get on with whatever you need to do. But also because the government is getting far more serious about the electronic waste industry and the problems that it's causing, it's very good to jump on the right boat, because like I said many times, we've had to make a lot of moves to help to formalize the industry and to support government agencies to say, okay, this is the right way, you know it, and we are the right kind of company that's supposed to be able to do it, the private sector in particular. So special project, partnering with local and state governments and corporations to implement e-waste management programs within host communities to create green employment and reduce poverty. Perfect, that's what I was saying previously. So the benefits are reduced vulnerability. I'm not going to read it all out. Reduced vulnerability from old and obsolete and decommissioned IT equipment, achievement of organizational business sustainability goals, avoidance of health crisis. This is very important. Lower business costs, good corporate image, enhanced brand equity, and increased patronage for companies. Access to affordable recycled electronic devices as well, so that yes, everybody still gets what they want. So it's a win-win-win for everybody. And I hope this is what we're going to be able to achieve with when nanotechnology really starts catching on, because it's as I've said, it's a stronger issue. When the smaller it gets and the more minute it gets, it's the harder it gets, and it's already very hard. So this is what we look like. This is our facility. This is in Lagos, in Abuladom. MRRF stands for Material Recycling and Refurbishing Facility. So the first machine, as I told you, is a CRT machine that performs CRT treatment. And as I've said, the offsite data destruction. Okay, perhaps I didn't say this, which is the sensitivity of bringing all of your confidential data to out of, for example, CBN. Nobody will want that to fall into the wrong hands. So that's why within developed nations they have offsite destruction, and even better than that, they have a mobile plant. It's on-site mobile data destruction. So we actually, within this truck, you can drive it over to wherever the property is, for example, wherever your headquarters are, in order to permanently destroy the hard drives and SIM cards, ATM cards, whichever kind of confidential data storage device there is. So moving on. Yet again, if I told you about bulb, the CFL compact fluorescent lamp light bulbs through India, China, and numerous other countries, they are aware that CFLs contain this thing that everybody your learned fellows here would know about, is mercury. Now, mercury is obviously is carcinogenic and is very toxic. So while the compact fluorescent lamps are on, they are emitting mercury vapors into our bodies, man, woman, and child. Now, when the compact fluorescent lamps are not usable anymore, where do they go? We are trying to encourage that they go to an electronic waste recycling, a certified, reviewed electronic waste recycling company. And this is building, thankfully. And also the producers of these light bulbs and electronic devices, sorry, I didn't mention them, because the producers are very, very important. On that diagram that you saw previously, it's quite a long time ago, but the diagram, the manufacturers are there. So the manufacturers have to actually take responsibility. That's why it's called the Extended Producer Responsibility Scheme. In fact, yours truly, I'm actually part of the Extended Producer Responsibility Organization of Nigeria. I'm the chair of the awareness creation sector of that, to actually say, please, Dell, HP, whichever there is, whichever kind of producer, please, you have to do what is done in developed nations as well. You have to pay electronic waste recyclers, and you have to help us create awareness and build understanding for our mass of or your mass of consumers, so that it's a win-win for everyone. As I said, the cable shredder, as it shows, that's a cable shredder. Now the issue, the need for this is that a lot of the millions of informal handlers, they know that copper is quality. I mean, copper is valuable. So what they would do, they would just burn the wire, the lots of cables they have. They're going to just burn it, and this machine is an example to them, and it's actually servicing their interest as well. It's an automatic stripper and shredder. This is what official formal electronic waste recycling organizations do. Okay, so our waste recycling methodology, very, very quickly. E-waste undergoes eco-friendly component recovery and parts harvesting. Dismantled components like aluminum, plastic, iron, copper, including shredded crossbolts and shredded paper from data destruction services, are sent to local and international value chain partners, because not one company can do everything. You have to be part of in fact, the global cradle to grave waste management philosophers. You have to be part of the loop. You have to be a responsible part of the global loop, and that's what we are. We have numerous partners all over in Nigeria, in West Africa, and especially all over the world as well, that will perform whatever it is that we ask them to in a responsible fashion. Okay, so I think I can skip this because I'm trying to go fast. So this is what operations looks like. On the left-hand side, you have the recycling. I mean, first it's collection, sort and gather, and evaluation. Then we decide whether it goes to recycling or refurbishing. Refurbishing, it goes back into the marketing, assuming it's successful. Whatever components or computers or whatever it is turned back to new, and it goes back in. If it's totally dead, then it goes into recycling, and that's where it goes into goes back to the resources. It goes to the refineries, the electronic waste refineries. Now, eTerra is not a downstream operator. This is recycling. The actual refining element of recycling is a downstream sector. That's when really the nanotechnology comes in very strong. So it comes down to which kind of treatment is best. For me, I don't like the pyrometallurgical process. Sorry, it's a mouthful, and I'm trying to go fast. So the pyrometallurgical process is not for me, and it's an old-fashioned way of doing things, because you burn off a lot of the well, not a lot, but you burn off some of the material, some of the resource that you're trying to recover. So it's a no-brainer. So leaching, the hydrometallurgical process was the next step for that. So I was actually looking into that, but lo and behold, because of this event and this the information that was passed on to me a couple of months ago, I can see that there's nanotechnology is getting nano processes are getting in as well. So, but obviously with nano processes, you have to be extra careful with occupational health and safety of the staff that are operating those machines, because nanoparticles are very, very, very minute, and we're dealing with very, very dangerous material in electronic waste. So this is what eTerra looks like. We are always, as I'm saying, dangerous material. So we deal with dangerous material. Personal protective equipment must be worn all the time. Hazards of concern include task, risk, work area. A work plan must be predetermined before commencing on e-waste evacuation. Everything is monitored domestically and internationally, so we are the real deal. use of adequate transportation assets for electrical and electronic products. That's us. So just so, because many people don't know that we are actually, it's actually true. They say, oh yes, this is just a PowerPoint presentation. So I'm used to, I have to show, put in the pictures of of the company doing their job, as I've mentioned. These are some of the corporate beneficiaries, the clients that we have been able to attract, to service, to deliver our services to. And thankfully, it's slowly growing because obviously these are very hard times, and no company, hardly any company will want to spend money on their health. How to spend money on recycling, excuse me, let me be serious. Recycling had not, as of 5 years or 6 years ago, what was not ever in the finance department, in the books of some organization, of a lot of organizations. But thankfully, because of the work of governments all over the world, of determined CEOs as well, yes, it's catching on stronger and stronger. So going forward, societal engagement, like I said, just really quickly breezing through this. Grassroots enlightenment. So you as you are listening to, I'm silently angry that I wasn't able to catch more people, far more people onto this presentation, but it's okay. It was still, the news will spread one way or another. So we conduct grassroots enlightenment and community detoxification, micro and small businesses on the dangers of improper storage, handling, and disposal of scrap electronic devices, as I've told you in this presentation. ERF, e-waste relief, and encourages society to bring out their unwanted electronic devices for immediate cash incentives. So we are in the state-of-the-art site, the state-of-the-art facility that we built, but we're also in the streets. We try to be in the streets as much as possible to talk to people and let them understand things. There I am there talking to the two children. E-waste release, recycling, education. Yes, we've also sent proposals to the Ministry of Education. We sent proposals for electronic waste recycling to actually be included into the national curriculum, the study of it. And yes, it's slowly being embraced. It's slowly being embraced, but we hope it gets faster. I mean, we do have a science section already, so I hope that we can be carried along with nanotechnology. So this is us in the streets some more. I think I'm gonna rush through this. The Lagos e-waste handlers capacity enhancement program in 2018 was the first step that we took to actually start teaching, along with state and federal governments, and Professor Sibanjo is there. So all the key players are there. And the most key players are the informal handlers themselves, so that they are turned into scientists. They get knowledge of the basic knowledge. They're not going to be turned into people on your level, but they're not going to be turned into professors, but they will at least know the implications of what they're doing. They will know the toxicity of what they're doing. They will know that the people that they're trying to make money from, they should not poison them as well as poison themselves, but majorly not poison the people at home. Because we've had so many, I don't have time to really talk about the kind of things that we talk to them about. Because, for example, young girls are seeing their period at age 9, at 9 years old. You know, because there's a lot of pollution in the air, and it's obviously not stopping. So. Yes, this is the next one. I think we did in 2020 and 2019, and that was 2019. So let me quickly go, and that's us teaching as usual. I do that too. So achievements. Oh gosh, I wanted to leave this out, but recorded the following modest achievements to date: collected and recycled 170 tons of electronic waste, thereby diverting waste from landfills and open air burning. That's good. Operations, adopt dry processes. Thank you. I should have mentioned this before, because the wet processes are one thing, which is the next level of what I wanted to do. But since since technology might overtake my decision, perhaps I'm going to leapfrog over wet processes and go into nano processes. But our operations adopt dry processes, avoiding emission of over 290 metric tons of CO2 into the environment, thereby contributing our quota towards reducing Nigeria's existing e-waste pollution and health crisis. So e-waste sensitization visits to over 254 businesses and to local communities. 44 companies are engaging us. You saw some of their pictures there. Conveyed Nigeria's first major, I would say the first major e-waste recycling exposition where we actually showed what e-waste recycling machines look like. Organized basic HSC training for informal e-waste handlers, which you've seen pictures of. Acquired hectares of land at the Korodu-Shagamu industrial area for proposed Nigeria's refinery, toner cartridge, battery, and HVAC recycling. That's fridges and ACs, which is like, that's actually one power that has surpassed, as impressive, I suppose, as broad as what ITER is trying to do. We have not reached that AC and fridge segment. It's highly capital intensive and it's very, very tough to do. But hopefully we'll get there. So the last slide, I think, in recognition of ITER's contribution, we've won these awards: Green Hour Award for Environmental Sustainability, Lagos Green Award for Innovation, Sustainability Award, e-waste category 2018. We've been winning awards up to this year, Innovation and Excellence Award, Corporate Live Wire. So yes, we are being recognized for what we do, thankfully, even though the informal sector is trying to cloak or act like you'll be faced with lots of people who actually are acting like they have what it takes to do what is necessary to the level of us that are sitting here. I mean, with the knowledge that we have, we need to actually understand that, yes, the battles are being fought, and hopefully you can join us to prevent the worsening environmental and health hazards caused by the improper disposal of e-waste in Nigeria, especially the future of nanotechnology. Please, let's stay on board and stay on top of things. So for more information, please visit itera.com.ng or ewasterelief.org. We're there, so you can see more about what we're doing. Thank you very much, ladies and gentlemen.
This is a big round of applause for Dr. Ifeanyi Ochonogo. His is slightly different from, while another person had talked on how to generate, his is on how to take care of what has been generated, used, and is to be disposed. So I want to very warmly appreciate you, Dr. Ifeanyi Ochonogo, for the presentation. You can see the applause received from the background showed that yes, your group, you people are doing what is expected in this environment, because we know very clearly that the removal of or the treatment of about 170 tons of e-waste, 170 tons, where 1 ton is about 1,000 kg. It's not a small thing. We know also that that treatment that has led to the removal of a minimum of 290 metric tons of CO2 that would have gone ahead to be contributing to the ozone layer depletion, the greenhouse gas that it is, and the problems associated with it, would have added to what is making the system not to be what it should be, and then the type of flooding and other things associated with it, not to talk about the food shortage and other things. So I want to appreciate what you are doing or what your group is doing. And you've started partnering with the Nano Research Group of the University of Nigeria. That partnership, we know, will lead to bigger achievements, both by your company and by the Nano Research Group of the University of Nigeria. Thank you once more for that presentation.
You're welcome. Thank you very much.
Yes, at this point, we will need to summarize. The day is very fast spent. We need to summarize on our activities today. You will recall that the day started with ions irradiation, induced defects, engineering in nanomaterials by Ishaq Ahmed from the Physics Institute in Pakistan, National Research Center in Pakistan. And shortly afterwards, we had the nanomaterials in electrochemical water treatment and sensor technologies from Professor Omotayo Arotiba from the University of Johannesburg, followed very closely by the nanomaterials for application to energy and health by the distinguished professor from the Wits University, Professor Ken Ozemena. We also had material sustainability through renewable materials from the Rajan Jos, our collaborator from Malaysia. Justice Ndokife pepped it up with the tweezer, the nano tweezers. And shortly afterwards, the nano interrogation of chloride-induced passivity breakdown in corrosion was taken up by Professor E.E. Oguze of the Federal University of Technology in Owerri. Yes, may I remind us that there was a review of eternal energy-based gravity versus renewable energy, the theory and prototype design for sustainable energy supply by Henry Isaac Elling. And that was followed by the paper from MV Reddy on novel electrode materials for energy storage. It is also on record that Chibeze V. Amanchuku presented a paper on controlling electrolyte molecular structure and ion solvation effects of lithium metal batteries. And the entire presentations today was spiced by the fact that it is not all about production. It is not all about generating these materials, but it is also about making sure that at the end of the usage life of these materials, that they are appropriately taken care of, as was elaborately presented by Dr. Ifeanyi Ochonogo. You will agree with me that it has been a very wonderfully spent day where specialists in different areas of nanotechnology and electronic waste recycling has, have led us to a lot of things. At the end, nobody will leave the venue today, nobody will leave the site for those that are online without having said that scientifically speaking, that they have been well enriched. So on that note, may I, on behalf of the local organizing committee, on behalf of the coordinator of the Nano Research Group, the University of Nigeria, Professor Fabian Ezema, on behalf of the leader emeritus of the Nano Research Group, Professor Rose Osuji, and on behalf of our major facilitator, our major collaborator, the the OESF Group Limited, and on behalf of the US Army that is also supporting us fully, say thank you very much for being here today. And we need to inform you that tomorrow that the plenary sessions will continue with another key paper that will be presented by many scientists from all over the world. So please, tomorrow at 8:30 in the morning, at 8:30 a.m., we are Nigerian time, we are gathering here to continue with the conference. And okay, yes, we are continuing tomorrow with the plenary sessions, which will be by visual stroke Zoom arrangement. And the presentation will shift base from the Princess Alexandria Auditorium of the University of Nigeria to the ICT Center that is opposite the Faculty of Engineering, where you have the Zenith Bank and Access Bank ICT Center. In those places, we are going to continue with the presentation tomorrow. So thank you very much once more for being here today. And we pray that you have a good night rest to be able to join us again tomorrow. Thank you very much.